Pranam, can you hear me?
Yes, we can hear you.
Okay. I don't have your headphone kind of gadget here, so okay. Karthik, hi. Morning,
Hello,
Karthik.
Karthik.
Hi.
Good.
Morning.
Yeah, it's being held pretty nicely actually. I really like the app. It gives you an actual feeling of the conference.
Yeah, the interface is like built like
Interface
that.
is
In
yeah.
fact, they have actually this hall they have done. It is like the lectural complex of the IIT Delhi. So they have
Yeah.
tried to
I,
somewhat.
correct. No, I could sense that. I know the ideally complex. So, but who is this doing? This is a private firm whom has been outsourced, I guess, right? Who has made this
Yeah.
India?
It's a private firm. Because this is a big conference, it's difficult to manage ourselves. So there's I think I'm forgetting the name, but it's probably written there in the website.
Mm-hmm. Yeah, it's there on the website.
So, but where is our first speaker?
Yeah, he'll enter with a bang. Exactly.
Speaker may be taking a flight now.
It looks like he has a paper on superconductivity yesterday.
Ah,
Oh, really?
So there is.
So, but I will restrict him to speak about spin interface only. No superconductivity.
This is the same material system where Icee Bangalore had a reported room temperature. I don't know, that paper got published ever, or I don't know.
So Arindam is right now. I think Arindam Ghosh and Anshu are giving a talk at Penn State or UPenn. UPenn, I think this week or next week, discussing what the recent results. So there is something happening.
Mm-hmm. There was one paper last month on another system where we have reported room temperature superconductivity, but at high pressure.
High pressure, yeah.
Well, I guess I don't know that it will go to it will go live on YouTube or to the and then to the website. Probably not. Not sure.
Call him? Or...
Let me see. There is 4 minutes to go.
Is it that, or I am hearing my things twice? I tell you once and then I am hearing it again.
It's just you.
Oh.
Yeah, I'm not hearing.
So Pranav, is it okay? So we have 25-minute presentation and 5-minute discussion kind of?
Yes. I think in this session all the talks are 30 minutes. So 25 plus 5 is typical. So we actually have some. I mean, we can go up to 1 o'clock. So there is we should not probably stop somebody if somebody wants to speak a little bit more. It's okay. So where is Subankar? Maybe I will call him.
Yeah.
Pranav, can you hear me? Pranav, can you hear me?
Yeah, we can hear you.
Okay.
Yes. Yes.
No, I because something was echoing to me, so I thought of putting the headphone back.
Okay. Yeah. Sometimes the headphone works better. Headphone. Otherwise, what you are speaking is basically going back to the microphone and
True.
some kind of.
Yeah. So he's coming.
He said he's joining, but he has not. I don't see him here yet. But shall we start? Well, there's 1 minute to go. After that, you can start introducing the speaker.
Okay. Yeah. So good afternoon, everyone. So in this session today, we have four talks. Three talks are invited talks, and one would be a contributed talk. So we have first talk by Professor Subhankar Vedanta from NICER. We are still waiting for him to join. And we have second talk from Professor Karthik Raman from TIFR Hyderabad. And then third will be by Professor Martin Bowen from Strasbourg, France. And the fourth one will be by Joy Narayan Mukherjee from TIFR Hyderabad. Okay. So, while we're waiting, let's introduce the first speaker, Professor Subhankar Vedanta. So, Subhankar Vedanta currently is an associate professor at NICER Bhubaneswar, and he did PhD from Duisburg in Germany. He did post. I think he did couple of postdocs. One from Duisburg, another from Princeton, and before joining at NICER, he did a guest scientist position at Forschungszentrum in Jülich, in Germany. And his areas of interest are flexible pentonics, magnetic multilayer, imaging, frustrated magnetic systems, 2D materials, all sort of things that relate to magnetism in a way. And he has more than 70 research publications. He's a recipient of D.A. Young Achiever Award, and he got few other awards like Young Scientist Award from Orissa Physical Society, as well as DAD Research Fellowship for exchange program between India and Germany for carrying out research for 1 or 2 months time period. That is him, and today he will be talking about Spinterface with Polarized. So we hope he joins us soon.
He's online.
Okay, Subhankar.
So,
Yeah, good morning.
Good morning. I have already introduced you.
Yeah, I've seen you. Thank you so much.
So please switch on your video. Yeah, good. Good morning. So Subhankar, you have 25 minutes to present, and have 5 minutes time share for questions and comments on your presentation.
So is my screen visible to you?
Yes.
Okay. That's
You
great.
can go full screen. Yeah, go full screen and use a pointer to proceed. Yeah.
Yes. So let me see the lecture. No. How should I minimize this window?
yeah, it's fine. It's fine. We are seeing the full screen. Just get the pointer and you can start.
Okay.
Subhankar, if you have a headphone, that is fine. If you have, because sometimes the echoes are coming, at least for me, so I have changed to a headphone.
Okay, actually, I'm trying to connect my speaker, but somehow, yeah, that is very bad. Actually, I have a Bluetooth speaker, but somehow it's not connecting. Just give me a second.
Sure.
Jyotiraj, can you hear me?
Yes.
Yes.
Hello?
Yeah, please. Subhankar, it is fine.
Well,
Please
I
go
can
ahead.
hear you. Just a second. Oh, very bad.
Yeah, I think it was working fine. We could
I
have
think
just
he could not.
continued.
Yeah, so Subhankar is gone now. I mean,
We cannot have the talk like this.
no, because without headphone, it echoes a lot. So he may not able to hear it properly.
No, I'm sorry. I'm not able to find.
No,
Uh,
Subhankar, no worry. Please go ahead, okay? Otherwise, we'll
Pranabhai, can you
lose
hear me?
time. Yes.
Hello, I
Yes, we are
cannot hear
hearing.
anything. Can you hear
We are
me?
hearing.
Yeah, we can hear you, Subhankar.
Somehow I'm not
We
able to
can
hear
hear you.
anything.
I think he can't hear, so maybe on a chat box you can message him.
Yeah.
But I think the Bluetooth that
That
he
is a
option that he,
problem.
yeah, the Bluetooth that you did, I think that disconnect and connect maybe
You
that
are able
created.
to hear, okay, but I'm not able to hear anything. Okay, fine. So then what I will do, I will continue. And if you have any problem, Pranavai, then you please drop me a message in WhatsApp, okay? Because I'm not able to hear anything. But is this echo better or it's similarly bad?
No,
No,
it
it
is
is
fine.
better.
It is fine.
I can't hear anything and I'm very embarrassed by this. Is this echo better? Okay.
There is no echo actually.
No, I'm not able to hear. Okay, I will continue. Just say, okay, I will continue. Just show me your finger like this, then I will continue. Okay, thank you. I'm not able to hear anything. So when you ask. Okay, fine. I'm really sorry for this inconvenience. So good morning, everybody. It's really my pleasure to give a lecture in this conference. I'm very much grateful to the organizers for inviting me for giving this talk to show our recent results and really putting a wonderful program altogether. In particular, I'm listening all the talks in the Spintronics kind of symposia with excellent speakers from around the globe. And I'm really thankful to Professor Muduli for his kind efforts and all his organizing team. So it's very nice coincidence that about a year ago, it's like 27th of November last year, I was in University of Strasbourg to give a lecture in the group of Professor Martin Bowen. And exactly like a year after, we are not able to physically meet, but I'm glad that at least we can interact through this web platform. Okay, so today I will be mostly talking about this Spinterface with fullerene, which is C60, and one type of organic semiconductor. And when we go through the lecture, we will see the importance of these images. So this is nicer in case some of you have not visited. We are close to Bhubaneswar. It's a nice campus, so you may visit us. I must thank my group members and my collaborators and funding agencies who have actually been very generous and helpful in making this work possible. And today, whatsoever results I will show, it's mostly the work carried out by these two PhD students. Srijani Mollik, now she is a postdoc at Thales Lab with Professor Manuel Bibes. Purva Sasarangi, she is in the final year of her PhD. Dr. Brajbhushan Singh is an Inspire faculty and he gave a very nice lecture 2 days back. Dr. Antajami Sahu is a new postdoc working with certain materials like rubrene, and Biswajit was a master student, now is a PhD student with Professor Eric Fullerton. And there are several people to thank and funding agencies who have been very generous, who can actually, who are actually doing the work. So my research interests are mostly related to food items. I mean, you can explain all the research in a very simple-minded picture. I will not have time to go through this. But today, whatsoever we are talking, it's mostly about organic spinterface, and we can relate it to biryani. I mean, we are close to lunchtime, and biryani means you you have rice, then let's say I'm talking about chicken biryani. So then you have a layer of chicken, then rice, and then you boil for some time, and you get the flavor of chicken in the rice. And similarly, if you consider now a system of ferromagnet and organic semiconductor, um, you will not have right away a very sharp interface like this. So if this is a ferromagnetic layer on a substrate, and then you measure the magnetic properties, you have another system of this bilayer composite where you have ferromagnet and organic semiconductor like fullerene or so. Then what will happen due to some interfacial hybridization, charge transfer, and so on? You will have a thin layer at the interface which will actually behave magnetic, but previously it was not magnetic from the organic. And that we call as a spinterface. This remarkable paper from San Vito about 10 years ago, where they showed that how this arrangement of these organic molecules on the ferromagnet can actually change the density of states at the Fermi level. For instance, here the organic is quite far from the ferromagnet, and this is the density of states for the ferromagnet, but here there is no spin splitting. This is basically a non-magnet. However, if you bring it close and you put it vertically or with different orientation, you can have actually some spin splitting at the Fermi level, and it will be like magnetic. And that's the basic idea of doing this heterostructure of ferromagnetic and organic. And then what is the advantage of C60? If you look, there is a big family of organic molecules, and C60 is something which does not have hydrogen, so it has almost no hyperfine interactions, and this carbon base is low atomic number, so it has very low spin orbit coupling. So you can use it in many spintronics applications. And if you look the electronic structure, so obviously its p orbital is half filled, so you can give some electrons, and there can be some electron transfer can happen. So that's basically the basic motivation behind these heterostructures. So I will be talking about various systems. So let's just jump into that, and some previous work. So I think Professor Cespedes' group from University of Leeds, where they showed a very nice work of cobalt and C60, and they performed neutron reflectometry, and they tried to evaluate the interfacial movement in C60, and they in a multi-layer they could show that the C60 is actually getting magnetic. It was very nice, but now in their model, if you look, the magnetic movement was not systematic, and there is some ambiguities in that model. But the good thing is that they could induce magnetic movement in the carbon, and second thing is they have shown that the interface magnetic movement from C60, which is ferromagnetic, and the ferromagnetic layer, they are actually aligned antiferromagnetic. So that was another nice thing from their work. And there are many other works where people have shown that how this C60 deposited on a BCC iron, then how much magnetic moment you can induce, and it has been shown that the carbon atom, which is just next to the ferromagnet, it has more magnetic moment compared to the carbon atom, which is a bit far from the ferromagnetic. And there is something called a 4-atom hole reconstruction, because this C60 is like a football, so you have to put it, and they have shown that to make a good structure. So let's say the 4 atoms of the ferromagnet will be removed, and the C60 will go and sit on that. So there are various experiments and even theories have been done, and this is a very nice work where they have shown that another organic material like manganese, this PC, where they have also shown room temperature spinterface. And I think I can skip. This is a really nice work from Paris, where they showed that if you take, a thin layer of cobalt, and we know if you increase the thickness of cobalt, then you get the spin reorientation transition from out of plane magnetization to in plane when you change the thickness about 1.5 to 2 nanometer, depends on your deposition system. But interestingly, what they found that you keep the cobalt thickness same, then you just deposit a different thickness of the C60, and depending on the thickness of the C60, the ferromagnetic behavior actually changes. It's a really remarkable result, I would say. And basically, you can tune the magnetic anisotropy from perpendicular to in plane just by depositing a layer of C60. Okay. Then, what are the open questions in the field? Because this field is actually growing really in a nice way, but still there are a lot of open questions. One of the question is, what is the thickness of spinterface up to which the C60 will show magnetic movement? Because you have a ferromagnetic layer, then you deposit say 10 nanometer of C60. Can we make the 10 nanometer of C60 ferromagnetic? I think no, but then up to what thickness? So that's also one. That is one question. What is the effect of this Spinterface in C60 on the magnetization reversal and domain structures of the heterostructure? Then, if you vary the thickness of the ferromagnet or the thickness of the organic, how is it going to change your magnetic properties? Then, if depending on different choice of ferromagnets like iron, cobalt, permalloy, cobalt, iron, boron, what happens? Then crystallinity, you can go from polycrystalline to texture to epitaxial, and all these are actually interesting systems and interesting questions. And to address this, so we have started with a polycrystalline iron. It is on silicon substrate. Several samples were prepared where we vary the thickness of iron. Okay, and actually we deposit the C60 thickness. So here this is the actual picture. So we have varied the iron thickness from 3.5 to 18 nanometer, and C60 it is more than 10 nanometer. And by seams, we see that there is some amount of interdiffusion, but the layers are nicely grown, which is shown from this high resolution cross-sectional TEM done by Professor Vishwarup Satpathy from SINP. And what we find that that for the single layer of iron, what happens if you look the magnetic hysteresis loops along the EG axis and you rotate the magnetic field from the EG axis, you get this kind of loops. So this is the EG axis loop, and the green one is the hard axis. Now you just do the same experiments for the bilayer sample where you have the same thickness of the iron. However, there is a C60 deposited on top of it, and you also compare the domains. So then you find that the anisotropy is actually decreasing by depositing C60, because if you see the coercivity is like 9 and here it's a bit less, and obviously that you can do more with ferromagnetic resonance. I will show in a minute. But in order to find out exactly how much thick at the interface is becoming ferromagnetic, we perform this very nice layer selective technique, which is called polarized neutron reflectometry. You come with a neutron beam with certain polarization, interacts with the magnetization of the sample, then it goes out, and depending on the magnetization, you can keep the same spin, or the spin can be reversed. So that way it is called a non-spin flip or spin flip. So you can look more about this technique. Then what we do, that we saturate the sample and we go to different points in the hysteresis loop, and we try to see how the magnetic movements and the thickness are actually getting magnetic, and that we can evaluate. So here in this bilayer, we found after really nice fitting that the magnetic moment of C60 now is about 1.37 mu volt, and the magnetic thickness of this C60 is about 1.1 nanometer for 3.5 nanometer. Now, if you increase the thickness to 7.5 nanometer iron, then you find the magnetic moment is slightly increasing, and the thickness of C60 is also slightly increased. You keep doing that, then we found for the 18 nanometer also it further increased, and this is the summary where it shows that the magnetic moment of C60 as well as the thickness of the magnetic C60 at the interface actually changing by changing the thickness of the iron layer. So that means it is also decreasing if you go down with the thickness. Now, in order to evaluate the anisotropy, we perform ferromagnetic resonance and angle-dependent ferromagnetic resonance spectra, and from that you can evaluate the resonance field, and you plot it as a function of the angle, and you fit with various model. And here we found the anisotropy for the single layer is 2.1 into 10 to the 4 joule meter cube, and for the bilayer it is unfortunately bit decreasing, and that we have also seen if you look in this hysteresis measurement, okay, because here the coercivity was a bit less. Okay, so then I think I can go to the next part where I will show now results of this iron C60, where the iron is epitaxially grown on an MgO substrate. The previous paper, that nanotechnology paper, was on a silicon substrate, so iron was polycrystalline. Here we have an MgO, and they have very nice lattice matching, and they grow and epitaxial films. Now we take C60 and we try to do almost similar type of analysis and to see the effect of epitaxy. And interestingly, we find for the epitaxial iron, the magnetic moment is remarkable. It is about 3 μ. This is the largest magnetic moment so far reported for fullerene cage so far. Okay, and the thickness of the magnetic C60 is about 2 nanometer for this epitaxial iron C60. Now let's look the hysteresis loop of this single layer and the bilayer, and I do not have much time to go into details, but please have a look to these papers if you want to understand more. That for the single layer, and the hysteresis loops are like this, from if you make parallel to the EG axis and so on, and the 90-degree, because iron on MgO, remember that it has 2 EG axes. There is an uniaxial anisotropy and there is a cubic anisotropy. And but interestingly, if you do a bilayer deposition, then the loop shape completely changes compared to the single layer. Now, in order to understand more, we have performed the hysteresis along with the domain images, and you see that for the 0 degree, there is not remarkable changes between the single to bilayer. There are just 2 90-degree domain walls are happening. On the right side, this video is showing how the reversal is happening. However, if you look the 45 degrees, obviously there is a remarkable change of the hysteresis shape, and that is also reflected in terms of the domains, because for the bilayer case, the second 90-degree domain is happening before the first one, and that's the region that you have this sharp drop in the hysteresis. You continue, this is one of the most puzzling loop where the single layer, okay, it's okay, but however, the bilayer, you have a very complicated loop shape, and that is because there are 4 reversals are happening, and which is corroborated by the domain images, and that is coming because the interface, the C60, that is becoming ferromagnetic, it is also contributing to the magnetization reversal behavior. Similarly, we have done the 90 degrees, and here it is not so prominent. So we found for the EG axis direction, the effect is not so prominent. However, for the angles away from the EG axis, the domain behavior is different compared to the between the single to the bilayer. Now we also did ferromagnetic resonance. So here I show the resonance field versus angle for the single layer and the bilayer. And very interestingly, for the bilayer case, we have a 2 order of increase in magnetic anisotropy. Please remember, for the polycrystalline case, the anisotropy was almost getting 50% reduced. However, for the epitaxial iron, you are actually getting a significant enhancement in the anisotropy. We have not understood this. It is unpublished, and we like to understand why in epitaxial case the anisotropy getting significantly enhanced. So this is a summary, and this work has been highlighted in the MLZ neutron reactor annual report last year. Then we continue to another system, cobalt, and here we saw that the magnetic movement in the C60 interface is a bit less. It's about 0.8 μ, and again there is the hysteresis loops. But interestingly, you see the anisotropy is getting enhanced in the case of cobalt. Okay, and also these are the domain structures. For the single layer, you see domains very small, very narrow band-like domains. However, for the bilayer, again it is band-like, but the width of the domains are significantly enhanced. Now, if you look at anisotropy, it is also getting enhanced for the case of the bilayer for cobalt and C60. Not so much like the epitaxial iron where it was 2 order. Here it is just like 30% more. Okay, now I will show some new results where we saw the results from cobalt iron boron C60 bilayers. Cobalt iron has a very interesting material because it has very low damping. It is mostly isotropic, and it is no Spinterface study has been performed in cobalt iron boron C60. In that direction, so Purbasa, she is working on this, and we have prepared few samples where this is a reference sample single layer, and these are bilayer samples where there is C60 of various thickness, and we found by increasing C60 thickness, the anisotropy is getting enhanced, and also the damping is getting enhanced. And later I will show that this is actually due to some spin pumping. Although C60 is low spin orbit coupling material, however, it is exhibiting some amount of spin pumping. Then these are the domain analysis for these three samples. This is the single layer, this is the bilayers of two different C60 thickness. Interestingly, we find that by depositing C60 here, there is not much change in the magnetic domain structure, like in the iron C60, where iron was actually epitaxial. So, and as I said, this cobalt iron boron is not epitaxial, it is just amorphous ferromagnet. So we find that when you have an epitaxial ferromagnetic layer, so then the domain structure are getting significantly modified. However, when it is polycrystalline or amorphous, the domains are not getting modified. Now, I will go to the all this research what I have shown up to now. It was all in plane magnetized thin films because cobalt thickness was like 10 nanometer, iron was like 10 nanometer, and so on. And it was much above the spin deorientation transition thickness. And here I would show the perpendicularly magnetized anisotropy. There are some research done, but we have chosen the cobalt platinum system, which is a very typical PMA system, and this is one of our work where we saw if you take a single layer film, there's domains are like that, and if you take an antidote which is not related to today's topic, we can engineer the domains. Just we took similar system, and now we have these very big bubble domains for the platinum cobalt, where the cobalt is like 0.8 nanometers, so it is much below the spin deorientation transition, and you have the bilayer sample where we have some C60 about 1.3 nanometers, like a monolayer thickness, and actually you see significant reduction in domain size. So by just depositing a monolayer of C60, you can do domain engineering, and this is very good for application point of view. Then we try to understand what is exactly happening, and then also we perform some relaxation measurements. So relaxation measurements are performed like this. Let's say you go to the negative saturation, you come and you put your magnetic field somewhere around this nucleation field, and then you fix the magnetic field. That means the Zeeman energy is fixed. Now you just relax it, and let's see what happens. So under the application of constant Zeeman energy and due to thermal activation, the system will expand and finally it will saturate. That's actually the point here, and this is the time, and you just take number of images, and you just take the average grayscale of the image, and you find out what is happening. And you get this kind of relaxation behavior. So finally, it's saturating from one magnetization state to the other, and by fitting, you find the magnetization relaxation time. Interestingly, for C60 also, it is getting faster. So faster is good for in applications. So we saw that in this perpendicularly magnetized system of platinum cobalt, if you deposit C60, you can actually do domain engineering and you can get faster relaxation time. Then we try to understand theoretically what is exactly happening at the interface, and for that we have a collaboration with Professor Ehsan Ali from INST Mohali, where he has tried to put C60 molecule on cobalt layer and try to find out the anisotropy energy, the charge transfer. So we found about 1.5 electrons can transfer between the HCP cobalt and pentahexa C60 interface, and this is good. He also showed by his research that there is a reduction of anisotropy, which is also we have experimentally seen. Okay, now I will next 2-3 minutes. I will talk about non-magnetic organic heterostructures. Previously, so far whatsoever I have shown, it is mostly Pranav is writing some message. Okay, it's fine. Let's continue. I'm losing time. So what happens if you take a non-magnetic like copper instead of a ferromagnet like cobalt iron? Then because copper is non-magnetic, C60 is non-magnetic. Now can you create magnetism in their interface? And this remarkable nature paper from Oscar Spinterface, where they told that they have beat basically the Stoner criteria. We know Stoner criteria means it is the product of density of states and the exchange integral. It has to be more than one. That's the reason in our periodic table there are only few elements which are magnetic, and that's basically is the reason why copper is not ferromagnetic. However, if you put C60 and copper, then there is some hybridization at the interface, density of states changes, and for some reason it is actually becoming ferromagnetic. However, this result not has been reproduced by any other to my knowledge, and in that direction we have prepared a series of samples of copper and C60 where we varied the thickness. And one interesting point to note from their paper is when they observed the ferromagnetism when the copper thickness was like 1.8 to 2.4 nanometer in that very narrow range. This is not understood why it's so, but we have prepared also similar range, and we found ferromagnetism in this case very similar to that their results. However, they have not quantified the magnetic moment, and that's what we have done it by XMCD. These experiments were done at the ALBA synchrotron source, and we found the magnetic moment for copper atom is about 0.01 Newton. So I think for the first time we have quantified this, and there has to be more understanding on this. Okay, just in last 2 minutes, I will finish that we have heard a lot of talks that when the heavy metal or any other metal like topological insulator or antiferromagnets where they have high spin orbit coupling, and if you put on top of a ferromagnet, you can have this spin Hall effect. I'm not going into details, so I can skip it, but I will show you that even in carbon-based compounds, you can actually expect to get the spin pumping, although the spin orbit coupling is very low. I mean, carbon is a low atomic number, and there are some papers by other groups where they found the spin pumping, obviously with some modification of their technique, or they put a platinum to enhance the signal. But in our case, we have been lucky to get also nice spin pumping signal in this cobalt iron boron C60 layers. We have calculated the spin diffusion length and the spin mixing conductance and the spin Hall angle, and this is an ongoing research, and I'm happy that we could also demonstrate that. So I'm at the end of the lecture. So I think I have convinced you that the Spinterface physics, which is very new, actually just a decade old, and it is getting more and more interesting, but there is still a lot to do in terms of understanding and exploring and doing a little bit of material science and going further. So with this short note, I'm actually done with my lecture. Thank you so much for your kind attention, and if you have questions, please ask. You may write in the chat window and I would be happy to answer.
Okay. Thank you, Professor Shivankar, for the nice presentation and overview of work done on ferromagnetic as well as C60 interface. Now, do you have questions? If Pranav, if you can see from the other end, please let me know. I don't see any chat window questions so far.
No, there is no question on the chat.
Okay.
Are you able to hear Shivankar?
Yes, I'm able to hear now.
Okay. Oh, okay, so, okay. So that's great.
There is a question.
Yeah, there is a question from Karthik. Okay.
Yeah.
Okay,
So in your domain,
the domain size increased from cobalt to cobalt C60. Okay.
Yeah, because your image magnification was different. One was 500 micron, one was 150 microns. So I just couldn't make out by looking at it.
You mean the perpendicular or in plane?
No, you showed
the in plane one. The in plane one.
39. Yeah, 30. No, 39, I think, the slide before. No, the one before the platinum work. No, before. We just go a few slides before. Yeah, there was one where you had a street. Yeah, this one. So here you said the domain size increases, but since the magnification is different, I couldn't make out.
Yeah, you are right. So I don't have. You are right. So obviously we have zoomed in, but I think even if you go to 500 micron, it would be still a little bit larger than the this. So exact analysis.
So factor of around two or three, not like tens or 100, right? Factor of 2 or something.
Yeah, I mean, of course, it is not like so. Good point that for the in-plane magnetized films, so it is like I don't know factor of 2 or something bigger. But when you do the perpendicular system, it is really remarkable here. So when you put C60, you are actually getting smaller domains, which is good, and much smaller because here the scale is same.
Yeah.
Yeah. So So I will look at it and I can tell you later. But it's a factor of 2 or 3, something like that.
Sure. Thanks.
Yeah. Thank you.
Pranav, do you see any other questions on the other side? No.
No, there is no question.
Okay.
Maybe I can ask one question.
Yes.
I was wondering, was there any coating on top of C60? In this case there is, but in the iron films you had iron, then cobalt C60, and then
no, there is a tantalum. There is a tantalum.
There is a tantalum. Always we put tantalum.
Tantalum. Okay.
Yeah.
And have you studied the reverse order where you have C60 first and then cobalt layer?
Well, that we have not done. So maybe for these polycrystalline films or amorphous, it would not matter much. But if you look the epitextual iron, so I think this work, okay, here it would matter because iron needs to be deposited on NGO to get the epitextual iron. But if you put iron on C60, then iron will become polycrystalline. So I think there is some research in our lab going on. Results are in preliminary stage. But I think that would be not very conclusive because the iron or cobalt whatsoever you deposit on top of the C60 it would have significant effect because the magnetic layer is not really crystalline perfectly.
Okay. So one question from Martin. Okay.
Maybe you can ask directly, no?
Martin, can you ask him directly?
Good morning, please go ahead.
Right. Yeah, good morning to all of you. It's nice to be here. Nice to be back in India, even virtually. Yeah, my question was, do you plan to try smaller fullerenes given that at almost 1 nanometer, well, you're starting to be far away from spinterface effects? You might, I guess you'll see why I'm asking the question in my talk.
Yeah, I mean, there is some plan, but we do this fullerene by thermal evaporation. So these organic materials a little bit difficult to control the thickness at lower limit. But in principle, this is something we want to do. Maybe not for C60, but maybe for some other organic materials. And it's a very good question. I mean, thank you. But this is not yet done. Just we have tried, but it has to be optimized.
Right. I mean, C60 is a standard molecule and somewhat easy to find. I've started looking into it. It's not so easy to find smaller ones that are cheap or commercially available. Then you have to start collaborating with chemists. Is that correct?
Yeah.
Okay. Okay, good. So Subankar, I would have a quick question before we close your part. So in the general question related to, so if instead of the 3D material that you're looking at, 3D elements, so to say iron, cobalt, nickel, you're growing fullerene on top of that, and then you're expecting, you saw a good amount of magnetic moment for cobalt, carbon 60. But how about if you grow it on a rare earth where the F electrons are, the carrier, okay? do you expect similar kind of things to be, to seen, or it is more that a 3D to P kind of, coupling that you see strongly here?
Well, this is something we have not tried. This is in our plan. Like we have just recently started work on yttrium garnet and C60. Of course, there are some people working on manganite C60 now. These rare earth, I'm not aware. Maybe some people have tried, but we are new in the game. People like Martin, who are in the game for long, I think they are doing a lot of good work. So this is something in our to do. But we will go slow. I mean, we have really, there are a lot to work in terms of materials and interfaces and so on. So I think this is something to be done in future.
Okay. So could you comment on the total spin moment that you have seen turned out to be quite high for C60. So I mean, compared to your iron system versus the polycrystalline system, okay, and the crystalline system, the MgO based one. The MgO based one are giving you better Bohr
Yes.
magnetism. So
Yes.
is it so what is being is it the spin part, or is it the orbital part getting more enhanced for the total magnetic moment that you're looking at?
Well, I mean, this is a very good question. I think I really do not have a clear answer. So what experimentally we observed that when you deposit iron on silicon substrate, so it is basically polycrystalline. So your magnetic moment is a bit lower, like 1.5 μ per C60 case. And when you deposit iron on MgO, which is epitaxial, and there if you deposit C60, so you are getting like 3 μ. So it's a bit higher, obviously. And why it is happening, I think theory has to tell. So, but so far whatsoever computation work has been done, they usually take a monolayer of, due to computational limit. So they take a monolayer of magnetic film and then try to put some organic and try to see how the hybridization charge transfer happens. Now, I have to talk to some theorist, of course, that how you can take a polycrystalline film and how you will take a epitaxial film. So these things, I think, have to be done. Or Martin can comment if it is already known.
Okay.
Well, Martin has another question. Maybe he can ask the last question before.
Yeah, you can.
Martin, please go on.
Well, you focus on the lower interface, and that interface is crucial for whatever devices you want to make afterwards. I'm concerned about my own work when it comes to the top interface, and because of interdiffusion. And I think you saw one of the recent articles of Vincent Repin, who took cobalt C60 as a model system and demonstrated that there's some interdiffusion at the top interface. And I was wondering if you could comment on that in the context of your experiments. And do you have are there any strategies, according to you, in order to improve the top interface structural and therefore electronic quality?
Well, I recall our discussions about a year ago, Martin. I don't know if you attended my lecture today from the beginning or you came just now. So I mentioned that about a year ago, I was in your lab. So November 27th. And I remember a nice discussion in the afternoon at coffee. You also mentioned about this question. But this is something we have not addressed so far. This was in the to-do list, but due to Corona, nobody was here. But we want to do actually a same system. We want to take and the capping we want to change and see how it is changing the magnetic properties. Because whatsoever we are doing, it is mostly coming from the bottom interface. But the top interface has something to be tackled. I mean, logically, there could be no effect, but I know Vanso has done good work, and it has some, and your group has also done some good work. I think it will have some effect.
Okay, so I think with that, let's thank Suvankar again for a nice talk, and all the questions we can still continue asking Suvankar anyway. So, and thank you, Suvankar. Okay, so let's welcome the other section. So thank you, Suvankar. Okay, take care.
Thank you.
And
See you.
yeah, and then with this we close the first presentation, and now I will introduce the second speaker of this session, Professor Karthik Burman from TIFR Hyderabad. So Karthik is Karthik Raman, yes, Karthik Raman from TIFR Hyderabad. So Karthik did a BTech from IIT Delhi, and then afterwards he did an PhD in MIT. And before joining KFR Hyderabad, he spent around 2 years time at IBM, basically looking at mostly memory-related applications and technology. Karthik's focus is in the area of thin film growth using both sputtering as well as MBE. More attention given to quantum material, 2D materials, and so on. And also he is interested in lot more spintonic aspects of this materials. And today he is going to talk about robust monolayer exchange bias effect in molecular crane pulley response at magnetic surfaces. Karthik, all you.
So
please,
you
yeah.
Karthik, you are muted.
Yes, Karthik, can you unmute, please? You are muted.
Yeah, I think, yeah, now you can hear me. It's just got moved to a different screen. So you can see the slides now?
Yes.
Yes. Yes.
Please go to the full screen.
Yeah. Is that fine now?
Yeah. Yes, please go ahead.
Okay. Thank you, Jyoti. So first of all, I should really thank the organizers, the Icee organizers for this wonderful session and the talks that's going on, and also Pranava and his colleagues for really working hard on this particular session and for inviting me for this conference. So let me start off by saying that I work at TFR Hyderabad. This is kind of the campus. The top view that you see here is a campus right now. And so the work that I'm presenting here today is primarily done by two students, Suman and Saurabh. And so the main story of my talk is summarized with a simple cartoon. So what I'm trying to essentially, the message, take-home message here is that which Shubhankar already presented a while back in terms of the strong interactions that molecules generally give rise to on the surface, on any reactive surface, and my focus here right now is on ferromagnets. So what you see here is an action where molecule, as if like a crane, really interacts strongly with the surface of your ferromagnet. And these interactions are so strong that you can decouple the magnetization of your surface from the bulk and giving rise to very interesting electronic responses. So with this, let me just share about the kind of work that we do in our lab. So this is a custom design integrated system that we have kind of built over the last few years. It has the capabilities to be able to integrate different material structures in situ and also perform some SEM measurements. So this is, so right now we're focusing primarily on three main projects. One is interface system microspintronics. That's something I'm going to talk about today. And we also work on topological insulators, proximity effects with magnetic insulators, or even superconductors. And we have another project on Kagame antiferromagnets. This is something Joy Narayan Mukherjee is postdoc with me. He'll be presenting later in this session, I think the last talk of this session. And he's going to introduce the nice results on chiral anomaly and wild fermion states that we observe in one particular antiferromagnet that he's going to talk about. So stay tuned for his talk. So let me now summarize or give you one slide overview of what the effects of molecule is on the surface. And this is the details are there in this reference in this review article in APL, which I had written a while back while I was establishing a lab here. So what you see here, typically when you have molecules on a surface, you will assume them to be physisoid. And this is true for surfaces like gold, platinum, or other inert surfaces. But when you have these molecules grown on reactive surfaces, say a ferromagnet which has spin polarized bands, you can create a strong hybridization between the two surfaces, between the molecule and the ferromagnet, and creating new interface states, which is just shown by a cartoon here in terms of simple bonding, anti-bonding picture, creating new interface states. And so the results of this is that you see that the electronic states that you observe in the interface is much, much different than you have at the surface of your ferromagnet or of your molecule. And how do you probe this is one technique is using spin polarized STM that people have done, where you see this bottom image here, where people have observed at different tip biases the spin contrast over the molecule. And they have simulated using theory and saw one-to-one matching, confirming that indeed the hybridization effects do play a role and are important in order to understand the strong chemistry and the physics associated with these materials. So what are the modifications one can observe? I mean, this is something that's really opened up in the last 1 decade, where you can observe strong changes in the electron spin density, and therefore spin polarization gets affected drastically. You can have changes in magnetic anisotropy, exchange coupling, and many other effects that is just being observed or starting to observe in the last couple of years. So with this, let me come to the basic part of today's talk, which is essentially focusing on this aspect of exchange bias effect. Now, just a simple schematic where you have a ferromagnet, and if you try to do a magnetometry on a ferromagnet, you try to measure MH response using a squared VSM or any other technique, you will observe a hysteresis to be centered around 0. Or you could also use an AMR technique, an anisotropy magnetic resistance technique, where you primarily just measure the resistance of ferromagnet as a function of light field. And you will see that at the coercivity, at the switching point, you will see in this case, for example, a drop in the response, in the resistance of the device, typically of the order of less than 1% in ferromagnets. So this is another technique which is very sensitive. Electronic technique is sensitive to the switching dynamics of your ferromagnet. So now what happens when you have a ferromagnet in proximity to magnetic hard layer is that you essentially shift the hysteresis from the 0 to primarily one side, which is exchange bias effect, which can also be observed in your AMR response. How do you observe this is, if you can just put typically how this is observed conventionally is you put an antiferromagnet, which has typically a large internal anisotropy in proximity to ferromagnet. And so when you're above the Néel temperature, your hysteresis is symmetric around 0. But as soon as you have your antiferromagnet domains aligned, say you cool down in field, then you create a strong interfacial exchange coupling, which gives rise to the shift in hysteresis. Now, the basic question or the basic understanding that has been prevailing in the last decade or more than a decade in conventional antiferromagnet systems is that when you typically thin down the thickness of antiferromagnet, in most cases, you will observe that your exchange bias gets weakened, and eventually it's a critical thickness below which the exchange bias just goes off to 0. And that's because you don't have enough internal anisotropy in your antiferromagnet to stabilize its domain. And therefore, they become part of the ferromagnet and switch along the ferromagnet, giving rise to a hysteresis response just like this, as you see here. And this is primarily when the field began in multi-exchange bias effect. This is a work done at Strasbourg, and Martin is here. He's one of the pioneers in reporting this phenomenon of exchange bias effect, where they observed that, of course, in their study, they observed that they could observe this exchange bias response all the way to around 60 to 70 Kelvin, and there have been reports, I think, up to around 9800 Kelvin, where they see exchange bias prevailing. And what they've observed is that below critical thickness, say 10 monolayer of this molecule, manganese tyrosine molecule, they don't see the exchange bias effect. It's very weak, and essentially it's not observed. And so the claim has been that you are creating an antiferromagnetic spin cluster chain here, which supports. Which essentially gives rise to an antiferromagnetic nature of your molecular film that gives rise to this exchange bias effect. And there has been questions in terms of so if you consider this molecule by itself, it typically shows antiferromagnetic nature below maybe around 10 Kelvin that has been reported. But when you put them on a surface ferromagnet, there seems to be an enhancement of this antiferromagnetic domain structure, giving rise to this exchange bias being reported all the way up to 40 to 50 or even around 100 Kelvin. And after this, there have been other reports around the same time and even afterwards in terms of cobalt PC, and then you have reports on other polyethylene structures, and even C60 recently, where there has been exchange bias response. But there has been some clarity that these exchange bias is also being reported in systems where typically the spin chain formation is not strong. So the question is, still rose in my mind. And therefore, this is also based on our previous work when I was a PhD student, which was reported a while back, where if you consider a vertical stack structure of, say, cobalt, a molecule which is zinc metal phenyl, and copper, we also observe very nice resistive response with an exchange bias response like phenomena, which is reported through a matter resistance measurement. So this is not, this is a spin filtering response that was observed. And we observe importantly that at the interface, we create a magnetic hard layer. So the magnetic anisotropy effects, one of the first reports using transport was done in these devices, where you could observe this surface magnetic hardening response with this structure. Of course, this is a vertical structure, and there has been subsequently other reports using various different techniques where people have reported this magnetic hardening response in different molecule ferromagnet structures, confirming that indeed hybridization effects are really strong at these surfaces. So that's what made us think that whether surface magnetic hardening is also possible reason for the origin of this exchange bias. And to really look at these effects, we devised a scheme which is to be able to do a systematic study of essentially choosing a certain device structure which is grown simultaneously, which gives us very good control. So what we did was to grow this layer of iron, for example, in a film of iron simultaneously. We cover one iron film by a mask, and then we grow the molecule. And then we cap it with standard capping techniques, and then try to look at the difference in the response of our control device, which is on the left, and the molecule ion device, which is on the right. And we've done this study for different thicknesses of ion and molecule. But primarily, we wanted to restrict our molecular growth to less than 5 monolayers, to be really sure that we are working in a regime where the bulk antiferromagnetic effect of the molecule is very weak or doesn't exist. That was the primary goal of looking at these devices when we started off. Of course, the first question is, how do you control the molecular growth to those extents? And this is something that we have good control. We have in situ STM. So for example, this is a question that typically is asked, whether this molecular structure integrity still retains on the ion or otherwise. So this is something that we can confirm by STM. Also, we have done spectroscopy measurements where there have been reports that they essentially move from 1 monolayer to 2 monolayer structure of these tyrosine molecules. You can see the negative differential conductance appearing. And that's precisely what we observe in our devices as soon as you go from 1 to 2 monolayers. And therefore, we have a good control on the molecular growth of both MNPC and cobalt PC in our system. So we started off with room temperature measurements, a standard Mock care effect, and AMR measurements, just to see how the two correlate. And they correlate 1 to 1. So we work with different thicknesses from 1 to 3 to 5 nanometers, 6 nanometers. So you have seen the summary is bottom here in the C plot. What you see is at higher thicknesses, 5 and beyond, it's very difficult to find any difference between the coercivity response of your ion control sample and ion with the molecule. And at low devices, at low thicknesses, you're perhaps very closer to the superparametric limit that at room temperature, the response is not very evident. So this is the region between 3 to 4 nanometers that's very clear that there is a hardening effect that's even observable at room temperature. And therefore, we restricted our study primarily in these two thicknesses range. Now, let us start looking at cool down response. Now, when you cool down the device, and these are the reference ion and the ion MNPC, exactly same thickness grown exactly in the same conditions especially for the ion layer. So there is no change in the growth conditions. So now when you cool down a device, you see that the AMR response of especially the ion MNPC system really enhances. You have a very much enhanced coercivity of your molecular structure compared to your reference ion. And this is shown here in the right graph, where you see an enhancement for the reference sign is very bare minimum, maybe factor of 1.5 to 2, whereas for the case of molecules, always 2 to 10, that enhancement happens from 300 Kelvin to 50 Kelvin. And this is explainable because typically when you consider, say, MNPC molecule sitting on a surface of iron, you would have perhaps around 16 to 20 iron atoms being bonded to the molecule. And if you just consider the phonon energy or thermal activation energy, typically say of the order of kT, say 25 millielectron volt room temperature, and then you have around 20 pounds, you have almost 0.5 eV of this excitation energy that is there for this molecule ion surface to be looking at. And therefore, when you cool down, typically you overcome this and you have a stronger interaction, a stronger hybridization effect that is forming, giving rise to the enhancement in the cohesivity of the system. So the strong pi-d hybridization induced enhancement cohesivity is evident, even from room temperature to low temperature around 50 Kelvin. So now we go down to below 50 Kelvin. And what we did is we cool down in whether we cool down, I mean, I can say right away, whether we cool down in zero field or in a small field or a large field of the order of 5,000 Icee. You cool down in field or zero field, and then you start doing your measurements. So in this case, we have an ion which is 4 nanometer, and then we have an basic molecule is 4 monolayers. We start off at low field range scans, 200, 300, 400, 500, up to 600 Icee. You see exactly no hysteresis. And this is a region where we call this as an exchange brink response, where you have a soft ferromagnet and a hard ferromagnet on the top because of the surface hardening, and you have essentially exchange brink response up to 600 Icee. Above this, you start seeing hysteresis response, and you have an exchange bias response that I just previously observed, except that in this case, exchange bias is not between antiferromagnet and a ferromagnet, but between a surface magnetically hard layer and a bottom ion layer, which is switching with respect to the surface. And this is what is clearly giving rise to the exchange bias effect, because our reference samples don't show any such response. So, this is a plot on the left showing data for zero field cool and field cool, and you will see that primarily the same response as I shown before, but you see that there is an enhancement in the cohesivity, but not much in the exchange. The exchange actually remains more or less the same, whether you do a zero field cool or field cool study. And in terms of its robustness, I mean, you will see this is a study that was done for monolayer work. You will see the robustness in terms of exchange going from 63 millitesla to around saturating at around 49 millitesla. And it's very robust, it's very stable, irrespective of the training response that you see here. Now, if you compare this with all previous work, which is kind of summarized in this plot here, you will see that the response in terms of exchange bias before training and after training. In many cases, there are not many reports, but I mean not many reports presenting both before and after training, but there are a few examples, especially 4 nanometer. You will see that in these systems, before training, the value is large, and after training, it really collapses to a smaller value. And one could understand this in terms of perhaps a combination of both responses, as Martin's paper had earlier reported, which is coming from the aniferromagnetic structure, which is in a way supporting the surface hardening response. But when you do a training effect, you kind of collapse the spin cluster here, and all the exchange bias is coming only from the surface effect. And that is evident here, where in our case, we hardly see any noticeable training response compared to all previous studies. So confirming that the surface hardening is kind of very robust, which shows up at lower thickness of your ferromagnet and stays there irrespective of essentially any measurements that you do. So this is a study of the robustness of the exchange bias. This is called healing effect, or we claim as healing effect, where what we do is we again measure the training cycle, which is done for 0.2 Tesla, plus minus 0.2 Tesla, but we measure the exchange bias and cohesivity after every training cycle. So what you do here is that first training, second training, third, fourth, and then at the fifth training, we actually apply a one-sided destabilizing field of 1 Tesla. And then we again do a training cycle measurement at plus minus 0.2 Tesla and measure the cohesivity and exchange. And we do this, go to one-sided destabilizing 2 Tesla, 3 Tesla, and 7 Tesla. And you see here that it temporarily destabilizes the exchange drops down. But subsequently, when you do a standard training cycle, it again heals up. And it clearly shows up how robust these molecular exchange bias effect is without requiring any antiferromagnetic system in your device structure. So this is the summary of all the measurements that we have done so far, going from 1 monolayer study of molecule to 4 monolayer studies. And what you observe is, firstly, that there is a drastic enhancement cohesivity. And as soon as you have an onset of exchange bias, field locking temperature, which you call it, where the exchange bias picks up, you see that the cohesivity suddenly saturates. Okay, it just flattens out, or there's a marginal increase in the coercivity. And we call this essential response as the origin of this response to be molecular grain pulley effect, which is summarized by here in this right side, which is a combination of not just surface magnetic hardening, but it's a combination of magnetic hardening and also the fact that the hybridization of the surface weakens the magnetic exchange interaction strengths, which extends deeper into the bottom ion layer. So what we show here is that, for example, at room temperature, high temperatures, if you assume that the surface has a switching field of, say, Hc surface is a phenomenological value, which is denoted only for a surface, which is higher, which keeps increasing as you cool down your system. But what you see experimentally is this black solid line, which is an average response of your surface and the bulk, is basically a volumetric average of your surface anisotropy and the bulk anisotropy. But you see this effect only up till this docking temperature. Below this, it becomes energetically favorable for the surface to really decouple from the bulk and let the bottom ion layer kind of switch independently. And when you see this, it gives rise to a saturating coercivity value with enhancement even now compared to your reference ion, which is much lower. So we've done very detailed systematic study in terms of a very simple model, which is extending the model based on Stoner's Wolfram model, assuming that the domains are large enough and the main contribution of your coercivity enhancement is coming from individual domains, which at the surface is enhanced by this molecular hybridization. And we have done angle dependent measurements of these studies, and we modeled a very simple case. We assume that, say, a molecule is sitting here, it's an MNPC4 molecule system, and we do a random monetization of this molecule and try to fit this data with all our experimental data. It seems like if you introduce a biaxial anisotropy term in the bottom ion, it seems to really do a better fitting than other anisotropy terms, and therefore it gives us an idea whether we are looking at the formation of a biaxial anisotropy induced by this surface hybridization into the bottom ion layer. And we have done this angle dependent studies where essentially we're looking at this asymmetry delta R, and we are probing this asymmetry of this AMR as a function of applied field along the in-plane axis. Okay, so what we observe is delta R essentially shows a very nice 4-4 symmetric response, but the details of this is essentially governed by the fact that when you do magnetization switching from top to bottom, how the magnetization switches, whether it is one-sided or completes a complete 360 rotation, affects the response in terms of how the asymmetry in your AMR response is. So to conclude our analysis of this Stoner model, which is available in our published article, which is that it seems like we are observing some kind of biaxial anisotropy, which needs further confirmation. But if it is really so, then that means that molecular geometry to some extent can really play a role in inducing some form of anisotropy in the ion. And so far, as I reported, that whether we cool down your field in zero field or in field, we hardly notice any change in the exchange bias. It remains absolutely more or less the same. So that made us wonder whether we can intentionally create any disorder or any magnetic disorder at the interface, or at the interface, or even the bulk ion. We don't know what's really happening. So what we did was we decided to cool down in oscillating field. We applied a oscillating field around 50 millitesla at around 0.1 hertz, and we cooled down below the blocking temperature. And then we did exactly the same analysis. And here what we observe is that the AMR response, especially the coercivity, drops down, going from a zero field cooled to oscillating field cooled. So OFC is oscillating field cooled, and FC plus OFC is nothing but a combination of DC plus AC field that we apply. And we see a systematic trend in terms of reduction in the width of the AMR. And also the coercivity goes down, which is shown here by this plot. So the question, which is very atypical, because if you take a reference ion actually coercivity remains more or less the same, but there is a broadening in the AMR response. The gamma value, which is shown here by this width, actually increases by creating this disorder. And this is in contrast to what is observed in these devices with the molecule on top. So therefore, the question arises that we are transitioning from a case where we have a monotonic increase in the coercivity cool down to a non-monotonic increase in coercivity, where you have drop, and also complete lack of exchange in the complete temperature range. The exchange remains more or less zero. So if you do further analysis, which is there in this archive, I can't summarize in a couple of slides, but the analysis tells you that we are able to create a magnetic disorder, which is not really at the interface, but extends deeper into the bottom ion layer, giving rise to a softening response. And such softening response essentially tells you that we have transitioned the bottom ion layer from a strong ferromagnet to a re-entrant ferromantic state or a re-entrant spin glass state, where you have spin glass domain formation, which coexist along with your ferromatic domains in the bottom ion layer, giving rise to these contrasting features. So the take-home message is that from these analysis is that the hybridization not only creates or gives rise to surface hardening response, which people have reported extensively in many FM molecule structure, but also the fact that the magnetic exchange interactions at the surface extending deeper into the bottom ion layer gets affected. And our work shows that we have brought them to a critical range of long-range ferromagnetism. We have weakened it enough that it's at the critical state of ferromagnetism. So to summarize my talk here, which is that there's lots to explore. This is a cartoon again, which tells you that the exchange interactions is something which so far has not been really focused much extensively in experimental groups. And this is an area where one could really explore and really observe very fascinating results in the future. So with this, I would end my talk and be happy to take any questions.
Thanks, Karthik, for the nice talk. Are there questions?
Yeah, Martin,
yes,
I think
Martin has a question. Martin, please go ahead.
Karthik, a very nice talk. Lovely fundamental work into the anisotropies, much needed relative to the state of the art. So that's wonderful. I had a first technical question. How do you achieve the AMR results? Are these in situ results that you're achieving by depositing and then transferring to some AMR station in vacuum?
No. So these are all capped with aluminum layers on top, and then essentially then taken out.
Okay. So yeah, that sounds good. My second question is: you notice that the coercive field for exchange, the exchange bias field for cobalt PC appears to be stronger than for MnPC. I think that this is a result that, is different from what we published in that Nano Letters paper of ours in 2018. But your study, I think, is more thorough. So I was wondering if you could comment on that.
Yeah, I think there's in the Nano Letters paper, I have to recollect, but so there are two things. Your films were grown epitaxially there. In the nation materials was grown epitaxially, but I'm not sure. The cobalt was epitaxial, but then in the Nano Letters paper, it was polycrystalline, or was it?
That's right. Yeah. We're on SiO2 with a buffer and so on.
Yeah. Okay. So I think in your case, there are two things to it. In cobalt PC, we have grown multiple samples. We have always seen it to be higher than MnPC and always touching 48 to 50 spot. More importantly, there is a small drop, which I could not confirm because we are limited with our resources. But this small drop, whether it is weakly antiferromantic, I'm not sure. But it's always the case that in our system, cobalt PC has been showing a higher blocking temperature than MnPC. It could be because of the thickness range involved, perhaps, where the bulk antiferromagneticism of a cobalt PC also contributes in a different way. So one thing which I want to just showcase in extension is that what we have done is this. So what we have done is we measured the coercivity for different thicknesses of ion. So since your work was primarily the cobalt one first was focused on thicker films of around 8 nanometer or around that range. So we see that, we compare with and without the molecule. First of all, you see that when you take 4 nanometer, the coercivity is dominated by the molecular structure. But when you take 8 nanometer of a ferromagnet, at low temperatures, there is hardly much enhancement because of surface dominant effect. But then if you compare the coercivity of reference and ion, at low temperature, they really shoot up. They really match. So it seems like the anisotropy of the bottom ion is dominant over the surface. And to be able to observe exchange bias, you need to be in this regime where the surface enhancement is evident.
While we're at it, on this slide, I noticed the final regime at low temperature, where this is a volume-dominated anisotropy. Is that correct?
For the 8 nanometer, it seems like because the reference coercivity and with the molecule they match, they kind of overlap, right? But so this slide tells you that why we don't see exchange bias in thicker films of ferromagnet, say 8 nanometer. Because
is this effect explained in one of your papers?
This is there in the supplementary material. This figure is there in supplementary material of the physical review of light.
Great, thanks.
Yeah, and there's explanation given for that.
Yeah, I think I'll leave it at that. Thanks.
Yeah, thanks, man. We never met, but it's the first time. I hope we have a chance to meet in person.
Okay. Is there any other questions? Pranav, you also see something? I don't see any.
No, I don't see any more question.
Okay. I'll have a quick one, Karthik. Is there any special reason that you have chosen aluminum as a capping layer? Because you are not essentially looking for any, kind of optical measurements like in this.
Yeah.
Okay. Except that you look at a MOC or data, right? But is there any specific reason for it?
Aluminum is good because typically you grow even 2-3 nanometers of aluminum, take it out, and it will oxidize and form a dense. So we don't want, typically you don't want moisture or things to go because you're taking out air. And this is a question generally because, so aluminum is not that actually just on the top, but even in the, if I show the schematic, we have in some samples we've grown below the iron also to rule out any oxidation effects from silicon oxide, because iron is a stronger oxidizing agent than silicon oxide, so it can oxidize a bit. And also to give controlled AMR, because when you grow iron 1.5 2 nanometer, there'll be strong thermal drift. So to compensate for that, we grow aluminum. And this is a study where even if we grow 5 nanometer aluminum on the molecule, we still can make aluminum superconducting. And that tells you that the aluminum is actually capped very well.
I had a final question on this fact. I mean, your molecular layers are very thin, and you're depositing the aluminum on top to allow it to oxidize and cap and protect. Have you tried any aging experiments? So you take a bar, you take it out, you measure it, and then I don't know, you leave it in air for 2 months in a humid environment, and then what happens to it? I ask because we've had to be sure of some of our experiments. In terms of avoiding aging effects, and the capping layer is crucial, especially when you have rather thick molecular layers that then induce a certain roughness that needs to be covered. The holes have to be have to be patched up and so on. So I was just wondering if you had done that, and if you haven't, it's no criticism of your work. It's more a reflection on the difficulty of the work. That capping is crucial, otherwise you can be led into error.
No, I agree. So this time we really haven't kept it for 2 months outside, but we have same device we have measured 2-3 times, starting from putting it on the probe, going to low temperature, taking it out, and again measuring after a week, just to look at the. Sometimes we miss doing some particular measurements. So we have done those things. It seems to be very stable. But on a month-long, we don't keep it in air. We have kept it in a nitrogen environment. So we haven't really started an aging effect in air.
I would try all combinations just once, and you'll feel happy about your results.
Yeah. That's why I said we grow reference iron absolutely the same way, and we measure it every time along with it when we do the measurements.
Yeah. But the capping capability will be different whether there's the molecule or not.
Yeah. Exactly. Agreed. So the wetting nature will be very different. But that's why we have this plot essentially showing that even if it's 5 nanometer aluminum, it's from the electronic point of view, it's transporting and turning into a superconductor. But yeah, this is something aging effect we're trying to do it. Thanks.
Good. I don't see any question in this chat window. Pranav, do you see anything else on the other side somewhere maybe?
No, I think we should move to the next speaker.
Okay, sure. Yeah, so thank you, Karthik, for the nice talk. So, and now we'll start had invited talk. So let me introduce the speaker today, Professor Martin Bowen from IP and CMS France, Strasbourg, and he did PhD in statistical physics from Polarized with Professor Albert Scott. His name goes, everybody knows in the community about Albert Scott and so on. Martin also did work at PDI, where we had some interaction with Martin, and he had done a lot of work with Eric Berupier group in France, and then he has more than 70 research publications, 5 patents. He is recipient of several grants and for his scientific contribution. Martin's current interest is in hybrid spintronics, mostly looking at organic spinterface, then spin polarized transport on quantum objects, then looking for the oxide layers for spin chains, and then he's also usually a member of a lot of several sustainable research activities at his current facilities. And today's talk, he will be discussing about harvesting the thermal fluctuations of paramagnetic centers using spintronics. Martin, it's all yours.
So thank you for the introduction. It's fantastic to be with you together in India virtually here. And I appreciate the notion of I've seen some of the Paul Drude Institute members reunite so many years afterwards in this context. So that's wonderful. Yeah. So I don't know if you can see my screen. I hope you can. I'm trying to go full screen now.
Yeah, we can see. Can you go for full screen? Yes.
Yeah, I'm trying to. Let's see. Yeah, I should be able to see this now. And there should be the way to get a laser pointer here.
Yes.
Do you guys know how to get laser pointer or change the pointer size on?
I think on your bottom left side, on your lower left, there are yes.
Mm-hmm. What do I have?
No, the third one from the left.
Yeah, thanks. So, as the introduction mentioned, we're working on, overall multifunctional electronics. This is the Rhine River between France and Germany. And I live right around here, but I work over there. And we use oxide and organics to develop multifunctional electronics. These are the typical materials that we use. This talk will be focusing on a rather new entry for us in the field of energy generation or energy harvesting. And as you will see, this fits into the overall session on spinterfaces because we're actually using these spinterfaces to do so. So this is the title of the talk. I will first describe certain other energy efforts, both in the classical and quantum realms of electronics and spintronics. Then I'll describe, in contrast to all of these other energy efforts, work on what we call spin engines here, and highlight results from 3 groups, including ours, and illustrate certain features of these spin engines, and, discuss the thermodynamical conundrum, the question that they raise. And the conclusion outlook actually would be, it would be great if others tried this too. And so, some of the work is outlined, the overall concept is outlined on this website. The colleagues in funding are as follows. The work on the first spin engine, the third spin engine in the talk was done by these 2 students, and the work in the 4th spin engine of this talk was done by these 2 Indian students, notably in the context of a CEFIPRA funding grant that I obtained in conjunction with Pranava. These are the IPCMS staff members with a nod to Eric Berupier, our colleague who passed away a few years ago, and other colleagues here, both chemists, people doing sample growth of MGO, synchrotron, ab initio, analytical theory, and so on. And the funding is provided below. In general, when we talk about using spintronics to perform energy harvesting, one rather exciting route is to harvest the electromagnetic radiation that is artificially created for our information needs, GSM or Wi-Fi, and spin torque nano oscillators have been proposed and implemented in this way. As you can see, there's a broadband response of a DC voltage that is generated when the EM radiation allows the magnetization of a top electrode MTJ to further precess, and so you can harvest this. Of course, the outputs are still rather low, and furthermore, this is artificial, so then the question becomes, what about a natural source like heat? Which brings us to the topic of spin caloritronics, which combines thermoelectrics, so this is how charge flow and heat gradients are related, and spintronics, in which you have a two-channel model of transport involving the spins, and therefore when you combine the two, you can get two heat channels. And these two heat channels, due to spin polarized transport, reveal what is the so-called spin Seebeck effect. So it's an effect that appears due to spin polarized transport generating a temperature gradient. Rather, it's the opposite, a temperature gradient generating spin transport. And so you see you have an offset of a couple hundred microvolts here. In addition, there's a second effect which relates to the reversal of magnetization of, say, two electrodes relative to one another. And this can also generate a temperature difference. And this is the so-called magneto-Seebeck effect. So in these graphs, you have a first offset, as I've seen, and then the second offset relates to flipping the orientation of magnetization. I also chose for this introduction an additional example of what happens if you use an antiferromagnetic material at its phase transition. So here, this is iridium manganese in part of a iron MgO MTJ. And you can see that for this thickness of iridium manganese, it has a magnetic phase transition, well, around room temperature, but especially the Seebeck voltage that is generated peaks at the transition, and this is because you have maximum entropy production at the transition. And you'll see that this has relevance for what comes after. So this is in the classical realm. If you want to go quantum, what has typically been done is to use 2D electron gases and perform patterning in order to electrostatically define islands of electrons that can be modeled as quantum dots. So there are a lot of electrons, and you're studying how an additional electron alters the system and so on. And so that's actually the reason why in these sorts of systems, you have to work at very low temperatures. A lot of electrons, n+1, means that the energy difference between levels is actually very low, so you need low temperatures if you want to address them discretely. So in these sorts of experiments, you have one quantum dot that is connected to a hot reservoir, and its population is affecting the population of the other dot through capacitive coupling. And so that you're studying how heat flow and charge flow is occurring in these systems, but in discrete quantities. So you've got a first experiment here, for example, another one that shows that you can reach a quite sizable fraction of the Carnot efficiency for these sorts of engines, but of course the power output is low. So if you have, if you're curious about this, you can look at these additional references down below. And as I've tried to explain here, these two quantum dots, the transport across the transport quantum dot can be enhanced if you break all of these possible paths of transport. So, you don't want to go like this, and you don't want to go like that. You can try to generate asymmetries by changing the electrodensities of states or the transmission functions across the barrier. So ideally, you would have a situation like this, where, this direction is allowed, but say even this one is not. And then you can really direct transport across the transport quantum dot thanks to the fluctuations of the other levels, that's right here actually, on the dot. And so this brings us naturally to the question of how, this community could increase efficiency. And we, in the spintronics community, have a good answer for that, right? We use spintronics to generate asymmetries. That's what the whole MR effect is about. And so there has been a theory about, how you could do this sort of stuff from a spintronic standpoint using spin valves. And so there's been studies of heat exchanges, even this more detailed, more intricate study of how when you bring two spins together and you couple them, and you also allow transport between fully spin polarized electrodes, you can generate a so-called quantum Icee swap gate. I should add that, all of this stuff does nevertheless require a temperature gradient. And there have been a few experiments that I detail here, but I will not get into it. The overall, scheme of things is that in these experiments, you still require low temperatures, you still have low output power, and there's still a temperature gradient that's required. So in this context, we come to the spin engines described in this talk. And I understand these spin engines as responding to the following concept. You have so-called spintronic selectors on either side. These are materials or ways to obtain a fully spin-polarized current. You also have paramagnetic centers in the center of this, and they are in an effective magnetic field due to spin-polarized charge transfer between the spintronic selector and these states. And so this is, you could also describe this as spintronic anisotropy. When heat mixes an incoming spin-up state here, mixes it and allows it to acquire additional energy, then this mixing affects, through the exchange coupling between the paramagnetic centers, the spin occupation on neighboring sites. And so you have a fluctuation-induced feedback from one paramagnetic center to another. This isn't the full story. This is the beginning of it. Notice here that KBT is larger than the splitting between either this state or the other states. It's very different from the spin engines the engines I described previously. In these systems, apparently no nominal temperature gradient is required, and the measured output power, well, you're going to see is, as the Americans would say, out of the ballpark. So these are the engines I will describe. I will gloss over quickly the first two and describe the last two in more detail, explain experimental features, and try to provide insight into how it operates. So the first engine was reported by Blount and Maikawa in 2009. They used manganese arsenide clusters as paramagnetic centers and manganese arsenide electrodes as the spintronic selectors. And so if they take a device, they cool it down to 3K, and they measure the IV in no field, well, the IV goes through zero. But if they apply a field, oh, gee, you have a rather large current offset in the absence of applied bias. If you impose a static bias and you ramp the field, you can obtain current that is either positive or negative. So basically, in this region, the device is passive, and in this region, the device is actually active and generating energy. If you measure an open circuit, you can obtain a spontaneous bias over minutes. All right. Spin engine number 2 is reported by the Mudera group. Here, the spintronic selector was a europium sulfide spin filter, and the paramagnetic centers were these aluminum quantum dots that are subject to an exchange field generated by coupling to the europium atoms of the spintronic selector. Now, they, I think, got the basic explanation right, though they say that here you're harvesting thermal fluctuations on paramagnetic centers. And if they measure a spontaneous bias on this system, not only is it present, but it tracks the magnetic orientation of the two electrodes. This difference in current that can be measured can also be tracked when the device is placed in series with an ammeter and a resistive load. And as you can see, as you ramp the resistive load, you get a maximum output power of about 30 femtowatts. This is a great experiment. I actually wish that we did it, but we haven't done it yet. Which brings us to spin engine number 3 that you see here. Here, we were, in the context of spinterfaces, trying to confirm the high spin polarization of the cobalt carbon, amorphous carbon spinterface, by inserting it at interfaces between MgO magnetic tunnel junctions. Now, this result has an important caveat. It was measured on only one device, but the results are quite surprising. So, indeed, we measure high magnetoresistance in the system at room temperature, 300%. There's no symmetry filtering effect involved here. So clearly, this is the first observation that spinterfaces can indeed generate a high transport spin polarization at room temperature. And the accompanying literature, which many of you know about on spinterfaces, is listed here. Notice too that the peak here relating to TMR is actually having a full width at half max that is much lower than KBT. And I'll get back to that later. And finally, that the, yes, in this region, the device is active. You have, well, not only is it active, but you have even opposite signs of IP and IAP, as I was showing before, for a spin engine 1. The power is about 0.1 nanowatts. So what that means is that for carbon, for MgO, MTJs at least, if you could scale this to the densities that are used in STT-MRAMs, if you could scale this, even at 1% engineering efficiency, you could obtain a quite sizable aerial power density compared to other techniques. For example, it's much more than solar, even before taking into account solar cell efficiencies. So in principle, this has a lot of potential. The question is, how do you reproduce this sort of result, noting that it isn't possible, it isn't easy to control the insertion of these carbon atoms into MgO. As a final feature of this spin engine 3, if you take IVs and you do the DIDV, here again, you're getting spectral features that are much lower than KBT. This is a fundamental question for all physicists doing transport. Normally, a transport experiment has a resolution that is limited by the thermal broadening at the Fermi level of your electrode. So you have a thermal broadening of at least 2 kBt, maybe 3 kBt. We have here a spectral resolution that is 100 times better, and that is quite surprising. So the path that we proposed in this paper was the result of performing analytical theory of transport. So we're using code that is usually developed to study STM-based junctions. And so we have 2 paramagnetic centers. We have spinterfaces represented by other quantum dots actually in the system with a somewhat larger but still narrow density of states. And we're allowing the system to evolve as bias is applied. So all of the final results actually depend on the applied bias. All of the level broadening and exchange coupling is bias dependent. We limited the parameter space by imposing that the outer part remained the same whether we study P or AP. And so this allowed us to actually reproduce our experiments. So I'm showing here the theory spin by spin channel. One thing that you can see is that, for example, here, the spin down channel is strongly transporting in the negative direction, and whereas at positive bias, it is actually the spin up channel. You don't see it here, but in fact, the J, the exchange coupling, is varying as a function of bias. This is spintronic anisotropy, and at V equals 0, the J is negative. And so there is indeed a very good agreement between this sort of modeling and our experiments, noting how unusual these IVs and TMRV are. We've worked quite a bit in general on trying to understand what is going on in MgO spintronics from the standpoint of oxygen vacancies. And in fact, that was the focus of the CIFIPRA project with Pranaba on trying to link these localized states that you see down here, single and double oxygen vacancies, with a spin transfer torque. So we took this knowledge and tried to figure out, well, what state could we have in our junction that is paramagnetic near the Fermi level? And we've determined that in this particular case, what we have is the presence of a carbon dimer in 4th nearest neighbor configuration that provides the correct sign of J and the presence, indeed, of paramagnetic states at the Fermi level. So, well, that was nice, but we only had one device. This was very difficult to publish. And more generally, it shows the need to be able to control the insertion of paramagnetic centers into spintronic device. And if you could do so in a controlled way, you could even access the exchange coupling. And the answer here is to use magnetic molecules, metal phthalocyanines, which were extensively introduced in the previous talks. I would note that the exchange coupling J here is dependent upon structural properties. So if you vary the sliding angle in these, well, here this is in thin films, then you can vary the J over a wide range of temperatures. All right. So what we've done is we've taken iron C60 spinterfaces, nice previous introductions by Kapik, and we've used cobalt PC molecules for the paramagnetic centers. So As you know, paramagnetic centers on a PC chain are not fluctuating if they are deposited directly on the ferromagnetic metal. But if we intercalate C60, then you can reduce the effective magnetic field that is being felt by these centers due to coupling to the underlying ferromagnet. And so you obtain this hybrid condition of fluctuation, but within an effective exchange field and an effective spin splitting. So we designed our devices as follows, and it turns out that when you look at band alignment, the cobalt spin 1/2 state of cobalt PC does lie indeed at the Fermi level of our iron electrodes and the spinterfaces that they generate with C60. Notice that we have an asymmetric stack. We have 1 to 3 monolayers of C60 on the one side, 5 on the other, and 3 monolayers of cobalt PC. This work was actually done by these 2 PhD students, Bhavisha Shaurira and Lalit Kanpal, who respectively performed the growth and the nanojunction processing. I would add that we have developed a resist and solvent-free 300 nanometer wide organic nanopillar process that would be very useful for the community. We are ready to collaborate with others on trying to to bring about more of their results in this way. So if you were more interested in the process and in some of the questions that arise when you do not have the C60 interlayer spacer, i.e. relating to exchange bias effects, you can see this, this article here. Now, we've obtained results on 9 devices, so we do have reproducibility, and I'm presenting here 3 of them. So on one of them that I present here, what you notice is that you have spontaneous current and bias voltage over quite a long time. In the bottom graph, you see you obtain spontaneous current over up to 2 hours. Students got bored, and I told them we had to keep measuring. The IV is offset, yes. And in addition, if you zoom in at low bias, you see that actually there's a deviation from linearity in this particular metallic device. And if you take the derivative of this device, you again see in the DIDV spectral features that are way below KBT. And they are actually enduring over a wide temperature range. So you can see from 40 to 40K, you obtain the same thing. And so here we've improved our understanding and believe that what is going on is that this feedback mechanism here can generate a reduction in noise, and that when you are actually allowing through an applied bias these molecular levels to cross or not cross each other, you're generating these features. So the noise reduction due to feedback is explained in this nanotech paper. From a spintronic standpoint, these devices definitely generate a response. So on this junction C here, you see that if you go from a zero field and you apply an in-plane magnetic field to alter the magnetic orientation of your 2 spintronic selectors, here are the spinterfaces, you get a wide range of change in current. And in fact, for certain bias conditions, you can obtain negative and positive bias for the same value of fixed DC voltage. Now, since these IVs are offset, if you want to calculate resistance, you need to take the slope of your IV, i.e., you need to take 2 points for points on each of 2 R of H's in order to calculate the slope resistance. And in that case, you can extract the field dependence of resistance the way we normally would do, and therefore you can calculate MR. And MR is very high. Optimistically, it's almost 800%, which is a record for molecular spintronics, and translates into a 90% spin polarization of the iron C60 spinterface. And that's important, right? Because you want this to be highly spin polarized so that certain channels are blocked and certain channels are allowed. On device C, which was semiconducting in behavior, we observed a record 450 nanowatts of power, a huge increase over other results. But more interestingly, if you study the temperature dependence of this output power, which is represented here, you see that on this log scale versus 1 over T scale, you have 2 energy regimes of activation. There's a crossover at 120K. Now back to the slide on superexchange interactions and general magnetic exchange interactions. We believe that 120K is in fact our exchange coupling between paramagnetic centers. It is close to the value for alpha cobalt PC. And remember, we're depositing here on C60 with low interaction, so this would make sense. And it's close also to the 70K value that is not only seen in the exchange bias experiments that we published and that others have seen, but also that we observe in magnetotransport experiments across nanojunctions. And so what that means is that in this system, we have evidence that a magnetic phase transition between uncorrelated fluctuations and antiferromagnetically correlated fluctuations is driving output power. And this is important because, well, it strengthens certain of the elements of the concept that we proposed, a coupling between paramagnetic centers, fluctuation-induced feedback, and it also helps address this thermodynamics conundrum, which is that all of these engines are operating at nominal thermal equilibrium. So how do you extract work when you have a single heat bath, basically? How do you break the thermal or thermodynamic equilibrium? And so in this paper of ours, which is on arXiv and has all of these results, we are providing certain answers to this for future work. So if you run a current across paramagnetic centers, the local temperature can increase. If you have coupled paramagnetic centers at the phase transition, at the electrically driven phase transition between these paramagnetic centers, you can obtain a non-zero entropy production even when there is no temperature gradient. And then more subtly, if your engine contains material, quantum material that is at a phase transition, it is possible to overcome classical thermodynamical limits, such as, for example, having finite power at the Carnot limit. If the engine has quantum correlations, it's also possible to extract work from a single heat bath. So these are some directions into explaining how it's possible for these engines to do what they do. So the take home here is that there is a context in which spintronics is being used to harvest energy, whether artificial or natural, and there are also quantum heat engines, including spin. Relative to that work, the engines described in this talk are unusual. Their design is summarized in this in the schematic here, and they appear to have been observed by now 3 groups on 4 results. And despite a thermal equilibrium that is apparent, they have striking features. So, of course, we're using spinterfaces, and we see evidence experimentally for high transport spin polarization even at room temperature. Enduring outputs, such as 2 hours of output current like this, sub-kBt resolution, which really should bring physicists to consider this very, very carefully. This is a very unusual result. And high power at room temperature, which appears also to be driven by magnetic phase transition. So if you can do it, try it too. It'd be nice for others to try this as well. If this could be taken to the industry, would be an energy game changer, though I do note that funding is very hard to obtain for a subject of this nature. And more information can be found on this website. And with that, I thank you for your attention, and we'll take questions.
Thank you, Martin, for nice talk on the spin engines. Are there questions now? I don't see here, but Pranav, do you say something from your end?
No, I haven't seen any question.
Hi, Martin. I had a short question. Maybe I couldn't grasp this quickly, but then you see the TMR of your response going from positive to negative? So the origin of this change is you're attributing it to the coupling strength, J changing sign. Is that, or is something else that is contributing to change in sign of your TMR?
You're referring to the graph you now see on the right, is that correct?
The slides are not moving. Maybe
I think I'm still sharing my screen, right? And you see.
Yeah, you are sharing your screen. The one where you're seeing a 300% going from positive to negative TMR as a function of applied field.
So this is here. Is that correct? Yes. As a function of applied bias?
A function of applied bias. Sorry. Yeah. Yes. So what's the origin for this change in sign? generally.
Right. So what is going on here is, and this is why the analytical theory that we were able to provide with the paper has value.
Yes.
What is going on is that, so you place your paramagnetic centers between the spintronic selectors, and due to spin polarized charge transfer, even in the absence of an applied bias, you have a J that can be modified by the transmission between these paramagnetic centers and the spintronic electrodes. So that's one thing. And then when you start applying a bias, you change the energy levels, the positions of all of these levels relative to one another. And so this dynamically alters the exchange coupling between the sites. It changes the density of states on each of the paramagnetic centers and their coupling. And so in the
the coupling also changes sign? I mean,
yeah.
Right. Yeah, exactly.
I don't think I have. If I were to show this, I don't think you would be able to see it. You'll have to go to the paper and the supplementary information. This is one of these nice features of spintronic anisotropy, which is that you can design a device in which you are dynamically changing the coupling as a result of flowing current, spin polarized current. And so the short answer to your question is that when you see a situation like this, what is happening is that you're dynamically changing the coupling, and you are able to alter the fundamentals of spin polarized transport across your device. And that's precisely why you have a regime, for example, here, where you can have IP and AP of opposite sign, whereas, say, in this other case, that would not take place.
Very interesting work. I'll have a look at it. Thanks, Martin.
Subhankar, you have a question? Please go ahead.
Very nice presentation, Martin. On this slide, so how do you actually evaluate the KBT?
It's simple. We take 295K and we calculate what that means in milli-EV. And that comes out to 25 milli-EV.
All right. So it is just for that particular temperature. All right.
That's right.
Then I think in one of the subsequent slides, there was a plot where you plot this J versus something. So how this J also you are evaluating?
Are you talking about the analytical theory?
No, experimentally.
Then you must be referring to maybe this slide or an accompanying slide, like say
this slide is fine.
This one.
This one is okay. Yeah, this
like
one
this
is.
one.
Yeah, this one.
Yeah. So we in Spin Engine 4, it turns out that the bias range where we have these effects, this nonlinearity, is low enough that we are not confident to apply analytical theory to actually extract a J and track its bias dependence. That being said, we know from literature that J can vary quite a bit depending on the stacking angle. That's what these results show. And what we also see is that a J of about 100K corresponds to Kuppel PC in a natural phase, the alpha phase, and that this is rather similar to this break in the output power, the thermal activation of the decrease in output power, or of the offset bias, whereas, as you can see here, when you just look at the slope resistance around low bias, there is only one activation energy. So clearly, while the resistance at low bias is just tracking a normal activation energy relating to hopping between sites and so on, these elements related to energy generation seem to have two activation energies. And so we're not tracking J, we're just extracting a value here there's clearly a difference in behavior around 120K. And we believe that in a similar fashion to what is being seen in these exchange bias experiments, that this is also a signature of this magnetic phase transition between a regime of uncorrelated and correlated antiferromagnetic fluctuations. And so this phase transition, of course, if you come back to a Spinterface description without a spacer layer here of C60, this corresponds to the onset of the exchange bias effect.
So basically, it is the kind of inflection point where this slope changes. So that's what you tell as J by KB.
That's what we attribute this change to. We do not have additional evidence of this. We just note that it's at 120K. We note that, as I say here, we note that when there is no C60 spacer, well, we have a J over KB of a 7K, and we see this magnetically. In this case, for this paper, we actually model our R of H's. They're very complicated, but we're able to model them, and we extract this, and we also provide analytical theory to describe this. I don't think you'll see it in this paper, but we have it in a subsequent one.
Okay, I will read it. I still didn't get the complete answer, but I will read your paper and probably that will clarify. Otherwise, I will drop you an email.
You should, we'll definitely talk more about this. This is basically the transport counterpart to your studies.
Yes. If I'm allowed to ask one more question, Chairman?
Yeah, a quick one, please.
Okay, a quick one. So in this structure, C60 in between the iron and cobalt PC. So how is the interaction is happening between C60 and cobalt PC? So there is a spinterface between iron and C60 cobalt PC interface.
Yes, you're right. We to first approximation have not. I mean, there is going to be an interaction. There is going to be an interface dipole that is created. So we propose this band model based on electron affinities and so on. So clearly, because there's a slight mismatch, there is going to be. You expect there to be a charged dipole at this interface. That's correct. We, to first approximation, have neglected it.
Okay, thank you so much.
Okay.
Well, thanks again.
So,
thanks for your interest, Tom.
So there is other question, but Martin, I have a quick one because we are running out of time. So you started with when you were discussing in the beginning, you have given an example of manganese arsenate system, and then you have come back to iron MgO and so on. So why do we can't we go for a system like half metallic, where we expect that spin polarization quite high, and then do your spin engine business over there? Okay, why we are stuck with iron magnesium oxide?
So I mean, that's what they did in 2009. I think they stumbled on the results just as we did with the carbon stuff. And then you have other endeavors using spin filter and so on. I mean, so you technically could do a half metal, right? Whether it be a Heusler alloy or a manganite and so on. I would actually argue that spinterfaces are pretty practical. It's a 3D metal, super simple. You put molecules on top, you get it to work at room temperature, and this is in fact a strength of our results. We prove that these spinterfaces act as spintronic selectors at room temperature with very high spin polarization. So I guess my question would be, from an applied standpoint, why would you want to use a complicated material if you can achieve the same result using other means? And I say this as someone who studied LSMO for quite some time.
Okay. Thanks. Okay, so there are not other questions. Let's thank Martin again for a wonderful talk. Okay, and we'll move on to the last presentation by Dr. Joy Narayan Mukherjee from TFR Hyderabad. So Joy will be talking on negative magnetic resistance in a non-collinear antiferromagnet, which is basically induced due to the chirality. Okay, chirality anomaly. Joy, please go ahead, and you have maybe 12-minute presentation, and then we have a couple of questions. Please go ahead. Joy, you can unmute, and then please continue. You are still muted. You are still muted. Can you unmute?
Yeah. Hello everyone. I'm Joy Narayan Mukherjee, a postdoctoral fellow at TIFR Hyderabad, working with Dr. Karthik Raman. So first, let me thank organizers for giving me the opportunity to present our recent work on anisotropy epitaxial thin films. Yeah. And I would also like to thank Department of Atomic Energy and Department of Science and Technology for the research grant. So in this talk, I'll be talking about the chiral anomaly induced negative magnetoresistance in a non-collinear antiferromagnetic thin film. Recently, non-collinear antiferromagnets have attracted enormous interest to the research community due to its special hexatriangular or Kagome type spin lattice arrangement, which can be seen here. And it also possesses finite Berry curvature and linearly dispersive Weil cones, which gives rise to exotic transport phenomena. And most of the work in this direction has been performed on Mn3 tin and Mn3 germanium compounds, which are hexagonal, and they also do have a Kagome structure along the 100 plane. In our system, manganese platinum, which is a cubic one, and it also has a Kagome plane, however, it is along the 111 direction. Therefore, one expects that platinum would also show some exotic transport phenomena. Before going to the experimental results, I'll shortly describe about Weil semimetals and chiral anomaly. So this is the cartoon of the band structure of the Weil semimetal, and you can see there are linearly dispersive band crossing, and each crossing points are called as Weil nodes. And these Weil nodes in the momentum space always arise in pair, and each Weil nodes acting as a monopole and anti-monopole of the Berry flux. Therefore, the total monopole charge over a Brillouin zone is 0 and the quasi-particle excitations has been described by this Weil semimetal by Weil Hamiltonian given by the Professor Hermann Weil in 1929, where this plus minus sign is described for the chirality of the Weil fermions, as they have a finite chirality or handedness of these Weil fermions. And this is a typical band structure of this Weil system, and you can see near the Fermi energy there is a linear band crossing which is known as Weil points. And this from this band structure calculation one can calculate the Berry curvature, and which can predict the anomalous Hall conductivity, anomalous Nernst conductivity, and many more properties of a system. And we can see here the Berry curvature calculated from this band structure has a finite value, and then the anomalous Hall conductivity and anomalous Nernst conductivity is also having a definite value near the Fermi energy. And these values are comparable to the normal ferromagnetic material as earlier reported in experimentally. In parallel to the density functional theory calculations, one can do also the angle reserved photoelectron spectroscopy measurements to probe the Weil fermions in a system. So this is the result. Arsenide, first experimental evidence of Weil fermions in tantalum arsenide came from the two groups, one from Princeton University, another from Chinese Academy of Science, where they have observed the Weil fermions from the angle reserved photoelectron spectroscopy and also supported from the density functional theory. Here you can see the linear band crossing near the Fermi energy. And as we have seen that bulk Weil cones and Fermi arc surface states in the Weil semimetals, and they do also have the definite chirality. And due to this, their fermions gives rise to exotic properties in the sample. Now there are two types of Weil semimetals, type 1 and type 2, depending on the position of the Weil points in the momentum space. If it lies on the Fermi energy, then it is a type 1. If it is in either electron or hole pocket, then it is type 2. And these chirality induced phenomena gives rise to negative longitudinal magnetoresistance and planar Hall effect. There is chiral in a system, in a Weil system, when electric and magnetic field is not present, then the left and right-handed chiral Weil fermions are present equally in number. However, if we apply the electric and magnetic field parallelly, then electrons from Weil nodes to another Weil nodes can pump up different chirality, and therefore gives rise to extra conductivity in the system, which gives rise to negative magnetoconductance. And this pumping rate is proportional to the dot product of electric and magnetic field. As soon as these wild semi-metals have been proposed, then these chiral anomaly experiments have been observed in different systems like wild semi-metal and Dirac semi-metal. This is the example on tantalum arsenide, where the angle-dependent magnetoresistance has been performed, and can be seen that positive to negative resistance has been observed. With temperature and gate voltage dependence has been also studied. Recently, in 2017, in Mn3 tin system, also this chiral anomaly has been observed. However, this is on single crystal, and this is having a Kagome plane along 100 direction. Therefore, Kagome metals are also interesting in this direction. So coming to the Kagome metals having also linearly dispersive band crossing and flat band near Fermi energy, and they do also have finite momentum space Berry curvature. Therefore, they are having also exotic transport phenomena. This is another example of Kagome metal, which is ferromagnetic, Fe3Tin2, and from angle result photoelectron spectroscopy and density functional theory calculation, you can observe the flat band near the Fermi energy. In our system, Mn3PT, which is a cubic, as I have described, and it has a lattice parameter of 3.0 with a space group PM3 bar M. Platinum sits in the corner side, whereas the manganese in the face center position. It has two different transitions, one at 365 Kelvin from non-collinear to collinear transition, and 475 Kelvin is the nil temperature. This is the Kagome plane of the Mn3PT along the 111 direction, and you can see manganese in that one triangle is all in and another triangle it's all out. So this all in all out configuration has been observed in the platinum system. Therefore, one could also expect these non-trivial transport properties in this manganese platinum. So keeping all this in mind, we have grown these manganese platinum thin films using our customized star style sputtering chamber, and the deposition conditions are tabulated here. After the depositions, we have performed the X-ray diffraction, and we observed only the Mn3PT200 peaks along with the substrate peaks. These can be zoomed here, and we observed that a 2.4% of strain in this thin film, which is inconsistent with the previous report of manganese platinum grown on barium titanate substrate. After confirming the phase purity, we have carried out the 5 plane, and we observed the 4 equally spaced 90-degree apart peaks which are coincide with the substrate peak. This confirms the epitaxial growth of the sample. Then we have also performed the X-ray reflectivity to determine the thickness and roughness, and we found out the roughness of less than 1 nanometer, which tells you the very smooth nature of the sample and the drop surface and the interface. After confirming the structural properties, we have studied the phenomena on this Hallmark geometric device. This Hallmark has been prepared using the optical lithography and argon ion milling. So this is the temperature dependent resistivity plot. As we decrease the temperature from 300 to 2 Kelvin, the resistivity decreases monotonically, and we have calculated the resistivity ratio is almost 26, which confirms the good crystallinity of the thin films. And then we have applied the magnetic field perpendicular to the current direction or perpendicular to the film surface. And as we increase the magnetic field amplitude, the resistivity increases significantly. However, we have not seen any metal to semiconductor-like transition. Therefore, we have performed the magnetoresistance measurement in the out-of-plane geometry when the magnetic field is out of plane and from 2 to 40 Kelvin, and we observe a high positive and non-saturating non-linear magnetoresistance. At 2 Kelvin, the magnetoresistance at 8 Tesla of magnetic field is almost 33%, which is almost similar in 5 Kelvin, and then significantly decreases as we increase the temperature. This high and non-linear magnetoresistance is not common for a metallic system, which gives a topological hints in these Kagome materials. Therefore, we have varied the angle of this magnetic field, applied magnetic field, with respect to the current direction. So 90 to 0 we have varied. 90 corresponds to out of plane and 0 corresponds to the in plane. As we vary the angle of this magnetic field, we see this magnetoresistance percentage decreases, and finally at the in plane configuration, magnetic resistance becomes negative, which can be clearly seen in this plot. When this when this current and the magnetic field are in parallel, the magnetoresistance is first positive at lower field and then goes to the negative. This region is due to this positive magnetoresistance is small positive magnetoresistance due to the weak anti-localization behavior of the sample. Then we have varied the angle in the small step 0 to 5 degree. We have seen this negative magnetoresistance, and after the deviation of 5 degree, we could see the again positive magnetoresistance. At different temperature also we have seen this negative magnetoresistance, and here in this plot we have plotted the magnetoconductance, which becomes positive when the electric and magnetic field are parallel and goes negative when they are not in parallel combination. So after and as we increase the magnetic field strength, this behavior getting sharper and sharper. Therefore, which confirms that there could be a chiral anomaly features in this sample of this MN3PT. To further confirm it, we have taken a semi-classical formula which tells you that sigma 0 is the conductivity when magnetic field is not there, and second and third term describes the chiral anomaly and the weak anti-localization features. And we have fitted with these equations, and we could see up to 6 Tesla it is a good fit and deviates after that. This is a semi-classical formula, and when the magnetic field is more than 6 Tesla, it's going towards the quantum regime, and therefore we expect a deviation. And this is a plot of this chiral coefficient, and which decreases as the temperature increases. Now, to further confirm this chiral anomaly, we have also grown the 5 nanometer sample with the same conditions, and we have varied the angle of the magnetic field from 90 to 0, and we could see the similar features of the magnetoresistance plot. However, the amplitude has decreases from 33 to 10%, 15%. And in plane conditions where the applied field and the magnetic field, applied electric and magnetic fields are parallel, then we do not observe clear negative magnetoresistance because this chiral anomaly getting weaker in the lower thickness of the sample, as this chiral anomaly is a 3D bulk features. Now, to further have also carried out the density functional theory with Professor Tanushree Dasgupta and Indra Dasgupta from Kolkata. They have performed this density functional theory calculations on this system, and we observed just 20 millielectron volt above the Fermi energy that there are band crossing near the M point. And from here we could also see the Fermi arc surface states, which confirms the presence of wild nodes in this MN3PT. In this band structure calculation has been carried out, including the spin orbit coupling and all-in all-out configuration of the manganese, as we have shown earlier. So, in conclusion, we have grown the MN3PT thin films on STO substrates, and we could see up to 5 degree of deviation between electric and magnetic field, the negative magnetoresistance, and then it becomes positive, which is a feature of chiral anomaly. And the density functional theory calculations also showed you that wild features of wild cone presence in this system. In some other experiments of here, I have shown you this is a MN3PT grown on silicon dioxide substrate, which is a polycrystalline, and we can see from 300 to 5 Kelvin, we could see positive MR and positive anomalous Hall conductivity, which changes sign at lower temperature, which is because this all-in all-out spin configuration of manganese getting canted when the temperature is lowered below 50 Kelvin. And this is a plot of differential spectroscopy of 5 nanometer sample, which showed that strong states due to this flat band, which is robust up to 7 Tesla of magnetic field, which has been predicted theoretically in the Cabo materials. Thank you for your attention.
Thank you, Jay, for the talk. Are there questions now? I don't see any question on the chat window.
No question, but I had actually, it's very interesting talk. I was wondering, do you also measure the planar Hall effect to find this chiral anomaly?
Yeah, we have measured the planar Hall effect. However, we are analyzing those data. Actually, this planar Hall effect in this system, what we feel is that there are different contribution of this anomalous Hall effect also, and from the misalignment of the device also. So we are trying to analyze the data so to extract the signal of the planar Hall effect.
Okay.
So,
Suvankar has one question, I think.
Yeah, very
Subhankar?
nice presentation, Joy. Just a quick
Thank you.
question. This
Yeah.
MN3P, how do you make, because you are doing the co-sputtering, how do
Yes.
you make sure that the stoichiometry is MN3PT?
Yeah, so we are doing with manganese and platinum to different targets, and we try to fix with first the rate, and then we cross check with EDAX. Then we optimize the rate that at which percentage of the manganese. So manganese is kind of we have to put more than little bit of something 3.1 or 3.2 of the rate of this platinum.
EDAX you have done with TM or SEM?
SEM.
Yeah, but TM EDAX sometimes it's not very clear.
Yes,
But
yes.
you must have done the
But
XRD. Do
Suvankar,
you see?
XRD is there. XRD confirms the phase, right? So
Yeah,
Yes,
that's
XRD
what I'm
is
asking.
much more.
XRD also confirms, isn't it?
Yes, yes.
Yes, yes, and also these systems, this manganese tin and manganese germanium, they also show these chiral anomaly features up to also 5% deviation, and in EDAX we can also detect within the limit of 5%.
Okay,
So if
fine.
there is,
I understand.
yeah.
No, you must have done quite thorough cross-checking. And you said that you find this topological nature. Okay,
Yeah,
these materials are having this topological nature. So,
yeah.
do you think topological Hall effect can be seen here, or have you done it?
Yeah, we have tried, but we could not see topological Hall effect because the fact in the topological Hall effect, we should have the Berry curvature in the normal space, means not in the momentum space. So in our case, it could be that manganese ions are such that this Berry curvature of this case is getting zero. Like in other reports, when you see with manganese tin, there are a lot of tilting of these manganese moments, and the real space Berry curvature is there finite. So they have observed the topological Hall effect, but here we could not see. Means we have studied that experiment, but we have not observed.
Yeah. Thank you. Thank you.
Jay, I have a quick question. So you have
Yeah.
discussed about the quantum nature as well as the classical nature, saying if you apply the field beyond 4 Tesla, so you see that your empirical formula doesn't match with your
Yeah,
experimental
yeah,
value, right? So why
yeah.
is it happens exactly at 4 Tesla or something like that? Because is it to your system or?
No, it is not that exact. We can see that at 4 Tesla or 6 Tesla, but after that regime, it is not working, and it has been observed in other system also that this formula is not valid throughout that high field regime. But,
I see.
but that field is depending on the sample, definitely.
Okay.
So the quantum regime, essentially, you're saying it saturates, right? At high field.
After 8 Tesla, it's going to saturate. But
Yeah, the quantum regime, quantum theory says that at high field, it will eventually saturate, right?
Yeah,
Okay.
yeah.
Okay, are there other questions? No? If not, then thank you, Joy, for nice talk. And I would like
Thank
to
you.
thank all of the speakers today for this session. Professor Subhankar, Professor Karthik, Professor Martin, as well as Joy, for nice
Thank
talk.
you.
And okay, I hope we had good interaction. And although we took little bit the time off from the schedule, but we had good questions, to be answered by the speakers, and it's a good interaction session among the participants as well as the faculty members. So yeah, thank you all, and thank you Pranav for giving me the opportunity to share over this session, and it's over to you now.
Thank you very much, Professor Jyoti Mohanty, for chairing this session. And yeah, thanks all. We'll have a lunch break now. and
Yeah.
we'll meet at 2 p.m. For another session, the last session of this conference.
Yeah. Okay.
Where Jyoti Mahanti himself is also going to talk.
Yes,
So
yes,
see you
yeah.
for the next session then.
Okay. Okay. Yeah. Yeah. Thank you all. Bye.
Great. Thank you.
Thank
I
you.
can see Professor Anil Kumar also.
Yeah, Anil is there.
I'm here. I'm here.
Do you want to taste your thing or?
Just driving
Hi.
for 8 hours. Let me just see. Pop on chair. You see?
Yeah.
Yeah, yeah.
Yes.
Yeah, yeah. It's fine.
Fine. Good.
Yeah.
Good, good.
That's good. So we'll have some lunch and return.
Pranav, hold on for a minute. I also wanted to share and want to check whether it's working or not. Fine, right?
Yeah, you can.
Yeah. So if you unshare, then Anil, I can start.
Yeah. Yeah. I think you can just share it because I'm not
Okay.
seeing
Okay.
a
Right.
it says unshare. So you just share, then it should come.
It's there, right, Pranav?
Yeah.
Yes. Yes. Yeah. I
Okay.
don't know
Okay.
why some people are getting this. No, it's fine now. There was some kind of square boxes coming,
Box.
but.
But I think there is a notification. If you close it at the speaker end, then that closes actually.
Aha. Okay. Okay.
Yeah.
Because that box was appearing in Martin's talk all the time.
Martin stock, yeah. But it was started. I thought, I won't disturb in between. So actually, it's a notification comes that don't do it again, kind of. So you have to cross it. Then it works.
Aha. Okay.
Okay. Okay. Let me. Okay. Stop sharing and then. Yeah.
Okay.
Okay.
Good.
See you after. See you
Okay.
after the break. Okay. See
See you. Bye.
See you.
you. Bye. Bye.
So I hope our chair will join.
Yeah, can you hear me?
Yes, yes.
Yes, 1 second. 1 second.
So hello everyone and welcome to this session. This is the second session and the final session of this ICEE conference. This session will be chaired by Professor Devanjan Bhaumik, who is the Assistant Professor at the Electrical Engineering Department of IIT Delhi. So over to you, Devanjan.
Yes. Will you be flashing the details of the speaker on the screen? That makes it easier.
Professor
Or should
Anil
I
Kumar,
read
just
it
a
out?
moment. Let us.
I can read it out from here also. Okay, so let me just read it from here only. So it's my pleasure to invite our first invited speaker, Professor P.S. Anil Kumar. Professor Anil Kumar obtained his PhD degree in physics from University of Pune. He was a postdoc fellow at University of Twente in Netherlands and Max Planck Institute of Microstructural Physics, Germany. He joined the Department of Physics of IISc in 2004. He is currently a professor of physics and the dean of the prestigious undergraduate program at IISc. His research interests are in magnetic nanostructures, magnetic transport in metallic multilayers and oxides, spin polarized electron scattering. He has authored more than 190 research publications. He is the recipient of the DAE Young Scientist Award, Max Planck India Fellowship, DAE Young Achiever Award, Material Research Society Medal, Master of Research India Outstanding Faculty Award, DAE Raman Lecture Award, Professor T.Y. Thatachari, prestigious Research Award for Science, Material Research Society of India Silver Jubilee Medal, Young Career Award in Nanotechnology, GST Government of India, Professor C.N. Rao, Bangalore, Indian Nanoscience Award. Yeah. So now I would like to give the floor to Professor Anil Kumar and let him start his discuss his show his research and present his work. Yeah.
Yeah, now I can see her.
I see this not right.
Yeah.
seeing my screen?
It's coming.
It's coming.
He's saying he's sharing to share. He's starting to share content. So,
okay.
Probably just
Good. You can see that now, right?
Yes. Yes.
First of all, let me thank Professor Pranaba for inviting me for this prestigious Icee conference. And today I'll be talking about some of our work on systems with a perpendicular magnetic anisotropy. Some of the important aspects are magnetic proximity effect in this kind of systems, and current-induced magnetization reversal, and Jaworzynski-Moria interaction in this kind of system. So this is what I'm going to present today. And there's, of course, a large list of people who are contributed for this work. So these are the students from my group who presently or in the past contributed to this. And these are my collaborators, especially Timo and Sonia was helping me with this for estimation of this proximity effect at DESI. And Ardi Kashyap was helping us with some of the theoretical calculations. And of course, we have to acknowledge different funding agencies which fund our research work. So I don't have to go into the details of why the manipulation of magnetization is important in magnetic systems. A variety of reasons. So since this conference, this session is dedicated for spintronics, I'm not going to spend time on this aspect. So what all we know so far is can be the magnetic moment of a material can be switched from one direction to another direction by applying a magnetic field. That is one aspect. And more recently, or for last 1 or 2 decades, and people are also working on switching by electrical current. So these are the famous work, that was showing that, the magnetization can be reversed by passing electrical current to a system. So this is called spin transfer torque devices. But in the last 1 decade, you can see that people have started using alternate source of spin current. So if you look at the spin transfer torque, you need around 10 to the power 12 ampere per meter square is the current density that is required to switch the magnetization. So people were thinking about alternate ways of doing the magnetization reversal. And one of them is the spin Hall effect mediated magnetization reversal. So here, what happens is that if you have an unpolarized current passing through a heavy metal system, and due to spin orbit interaction, the spins get separated. See, for example, okay, let me just take a pointer. Okay, the pointer is not coming for me. No, this is not good. Okay, let me just use the arrows itself. So here what happens is that if a beam of unpolarized current is passed through a material with high spin orbit interaction, you see that the upspin getting accumulated on this side and the downspin is getting accumulated in this side. If you look at really a 3-dimensional structure, you see that the downspin electron onto this side and upspin electron onto that side, and the subspin electron onto this side and downspin electron onto this side. So if you take a 2-dimensional slab, you can see that an accumulation of a particular kind of spin onto one surface. So people have used this phenomena so that this spin accumulation on one of the surface is used to induce an angular momentum to the spins of an adjacent ferromagnetic layer, and one is able to switch the magnetisation of the thin ferromagnetic layer. So here what happens is that you take a heavy metal and you have a thin ferromagnetic layer with the perpendicular magnetic anisotropy. As you know that if you reduce the thickness beyond a certain point, you will get a perpendicular magnetization. And in this kind of a structure, if you pass electrical current with a much smaller electrical current, though the current density is still very high, but smaller than the spin transfer torque, you are able to switch the magnetization of this kind of materials. So the essential ingredient for this kind of system is a spin orbit torque. So perpendicular magnetic anisotropy is one of the important aspects. And then you should have a proximity of heavy metal like platinum.
So one of the devices that people are extensively looked at is a platinum cobalt platinum tri-layer structure, which has got a strong perpendicular magnetic anisotropy. If you look at the optimization of perpendicular magnetic anisotropy, you see here I have put platinum cobalt platinum. So you can start depositing platinum on a silicon dioxide substrate. Actually, it is a silicon dioxide substrate, and you have platinum, then the cobalt, then the next layer of platinum. Now, in order to optimize the properties, you also have an underlayer of tantalum, which you will see as time progresses that this underlayer of tantalum is also very important and crucial in determining many of the magnetic properties of the system. And also, in order to understand the role of this heavy metal cobalt interface, we also start introducing light material like copper in the system. So this is called copper dusting, we call it as. And we will also soon tell you that what is the importance of this platinum cobalt interface in determining the perpendicular magnetic anisotropy in the system. Films have been deposited in a vacuum system which is capable of ultra high vacuum, like 10⁻⁻10 millibar vacuum, and there are 6 different elements can be deposited inside the system, and ultra high pure argon gas is used to make sure that the surfaces are clean in this kind of a sputtering system. All are done with DC sputtering. And the base vacuum of the system can go up to 10⁻⁻10 millibar, but we will not worry about such a ultra high vacuum because we are going to fill with argon gas at some point. So just to give you an overview of this, you see that we always use polar magneto-optical Kerr effect, and down the line I will also tell you that we are using Kerr microscopy to understand the magnetization reversal in this kind of systems. Yeah, if you look at this particular system, you see that platinum 3 nanometer, cobalt X nanometer, and platinum 2 nanometer. As you vary the thickness of the platinum, you see that you get a nice square hysteresis loop. And beyond a certain thickness of the cobalt, you see that the system goes in plane. This is what is expected. So the temperature, you see that as the underlayer thickness of platinum is also very crucial in determining the right magnetic properties. Here you see that as the thickness of the platinum layer increases, the transition temperature, it's an ultra thin cobalt film. So what you have put is only 0.35 nanometers of cobalt. And you see that as you increase the bottom layer thickness of the platinum, the TC is also increasing to higher and higher values. So please keep that in mind. So what is happening there is that as you increase the thickness of the bottom platinum layer, the platinum is having more and more 1-1-1 texture, and that is improving the magnetic properties of cobalt, and which you will see after some time it is indeed the case. So now if you another thing that we try to do to improve the properties of these materials or the perpendicular magnetic anisotropy is to introduce a tantalum underlayer in this kind of systems. So if you see here, for the same thickness of the cobalt, you see the introduction of a tantalum underlayer has shifted the TC to a higher value. So again, you can see here, if you do a very, very close analysis with grazing incidence X-ray diffraction, you see that as you introduce a tantalum underlayer, the 1-1-1 texture of the platinum improves. So what we see here is that as the 1-1-1 texture of the platinum gets improved, the magnetic property of the cobalt is improved. That means for the same thickness of the cobalt, you get a higher TC. So this is an important aspect that please keep in mind, because after some time, I'll be discussing this aspect a little bit more in detail. So yeah, this is just to substantiate the point that the tantalum introduces the 1-1-1 texture of platinum. Also, the increased thickness of the platinum also improves the 1-1-1 texture. So what we do, we try to introduce a layer of copper between cobalt and platinum. So you can see here, so we take a tantalum 3 nanometer, platinum 3 nanometer. We start varying the thickness of this copper layer, and we keep the cobalt layer thickness as constant, which is say 0.52 here, and platinum 2 nanometer. So here you see that when you don't have any copper layer, we get very nice square hysteresis loop from the Kerr rotation. And as you increase the thickness of the copper layer, you see that the squareness is going away, and you get almost like a hard axis loop, or you will think that the magnetization has gone in plane. So if I just show this data without any further analysis, I can argue here that the magnetization of the cobalt has gone in the plane. But if you do a little bit more analysis, you will see that the magnetization of cobalt is not gone into the plane. It is still perpendicularly magnetized. So how do we do? How do we understand that? We use Kerr microscopy. So if you look at the domain image here, this is tantalum 3, platinum 3, cobalt 0.52, platinum 2. You see a nice domain wall. So this is down magnetized state, and this is the up magnetized state, or this is pointing towards you, or this is pointing away from you. And this is for this square hysteresis, the film with this square hysteresis loop. Now, if you start as you start introducing a copper layer, you see that the magnetization deteriorates. Not only that, it gets almost into a hard axis kind of a hysteresis loop. But if I look at very carefully, you see that as you introduce the copper layer like 0.2 nanometer, 0.3 nanometer, 0.35 nanometer, and 0.4 nanometer. So here what happens is that it is splitting it into up and down domains. So when you remove the magnetic field, the equal number of up domains and equal number of down domains are there. Because of that, you appears to see a hard axis hysteresis loop. So actually it is not hard axis. So this is splitting this magnetic domain into up and domain states here. So this tells that the proximity of the platinum is very crucial to retain the perpendicular magnetic anisotropy with a single domain state with 100% remanence in the cobalt system. Now, what is the copper capping layer? So if you start putting the copper, a capping layer of copper, you see that even after I put 4 nanometers of copper between the top platinum layer and the cobalt layer, the perpendicular magnetization is retained. And if you look at the Kerr microscopy, you see two well-defined magnetization states you can see here. So this tells you that the bottom platinum is very crucial in deciding the perpendicular anisotropy of the cobalt layer. So now the inferences from this part of the study is that, what we have seen is that if you increase the thickness of the cobalt layer beyond 0.9 nanometer, so it goes from perpendicular anisotropy, with a perpendicular magnetization to the in-plane magnetization. And as you increase the tantalum, as you introduce the tantalum layer or increase the layer thickness of the platinum, the 111 texture is improving. And also I told you that the bottom copper layer is very crucial. The bottom platinum layer is very crucial in determining the perpendicular magnetic anisotropy, and this is inferred by introducing a copper buffer layer, copper seed layer in between, and you see that the magnetization is getting into a multi-domain state and apparently looking like an hard axis magnetization. So now we look at the field reversal. If you so this is a system with 4 nanometer, 0.44 nanometer, platinum 1 nanometer. Here we deliberately made the thickness of the platinum more asymmetric, and you brought the thickness of the top platinum layer just 1 nanometer. So there is a reason to do that, which I will tell you very soon. So now what we are trying to do current-induced magnetization reversal. So we will structure this tri-layer film into a stripe kind of a system, so that you can have high current density through this stripe. So here we have kept the top platinum thickness is only 1 nanometer, because the spin diffusion length of platinum is approximately 1.2 nanometer. So that if I pass current through this structure, the spin accumulation from the bottom platinum is more dominant so that the top platinum will not give a spin accumulation at the interface because you are below the critical thickness. So suppose if I keep the both top and bottom platinum layer thickness equal and high, what happens? One type of spin gets accumulated at the one side of cobalt and the opposite spin gets accumulated on the other side. Because of that, there will not be any effect here. So it is like, counteracting with each other. So in order to avoid that, you change the thicknesses accordingly. So now what we do, we do Kerr microscopy here. So we have in-house created magnetic field system where we have the possibility to apply a magnetic field in plane as well as applying a magnetic field perpendicular to the plane. Not only that, we can apply pulsed magnetic field as well. So you keep your device here and then you start imaging it. Not only that, you have electrical contacts that is connected to the sample so that you can pass current through the system. So this, I'm just skipping this. So if the system has got pure perpendicular anisotropy, you need an in-plane magnetic field to switch the magnetization with the electrical current. So what we do is that we tilt the easy axis of magnetization by a small angle by a particular way of depositing the films, which I will tell you a little later how you estimate the tilt angle, etc. So you have a slightly tilted magnetization. So that, tilted means of the order of 1.5 degree, 2 degree kind of a tilting. And with that tilting, without an in-plane magnetic field, you are in a position to apply electrical current and switch the magnetization. So now if you look here, by here, what we are doing, we are weighing the film plane, and this black area is the patterned film. So it used to be a continuous film, and then lithographically it is patterned to give this kind of a structure. And you apply the magnetic field, and you watch at any pixel here, and you can get this square hysteresis look from this kind of pixel. So now what I do, I pass electrical current through the system. You see here, I'm passing current through the system. Now my x-axis has gone to the current instead of the applied magnetic field. And you see this is the magnetization. Again, you see that the magnetization is getting reversed at a current of 3 × 10⁷ ampere per centimeter square. So here you see, in this particular case, you see the magnetization is reversing everywhere because you have uniform magnetic field applied everywhere. Whereas in this case, the current density of this electrical current is maximum in this small area region. That is why the magnetization reversal is happening here. And here the width is more so that the current density is low. That's why the switching is not happening here. So this also demonstrates that we are able to do the current-induced magnetization reversal with low current. So now coming back to some of the puzzling things that we have seen here. Earlier I have shown you when I looked at the magnetization versus temperature, the magnetic moment of cobalt is approximately 2,500 EMU per cc. So that is because the bulk cobalt, if you look at, you will see 1,400 EMU per cc as a magnetization. So now because of the magnetic proximity effect, that means the platinum is getting a magnetic moment due to the proximity of cobalt. So we wanted to estimate the induced magnetic moment in the platinum layer here. So for which what we employed is that X-ray resonant magnetic reflectivity, and also we used X-ray magnetic circular dichroism analysis. So here what we do, we come with an X-ray beam. This was done at Petra 3 P09 beam line. So here you come in with a circularly polarized X-ray beam, and then you look at the reflectivity from the surface. So here you vary the energy of this X-ray beam to be in resonant condition. So first we do magnetic dichroism to find out what is the resonance energy that is needed here. And then first you do off resonant and then resonant reflectivity. This is like the X-ray reflectivity which you are doing generally in our labs. So here, in addition to this X-ray reflectivity study which we do in the lab, we are also in a position to change the helicity of the X-ray beam that is coming in, and also you can apply the magnetic field in two different directions. So this is how this experiment is done, and from there we are in a position to extract the magnetic moment from this kind of system. So what we do first, we vary energy and find out what is the resonance condition. So this XMCD is done to understand the resonant energy. So we find that the platinum absorption edge is 11,567 eV. So then what we do, so this reflectivity is done. This is exactly same as the X-ray reflectivity that we are doing in our lab regularly. So here, in addition, that you apply a fixed magnetic field and you switch the helicity of the X-ray beam, and from there you calculate something called an asymmetry. The asymmetry is this, when the intensity when the left circularly polarized light is coming minus the right circularly polarized light divided by the sum of that. Or what you can do, you can fix the helicity and switch the magnetic field. So from all these 4 data points, we get an asymmetry that is used to estimate the magnetic moment of these layers. So what we do, first we do an off-resonant X-ray analysis, and there are, see in this previous graph, okay, this equation I have not put it here. You need to extract different parameters. See this delta I depends on several parameters that which we'll not discuss here. So by doing first the resonant analysis, you fix some of the parameters. Then you go to an off-resonant analysis and find out some more parameters. And then what we do, you again do the structural parameters to the asymmetry data. From there, you calculate the magnetic data. So here, the absorption coefficient, which is the magnetic depth profile, is analyzed from this kind of experiments. So what you can do from this asymmetry, you can calculate this delta B value. So the delta B value will give you the depth profiling as well as the magnetic moment. So we know that, this delta B corresponds to, this much delta B corresponds to 1 Bohr magneton plus platinum atom. And from here, we can estimate what is the magnetic moment that is coming to the interface platinum atoms. So very interestingly, if you look at here, so this is air, and this is the platinum layer. You see that the platinum in contact with the cobalt gets a magnetic moment. Similarly, the platinum in contact with the bottom platinum in contact with the cobalt layer also gives this magnetic moment. And then this is a tantalum atom. So what we are doing here is that we are finding out the depth-dependent magnetic moment of the platinum layers. So here what we did, so this is the idea, is to find out what is the magnetic moment. So here we took without tantalum, platinum 4 nanometers, cobalt 2 nanometers. Please remember, this is in plane magnetized, platinum 2 nanometers. Then keeping almost everything constant, we start varying the tantalum thickness. And when you vary the tantalum thickness, what you see here is that when there was no tantalum, the both top and the bottom platinum layers were having almost identical magnetic moment. And as you increase the bottom tantalum layer, you see that the magnetic moment of the bottom layer is decreasing. And as you go to extremely high thickness of tantalum, you see that the platinum magnetic moment is much low compared to the top layer. So this is something very interesting. So that means the magnetic moment, the induced magnetic is decreasing as you increase the tantalum layer thickness. And what you could do, you could calculate the magnetic moment of the top platinum layer and the bottom platinum layer. And we can also do these measurements by vibrating sample magnetometry, where we, of course, will get the total magnetic moment due to the proximity-induced magnetization of platinum plus the intrinsic magnetic moment of the cobalt. And you see that what you estimate from the VSM is matching fairly well with what you are estimating from this XRMR. So this tells you that this XRMR data is giving you a very interesting result, that as you increase the tantalum layer thickness of the bottom, then the bottom magnetization of the platinum is also diminishing. You see here, the top layer remains almost constant, whereas the bottom layer, the magnetization of the platinum layer drops as you increase the thickness of the tantalum buffer layer. So we wanted to analyze that, and we find that as you increase the bottom layer of the tantalum, so we have just grown 4 nanometers of platinum on a very thick tantalum layer, and we find that what's happening there is that the platinum 002 texture is going up as you increase the tantalum layer thickness. So then what happens? So we took the help of Professor Arati from IIT Manti. She and her students estimated. So what is the moment induced in platinum, which is in proximity with cobalt when it is platinum 111 as against platinum 011? It's very interesting that her calculation clearly shows that, if you have this platinum 111, it has got more induced magnetic moment compared to platinum 011. And this tells us that, this is how this kind of results are experiment and the theory is going hand in hand. Now we start introducing copper layer. Remember some time back I showed you that as you increase the copper layer thickness, the perpendicular magnetization is retained. And also we wanted to know that to what extent. So we now put a tantalum, platinum, cobalt, copper, and platinum. So we introduce copper layer between the top platinum layer and the cobalt layer. And you see that as I start increasing the copper layer thickness, the platinum moment, which is here, which is diminished to this, and it is almost vanishing when you have 2.5 nanometers of copper. So this also tells me that as I increase the thickness of the buffer layer of copper between cobalt and the platinum, the induced magnetic moment of the platinum is also going down. So these are all interesting experiments which gives you a lot of insight into what is happening and also to what level this proximity of magnet, cobalt and platinum is retained in this kind of system. So in the last 10 minutes, I will tell you in this kind of systems, we can also estimate this Jaushinski-Moria interaction in this kind of perpendicularly magnetized system using Kerr microscopy. So I'm not going into the details of DM interaction because yesterday Professor Matthias Clauvi also was discussing about this kind of picture, etc. So what I'm going to tell you is that how we use this Kerr microscope to estimate the DM interaction in this kind of systems. So please look into this graph. Suppose if I have a system which is perpendicularly magnetized, and if you apply a magnetic field in the opposite direction, as you keep increasing this magnetic field, at some point the magnetization reverses. Even before this reversal field, every system has got, for example, impurities in it. Associated with that, there will be some pinning centers. So if a magnetic domain gets nucleated, you need a field higher than a critical field to come out of that, it's a depinning field, so that the domain walls can start moving. But in this kind of systems, even before attaining that field, since we are doing all these measurements at room temperature, so the domain wall starts creeping in this kind of systems, and this creeping is given by this equation. So here, this is the domain wall velocity, and then this domain wall velocity is an exponential of this psi. This psi is nothing but sigma hx to the power 1/4, where sigma is the one which gives you the domain wall energy density. If you look at the domain wall energy density, so what you can do, you have an applied magnetic field which is perpendicularly magnetized in a perpendicularly magnetized system. You apply a negative field which is smaller than the Gaussian field of this material, and you give a pulsed magnetic field there. So then you can also apply an in-plane magnetic field. So if you apply an in-plane magnetic field Hx, and if the domain, if the DMI field, the magnetic field associated to the DM interaction is HDMI, and in this kind of systems, this domain wall energy is given by these equations, where these conditions will tell whether you have a block wall or a Neal wall. So suppose if you look at this domain wall energy density, now look at this equation, or look at this equation, because this is what we are going to discuss in detail. When this Hx is equal to HDMI, and if they are in the opposite signs, so this can cancel out. And when this cancels out, that means an in-plane magnetic field, and then I look at the domain wall energy density, this domain wall energy density will become a maximum when my in-plane applied field is equal to the HDMI. So that means this term gets cancelled out, and then this becomes the maximum value here. So now, in case if the system has got HDMI, suppose in case this system didn't have any HDMI, what happens? Even with Hx equal to 0, the system goes to a maximum. Increase this Hx value, so this term decreases. That's why you get a decrease in this energy density. Now, suppose if HDMI is present in the system, what happens is that this graph will get shifted to one of these directions, which is equal to the HDMI. When Hx is equal to HDMI, then this profile will give a maximum. So that maximum will tell me that what is the HDMI field. Now, if you plug this back into this equation, so this will tell me that I can look at the velocity of this domain wall, and I can look for the minimum. See, now here this is the maximum. When Hx is equal to HDMI, your domain wall velocity becomes minimum. So if HDMI was not there, the domain wall velocity would have been having this profile. But now if you have HDMI, the domain wall velocity will become with this profile, where the minima will give me is a field that is due to HDMI. So let us see how that happens here. So this is another system. This is not cobalt. This is cobalt iron boron system. So we do this experiment on different systems. As time progresses, you will see. See, this is a system with the tantalum 3 nanometers, platinum 3.1 nanometer, cobalt 0.6 nanometer, platinum 1.1 nanometer. So what we do here, please have a look at here. You take the system and you nucleate a domain, and then you apply pulsed field. Apply an out-of-plane pulsed field of 57 oersted, and the pulse width is, say, 100 milliseconds. So imagine that I have a domain like this, and if I apply this pulse field of 57 oersted for 100 milliseconds, this gets into, it just expands. And if I apply one more pulse, it expands. So if the pulse width is large, it suddenly jumps to larger and larger in value. If my pulse width is small, I can slowly expand this domain. So now you look at here, and probably this graph may not be that visible for you. What we do image processing and find out the outer envelope of this. So this outer envelope is done by image processing. And what you can do is that I can see the distance traveled by this domain to the next size, and I know the time taken for the applied pulse. So the distance traveled by the applied pulse width will give me the velocity. So now here you see that the velocity is increasing. The velocity is same in all the directions, because it's a circular domain which is like that. So here I apply an in-plane applying any in-plane magnetic field. As you know that the HDMI field is radially outward. Now look at this situation where I apply an in-plane magnetic field of 500 oersted in the Hx direction. So here what happens, if you look at this domain, you see that it is becoming almost like elliptical. So not only elliptical, and also you see here what happens, I apply a magnetic field Hx here. I do have an HDMI here. So my effective field in this direction is the sum of these two. Whereas on the other side, the right-hand side of this, the right velocity of this domain is due to this H effective, whereas the left velocity of this domain is the resultant field, which is HDMI minus Hx here. So I now have a velocity profile where to the right it is moving faster. So that means as this becomes bigger and bigger, it also moves in one direction. Similarly, If I apply a minus 500 oersted magnetic field, what happens? Just opposite. Now I am applying opposite direction, whereas my HDMI and HX is more in this direction. You see that the domain wall in this direction is moving faster. So in the plus 500 case, it was moving in one direction with the right velocity higher than the left velocity. In the other case, you see it is moving in the opposite direction with the left velocity higher than the right velocity. So this gives you a lot of information. So now what we do, see in this, we have only 57 oersted of applied magnetic field. Now what we do, we start applying the magnetic out of plane magnetic field from 50 oersted to 60 oersted, and also you apply the in plane magnetic field in a wider window, and then several data. Please believe me that one such complete analysis takes 5 to 6 days continuously in the machine, because a lot of data need to be collected here. So from this velocity, from this contour, you see that this is the velocity plot. You see that the velocity goes through this maximum, and also you see that this entire thing shifted with respect to the 0 to the left side. So this value gives you the DMI field here. Fine. So I'm not getting into those details. Now, if you do an analysis of the velocity along that direction, you see that this is centered around 0. So here what happens, the resultant magnetic field is same in either direction. So because of that, what happens, it remains symmetric here. So here, since the HDMI, here also you can tell whether the HDMI is positive or negative. Let us don't get into that analysis. But one more thing, what we can calculate from here, we know the anisotropic constant, because from vibrating sample magnetometry, you find out the saturation magnetization of this material as well as anisotropic constant. And there is one assumption which we make, which is delta, which is the domain wall width, which is not measured. We just calculated based on the available value of the stiffness and the anisotropic constant. So if you plug in all these values into the equations of this equation, we estimate the D value of approximately 0.08 millijoule per meter square. So many such analysis is going on right now. This is an ongoing work. You see now that you are in a position to calculate the field due to the DMI, and if we can get the domain wall width also from a measurement, we can exactly estimate the DM interaction in this kind of system. So in the last 1 minute, let me also tell you that we can do again interesting experiments with this Kerr microscope. We can also find out what is the tilt in magnetization. I said that it is not a fully perpendicularly magnetic system. It is a quasi-perpendicular. That means there's a small tilt in the system. That small tilt is introduced by a very, very finite thickness gradient in the ferromagnetic layer. So suppose if this tilt is by value, we can estimate this tilt as well by this Kerr effect, magneto-optical Kerr effect. So the resultant field in this H tilt is given by this equation, and the tilt can be, see whether you magnetize, reverse the system from up magnetized state to down magnetized state, or down magnetized state to up magnetized state. These equations hold good. So this is the up to down state, and this is down to up state. So then what does it tell? This tells you that if I apply an in-plane magnetic field in a system, then this loop, if you look at it, will get shifted in one direction, right? And if you measure that tilt, suppose if I apply plus Hx, it will tilt in one direction. If I apply minus Hx, it will tilt in another direction. So you look at the shift in this hysteresis shift, and from there you can calculate this shift is equal to the applied magnetic field times the tan of the tilt angle, and also this Hx I can vary in plane. So this is the phi azimuthal angle. So if I vary the azimuthal angle and if I vary this Hx, And from this delta, the shift in the hysteresis loop, I'm in a position to calculate this tilt. So what I do, I plot this, the slope of this curve, slope of this particular curve will give you the tan of the tilt times this azimuthal angle. So what we do, this is a simple experiment, second last slide. You get this hysteresis loop. Now you apply an in-plane magnetic field, it gets shifted in one direction. If you apply the magnetic field in minus x direction, you get a shift here. Now what you do, you plot the shift in hysteresis loop. Then what you see as a function of applied magnetic field, you get a straight line here. So you take the slope of this straight line. Now this is for a particular phi value. Now you do all 360-degree phi, and then you plot the slope of this curve for each and every phi angle, and then you get this shape. And this shape is filtered, fitted to this line, and from there we estimate the tilt angle is 1.24 degree. So what I'm telling is that this cobalt iron boron in this particular case is perpendicularly magnetized, but just tilted by 1.2 degree in one direction. So, and also we do this tilt estimation with different thicknesses. You see that as you increase the thickness of the platinum layer, the angle also varies. And also now we are estimating the DM interaction for different buffer layers, etc. So in conclusion, what did I tell you? That I showed you that we are in a position to do current-induced magnetization reversal. I also told you that there is a proxy which gives you magnetization for the platinum layer. And also, I told you that even the texture of the film decides the magnetic property. Now we are getting results that even the texture decides what should be the strength of the DM interaction in the system. And I also showed you, how to calculate the DM interaction. In this particular case, we get some value. And also, we are in a position to measure the tilt angle. So all these things can be done with a Kerr microscope. And currently, we are exploring the interplay between the tilt and the DMI strength, and also the role of texture of underlayers in determining the DMI. And also, we are looking for the right combination of the metallic multilayers in realizing optimum DMI. As all of you are aware, is that the competition between the DMI and the exchange decides the skyrmion. So what we are looking for is a recipe to tell that, okay, this is the recipe to get the skyrmion whenever you want to work in this kind of system. With this, let me just thank you for COVID, the physics department of Icee, for your attention.
So it's really interesting to see these results coming from India. It's probably the fastest study to measure DMI using Kerr microscope.
Yeah.
So there are a couple of questions in the chat window.
Yes.
Yeah, I can read it out maybe.
Okay.
In the chat window, right?
I can read also if you have.
I cannot be able to see it. What do you see the chat? Oh. I don't see it. Can you read it out then?
Yeah. So the first question is in the XR-MR analysis of platinum cobalt.
Okay.
Platinum, there is some asymmetry in the shape. Asymmetry that get induced in the platinum. There is an asymmetry in the interior of cobalt layer compared to the asymmetry that gets induced in the platinum layer.
Let me read it out again. In the XR-MR analysis of platinum-cobalt-platinum heterostructures, why is there low asymmetry in the interior of the cobalt layer compared to the asymmetry that gets induced in the platinum layer or at the cobalt-platinum interface?
Sorry, I didn't understand the question.
Yeah. Let's move to the next question then.
Yeah.
How to make sure that the asymmetry in the shape signifies the DMI? Asymmetry in the shape signifies a DMI. Okay. I'm not sure which slide he's pointing to.
I think this is the slide, the is, see, what happens is that if there was no DMI, see, the question what he is asking is that, this circular versus this elliptical domain. So what happens is that since there is a DM field present here, when you apply a magnetic field in the same direction, so then what happens is that the domain wall velocity is more in that direction. So whereas on the other side, your DM field as well as the applied magnetic field is opposite to each other, so that the resultant field is low, so the velocity is low. So that is why the system will expand. At the same time, it expands asymmetrically. So this asymmetric expansion tells you that there is a DM field in the system. And another proof comes if you look at the velocity in the perpendicular direction, it remains constant.
Okay. Okay.
So Jyoti has a question, I guess.
Yes, Anil, very
Yes.
nice talk. So, so related to this question, so if you switch off your pulse field, so if you switch off your pulse field, do you see the extension comes back to the original position?
It remains there. See, it remains there. You apply a pulse field, it expands, and it remains there until you put the next pulse.
Okay, and this is like, instead of like if you going, let's say in x-axis now, okay, you are providing, pulling it down in x-axis. If you apply the field along the y-axis, okay, now you will see similar kind of effect, right? That is expands only along the direction. Okay.
So we will not apply the field in the other direction. If you rotate the sample by 90 degrees, it is equivalent to that, and you see exactly the same effects.
Correct. Right. Thank you.
I will come back to you because I wanted to see what is the domain wall width.
Yeah, please, welcome. You're welcome.
Okay, shall we move to the next speaker then?
Yeah, I had actually one technical question.
Yeah.
This in the first part you show this polar care measurements with the cobalt layer thickness is going down to well below 1 nanometer, like 0.3 or so. So which care microscope did you use? The home build care?
No, this is
Evico.
And for the hysteresis loop, we use our home built one that gives you much more quantification. Evico
I'm talking about the hysteresis loop only. Because there you have quantified also the
home built.
This looks very sensitive.
Yeah.
But is it single loop or it is measured and average over several?
Not more than 10 averages. Not more than 10 averages.
Okay.
In the first round itself, you get nice loop just to make sure that some 10 times average.
Okay.
So next speaker.
I think we have to move. I had many questions, but I think we'll take it offline.
Thanks, Professor Anil Kumar, for the very nice talk. We next move to our next speaker. He's Professor S.N. Piramanayagam. He has obtained his PhD from IIT Bombay, India. And after his PhD, he's carried out his future research at Shinshu University, Japan, before joining as associate professor at NTU, Singapore. He worked as a senior scientist at Data Storage Institute, Singapore, 1999 to 2015. His current interest lies in the interdisciplinary areas of magnetism, electronics, and nanotechnology. His research aims to gain understanding and solve issues related to areas such as spintronics, magnetic recording, and energy. He has recently secured a multi-million-dollar grant for research on spin-based neuromorphic computing. He has more than 175 publications in Icee journals, filed several patents, and edited a book titled Developments in Data Storage, Materials Perspective. So now I request Professor Piramanayagam to give his talk.
Thank you, Professor Vamik, and thanks, Professor Mudali, for inviting me for this conference. Let me share my screen. Can you see my screen?
Yes.
Okay. So good evening, good afternoon, everyone. So the title of my presentation will be Spintronics-based neuromorphic computing. And these are my collaborators, Durgesh, Jampeng, and Tianli are my students, and my collaborators from IMRI and Sultan Qaboos University. They helped me in providing samples and some analysis of the results. And before I get into my talk, I also would like to thank my grant agencies, NRF, which is National Research Foundation of Singapore, and ASTAR provided this AME grant. And this is my team, which will work on this neuromorphic computing project, which assembles a team of researchers from physics, material science, and electronics and computer science background. Basically, this is the outline of my talk. I will briefly give an introduction about neuromorphic computing in general. Then I'll move on to describe specific aspects of spin-based neurons and synapses, particularly more on domain wall-based neurons and synapses. Then maybe I'll cover a little bit of domain wall pinning, but spend more time on the energy reduction for moving the domain wall, which is the main aspect of saving power in neuromorphic computing. Then finally, I'll end with a summary of my presentation. So as many of you know, that the artificial intelligence is currently implemented in many products. So many of the major companies like Microsoft, Samsung, Amazon, Google, Apple, everyone have artificial intelligence applications. But one of the main problems associated with these artificial intelligence applications is the power consumption. So this power consumption issue mainly come from the way we utilize the artificial intelligence, because we are using the von Neumann architecture, which is about 70 years old architecture. So in this scheme, what happens is that we have CPU, we have memory. Whenever we do computation, the computation happens in CPU, but the data is fetched from the memory unit. So every time we do a computation, the data goes back and forth between the memory and the CPU. And if you take a computer, the memory unit is like 4 centimeters away from the CPU. So if you compare this to the size of a transistor, this is like a person going 1,000 kilometers to fetch something and coming back. So this kind of transmission of data happens between the CPU and the memory unit. As a result, there's a huge power consumption. So the current artificial intelligence applications basically make use of this architecture, but they have the neural network algorithms. So because of this architecture, there is a more power consumption in the artificial intelligence applications. And this will be very clearly evident if you compare the power consumption of the supercomputer that beat a human in chess versus the brain. So in the case of Deep Blue, which beat Garry Kasparov in 1997, the power consumption of the supercomputer is in terms of megawatts, whereas the brain of Garry Kasparov uses only 20 watt of power. So this is the huge difference at that point of time. Even now, if you look at the power consumption of brain for intelligence applications is 3 orders lower than the computation power employed by the computers. So as a result, people are looking at neuromorphic computing, which is a brain-inspired computing to help overcome this power problems, the energy problems. So in this case of neuromorphic computing, we'll have new hardware elements which mimic the brain elements, and we'll also have new algorithms. As a result, we may have much better power saving and parallel computing for the intelligence application. So this is the main aspect of neuromorphic computing, and this is the significance why people are looking at neuromorphic computing. So it's good to have some background of how the neuromorphic computing works, because it's a brain-inspired computing. So if you look at the brain has neurons and synapses, and neurons are the processors of the information, and the synapses are the elements that memorize things. So we exactly don't know how the brain does the calculation, but we know that these are the elements that play a role in the information processing of the brain. So researchers are trying to make use of these kind of electronic analogs of neurons and synapses to form the neuromorphic computing. So if you take a synapse, for example, a synapse is the bridge between two neurons, and the synapse gradually gets stronger as you learn more. So in terms of an electronic analog, we may consider this as a resistance whose value decreases as we keep learning. So people can draw this kind of things, and they can come up with the brain-inspired computing. And that's what we are looking at. So now I move on to specific aspect of how we are planning to do spin-based neurons and synapses. So if you look at the spin-based neuron, there are many studies. For example, Uli Grolier's group, they have used spin torque oscillators as a neuron. Basically, these neurons respond to the signals from the other neurons, and they produce an output in a digital manner. So this is what we expect in a spin-based neuron. And yesterday, Johan Ackermann also presented a spin Paul nano oscillator as a kind of a neuron. But this talk, I'm going to focus more on synapse. So as I mentioned before, synapse is the device that basically stores the information in the brain. So in terms of electronic analog or spintronic analog, we are looking synapse as a memory device with a multi-level resistance state. So if you have you can have high resistance, low resistance to represent the low weight and high weight of the neural networks. So this is what we are planning to work on in terms of synapse. And basically, we are looking at multi-level resistance states of a spintronic device. So around 3 years ago, Fukami et al. From Tohoku University, they showed multi-level resistance states in cobalt nickel multilayers based device using anomalous Hall effect. And 2 years ago, we showed multi-level resistance in cobalt palladium multilayer based domain wall device using anisotropy magnetoresistance and so on. But in the near future, we are planning to show multi-level resistance states using tunnel magnetoresistance. So basically, our interest in domain wall devices go back a decade ago. In 2013, we published this paper where we have proposed to use a magnetic tunnel junction device in the form of a domain wall configuration to store multi-level states. So although at that point of time it was mentioned, it was supposed to be used in a multi-level magnetic memory, we believe that this can be used in as a synapse for the neuromorphic computing device. So in this multi-level device, the domain walls can be moved to different parts of the MTJ. And depending on the domain wall position, we can have different resistance. And we can use this configuration, these different configurations to function as synapse of a neuromorphic computing circuit. So for example, if you use a magnetic tunnel junction, if you have fully parallel structure, you will have the lowest resistance, say for example 1000 ohm. And if you have fully anti-parallel resistance, you will have the highest resistance states. And by moving the domain walls to different positions, you can achieve intermediate values of resistance. So thus, this kind of domain wall devices can be used as synapse. In fact, neuromorphic computing circuit entirely based on synapse and neuron. Neuromorphic computing circuit with synapse and neuron entirely based on domain wall devices have been already proposed. But this is a circuit design which does not reveal any experimental results. So people are looking at demonstrating these kind of circuits experimentally. So our objective also is to come up with domain wall based synapses and neurons, and carry out this kind of circuit in the near future. So this is what we are in the process of doing. So now I'll move on to briefly explain domain wall moving and spend more time on the energy reduction for domain wall motion. So if you take a domain wall, it's not very easy to move the domain wall positions precisely. I told you that in the case of Synapse application, we want to move the domain wall precisely as that will lead to multi-level resistance, but it's not easy to achieve. So this is one example of what we see in a cobalt palladium based domain wall device. So in this case, this is a Kerr microscopy image, and let's say white represents the magnetization facing up, gray will represent magnetization facing down. So in this case, we saturate the sample to a high positive magnetic field, and when we apply a negative field of about 1854 oersted, the magnetization is still facing up. When we reduce the magnetic field a little further, from minus 1854 to minus 1858, the domain wall reverses. The magnetization of the whole domain wall reverses. I mean, there's no domain wall. The whole element undergoes a magnetization reversal. So this implies that we need to have some form of domain wall pinning. Otherwise, we may not be able to move the domain walls precisely into different steps. Therefore, we cannot achieve Synapse application without domain wall pinning. So we have spent a lot of time to study the domain wall pinning in this kind of domain wall devices. So one approach that we have done in the past is a staggered domain wall device. So in this case, what we do is we take a segment of domain wall device, but we offset them with respect to the previous segment by a certain distance. So the distance is shown here. So in this case, let's say the wire is 500 nanometer width. We displace the wires by a distance of 50, 100, or 150 or 200 nanometer. So each of this shift gives rise to a nano constriction, and that nano constriction pins the domain wall. So in this case, we have applied a magnetic field and we have moved the domain walls precisely to each of the corners. Okay. So this indicates that we can use this method to pin the domain walls. This is one approach that we have done. And similarly, we have also done the same thing in multi-layers with the perpendicular magnetic anisotropy. The previous study was based on in-plane magnetization material, but in the case of perpendicular materials also this kind of staggered geometry works. So here you can clearly see that we have a staggered arrangement, and by applying spin transfer torque current, we can move the domain walls precisely and pin them at different corners. So this kind of pinning mechanism is very crucial for achieving Synapse, because this is what will lead to different domain wall positions and multi-level resistance state. So now let me move on to the energy saving aspect. So as I mentioned, in the first case, we move the domain wall by magnetic field, which is very energy inefficient process. Whereas for real devices, we prefer to move the domain wall by electric current, because electric current is the one available in the electronic circuit. So the transfer of a domain wall by spin transfer torque is one method. This is useful, but this consumes significant power. So if you talk about the energy consumed by spin transfer torque, this is in the case in the scale of the nanojoules per bit. Whereas people are looking at more power efficient methods like the spin Hall effect, which has also been spoken by Professor Anil Kumar in the previous lecture. So by using spin Hall effect, we can move the domain walls with much lower energy. So in the literature, people have said that using picojoules per bit, we can move the domain walls. So this is the kind of energy people have reported. So in this case, we send a current through a heavy metal layer, and we have spin accumulation in the ferromagnetic layer, and that helps to move the domain walls. So this is the mechanism of spin orbit torque. So mostly for spin Hall effect, people have used a high pressure tungsten layer, and this gives rise to this high pressure tungsten gives rise to a larger spin Hall angle. But there are some problems associated with having a high pressure tungsten layer. Because of the high pressure, it leads to a higher resistivity. As a result, you will spend more power. That's one thing. Secondly, when you have a high pressure tungsten, the grains are tend to be rougher, and you may have larger pinning field in the magnetic layer on top of the high pressure tungsten. So this is the problem that we foresee. As a result, we have come up with a novel structure, which we call dual tungsten layer. So in this case, we have high pressure tungsten as usual, but on top of the high pressure tungsten, we also deposit a low pressure tungsten layer. So this low pressure tungsten layer is expected to smooth the surface so that the next cobalt iron boron layer, which is deposited on the low pressure tungsten, will have a smoother interface. That's one thing that we expect. And this low pressure tungsten may also reduce the resistance, and it may also reduce the pinning field. These are the things that we expected. And with these expectations, we carried out experiments on this kind of design. And these are the hysteresis loop of the samples and the coercivity measured from the different samples. So for the next few minutes, when I say S, I am talking about a single layer of tungsten. When the samples have a symbol D, that's basically the dual tungsten. This is our special tungsten design, whereas the S1, S2 are the commonly reported tungsten layers with only one particular tungsten. So by tuning the thickness of this two tungsten layers, we can actually tune the coercivity of the layers, as you can see from these two figures. And we have also studied the domain wall motion in these low pressure tungsten sample, high pressure tungsten samples, and the dual tungsten sample with the 3 nanometer of high pressure tungsten and 3 nanometer of low pressure tungsten. So this is the typical domain wall motion that we see. The domain wall nucleates at certain point and it moves as a function of the applied magnetic field. And if you look at the motion of HP6, this is the sample that shows a larger spin Hall angle. So in this sample, you see that the motion of domain wall happened over a very large range of magnetic field, around 0.08 millitesla, whereas the range of magnetic field is very low for the LP6 sample. This low pressure tungsten sample usually doesn't show much spin Hall effect, so this is actually useless. So if you compare the HP3 and the LP3 versus HP6, we see that our dual tungsten sample shows a narrow range of field in which the domain wall motion occurs. So this indicates that probably the pinning field of HP3 LP3 sample is lower than the normal HP6 tungsten sample. And we have also measured the roughness. The roughness of the dual sample is much lower than the high pressure tungsten alone, so which also supports our hypothesis. And we have measured the resistivity. So the resistivity of the D2 sample, where we have 3 nanometer of high pressure tungsten and 3 nanometer of low pressure tungsten, it shows resistivity over 120 microohm centimeter, which is also an indication of beta tungsten, which indicates the possibility of a larger, reasonable spin Hall angle. In fact, we measured the spin Hall angle of a high pressure tungsten and the dual layer tungsten. They are more or less identical. So now to study the domain wall motion, we have used a curve microscopy system. So in this case, we have observed the domain walls using the curve microscopy, and we applied current pulses and a small external magnetic field to move the domain walls. And as noted, the high pressure tungsten sample doesn't move the domain wall very consistently. For a large range of current and magnetic field, the domain wall motion doesn't occur, and suddenly the domain wall progresses very fast, which is an indicator that this particular type of sample is not very useful for neuromorphic computing. Whereas in the case of the dual tungsten layer, we could move the domain walls very precisely. So if you look at these results, you can see that the domain wall is moving consistently. So this is actually a good point of this dual tungsten samples, where we can precisely move the domain walls in a controllable manner. And more importantly, this particular sample with a dual tungsten layer shows domain wall motion at current densities as low as 1 E6 ampere per square meter. This is typically 4 orders lower than the current density that people have normally observed. So in most of the samples with the tungsten or any other heavy metal layers, the current density required to move the domain wall is 10 to the power 10 ampere per square meter or more, whereas we see domain wall motion current density is at 1 E6 ampere per square meter. So this is a very significant achievement for low power neuromorphic computing circuits. And we have carried out some studies to understand why this is happening. So if you compare the spin Hall angle, there's no big difference. But if you measure the pinning field, you can find out that the dual tungsten sample, HP3, LP3, have much lower pinning field of 2 millitesla in comparison to the pinning field of 4.6 millitesla, which is the sample normally fabricated by many people. So this small deepening field is one of the main reasons why we have observed domain wall motion at very low current density. So I'll skip some of these slides as we have no time. We have actually carried out the domain wall motion, and we have shown that we can clearly move the domain walls to different positions by coming up with a meander structure. And these kind of devices can be used as synapses. So all these investigations are carried out in single layer domain wall device, but in the near future, we are planning to make MTJs based on this kind of material that we have studied. So let me move on to the summary, and thereafter be ready for the questions from you. So basically, in this talk, I showed you that the basic concepts of neuromorphic computing and how spintronics elements can be used in neuromorphic computing. I also showed you that we can achieve domain wall pinning, which is a crucial aspect of domain wall based neuromorphic computing by geometrical methods. And finally, I showed you that by using a dual tungsten layer as the spin Hall layer, we can achieve a very low current density driven domain walls. And when we estimate the energy required to move the domain wall by 20 nanometer, that turns out to be in the order of attojoule. So we have shown energy reduction to the scale of attojoule per bit. So with that, I end my presentation. Thank you very much.
Hello, yeah. I think I don't see any more questions on that sheet. Professor Mudali, do you see any more questions for this talk?
No, not yet. Maybe you can start by asking some questions.
Maybe I will ask a few questions and then we'll wait till there are some questions crop up here. So my question to Professor Prem is, the first question is, this looks a very good results. So I just wanted to say that these are all like single device level, right? This is all for a single synapse.
Yes, single synapse. Yes.
So 2 questions. One is in terms of now, ultimately your neuromorphic. I think you are looking for using the synapse in some kind of a crossbar array structure, right? For neuromorphic.
Yes. Yes.
So there are 2 things to approach this. I guess one is for this kind of devices, if you have a model. So right now we are designing crossbars in my group or in other groups. The models that we use as a single synapse are more like they are based on some experiment, but not these experiments. So the kind of thing that you are showing here, like precisely controlling domain wall and all, best of my understanding, even 3-4 years back, this level of precision people moving domain wall was not there. Experimentally.
It wasn't there. Yeah, it
wasn't there. As a result, the models are also more primitive. For example, when the model I use is much more primitive, it doesn't have this kind of precise domain wall motion. So it will be interesting to model this phenomena in some kind of micromagnetic software and then see how a large crossbar behaves, right? Because if you want to use phenomena, see how crossbar behaves, one strategy is to build a full crossbar, but that will take a lot of time. But I'm saying that can be a good, interesting research direction where you have a micromagnetic model which totally models this phenomena, and that can be fed into a crossbar array design. So have you looked into that? And the second is, have you thought about making experimental crossbars of these devices?
Okay. So for the first aspect, we have collaboration with IIT Roorkee. Brajesh Kumar is a member of my CRP.
Okay.
And internally, I am also collaborating with Professor Mohammad Sabri Ali. I don't know if you are familiar.
No.
He is from UC Berkeley. So
he's a visiting professor there or something.
No, he's an assistant professor in NTU now.
Oh, so now he's joined that formally. Okay.
Yeah. So they are members of this team, and they are looking at this kind of circuits.
Very good. Yeah.
Then for the second aspect, yes, we are looking at developing the circuit. But currently, if you look at the results, my devices are not even MTJs. So next step is to do the devices at MTJ level. So TMR changes from say 1000 to 3000 in many 8 steps or 16 steps.
Right.
That will be the second step. After this, we are planning to show circuit. So we have a collaboration with the Global Foundries.
Okay.
So they are also part of this team. So these are in the pipeline.
All right. So, but looking at the experimental data that are published already or on the archive, it's possible to reproduce them through simulations, right? I mean,
yes, yeah. This one we can simulate.
I mean, I can look at the data and be able to make some design which on the micromagnetic code which can do this kind of thing, right?
Yeah.
Okay.
So you can easily simulate the meander geometry. So meander geometry is the one I showed a few slides ago. Maybe I skipped because of the time constraint.
All right.
The meander geometry looks like this. So we have a device that goes like zigzag.
I see.
So by changing this distance, you can change the pinning strength, and you can precisely stop the domain walls at a different meander junction.
Okay.
So this can be easily simulated using micromagnet.
All right. Okay. Other question, please, from the audience?
I have a question, Prem.
Yeah, good.
Anil here. See, for this dual tungsten layer, probably I missed the point. What is the resistance change you are getting if you have this multiple states? I mean, probably I missed that point. Yeah.
Okay, so the resistance change is actually we measure the resistance of the whole stack. So the stack consists of tungsten, cobalt, and boron, MgO, then some ruthenium layer on top. So the resistivity of the whole stack is shown in this slide. There is no big difference. I mean, the stack with the high pressure tungsten shows resistivity of more than 120 microohm centimeter. That is the signature of the beta tungsten phase. So that's shown by the high pressure tungsten as well as the dual tungsten layer. Whereas if you use only the low pressure tungsten, the resistivity is lower.
Suppose if you make that meander structure, if you push the domain wall from one point to the other point, so what is the change in resistance if you introduce multiple domain wall versus n domain walls plus n versus n plus one domain wall? What could be a change in resistance, just to get a feeling?
So that is our next step. We haven't gone to that level, and we are only observing the domain wall motion by magnetic curve microscopy. But if you look at this illustration, so if you have, I mean, we have not studied MTJ yet. We are making we are making MTJ. So in the case of MTJ, let's say the lowest resistance state corresponds to 1000 ohm. The highest resistance may correspond to 3000 ohms based on a TMR of 200% MTJs yet.
Thank you. Thank you.
All right. If there are no more questions, let's move on to the next speaker. So the next speaker, is there any more question? Yeah.
Yeah, I had one question.
Sure, go ahead.
I was wondering when you said MTJs, for MTJs, in order to get the tunneling magnetization, the current has to go through the barrier, right? So
no, the current has to go through the spin Hall layer.
The MTJ is for the reading, not for writing.
MTJ is only for reading, yes. The reversal takes place, I mean the domain wall motion takes place by spin Hall effect. So the current only has to flow through the spin Hall layer.
So it's like a 3-terminal device.
SOTM
yes,
RAM.
It
It's
is
like a 3-terminal SOTM RAM, yeah.
Yes, it is a 3-terminal device, yes.
The problem is once you put these things in crossbars, the design becomes very critical. So yeah, because 3-terminal device, because the standard the things that people use for neuromorphic computing, the two standard devices are RAM and PCM, and they are mostly used in a two-terminal configuration in the crossbar. So the moment you have a third terminal, you have an additional line and all that. So our group is also looking into that. But yeah, if somebody else is doing this, yeah. It's a full crossbar design. Yeah. So do you have any more questions, please?
I had one short question. This high pressure tungsten, I probably missed that. What do you mean by high pressure tungsten? It was grown
so when you deposit the tungsten layer, you can change the gas pressure inside the sputtering chamber. So if you sputter your film at say 1 milliliter or below, we call that as a low pressure sputtering. So if the tungsten is sputtered at a gas pressure of 4 milliliter or above, we call it high pressure sputtering.
Okay.
Yeah. So basically the pressure of the argon gas pressure inside the sputtering chamber changes the morphology of the tungsten layer that we deposit.
Yeah.
You may have a very continuous smooth film, or you may have some granular film, depending on the sputter gas pressure.
Okay.
Maybe I just want to ask one more question and then we can go to the next speaker. I also thought about it. So has this question ever come up in when you are presenting this work, is that compared to RDAM or PCM, your change in conductance is much lower for a magnetic device.
Yes.
So between your lowest, like your negative weight and your positive, between your max and mean conductance, in RDAM the ratio is often 10 times. But even with 100% TMR, your best case ratio is 2:1. So how will this be able to compete with those devices?
Yeah, so this is obviously a drawback of the spin-based neuromorphic circuits. The resistance swing, the voltage swing that we may get is not that high comparable to our RAM or PC RAM. This is the main drawback.
Yeah.
But on the positive side, we can talk about endurance, all these things.
Agreed. Because there the endurance is much lower. Yeah. But this is often when you talk to other people like doing RDAM or PCM neuromorphic, they will say this is the main problem with Spintronic. So
yeah, this is the main problem.
Yeah. Okay, so let's move to the is that okay? Can you
let's.
Yeah. So
okay, thank you very much. Thanks everyone.
Yeah. So let me introduce the thank you for the talk. Okay, so coming to the next speaker, our next speaker in line is Professor Jyoti Mohanty from IIT Hyderabad. So he obtained his MTech in solid state physics from IIT Delhi in 2000, PhD from Polarized University, Humboldt University, Berlin, Germany in 2005. He did postdoctoral work at Catholic University, Leuven, Belgium, and at Department of Physics, University of California, San Diego, California, USA. Then he worked as a research scientist at Technical University, Berlin, Germany. Since 2012, he has been a faculty in the Department of Physics at IIT Hyderabad. where he's currently an associate professor. His research aims to gain understanding and solve issues related to PMA in magnetic thin film and multilayers, magnetic nanostructure, by tunable electrodeposition, multiferroic and magnetoelectric materials, carbon-based nanosystem. So I now request Professor Mohanty to give his talk.
Hello, can you see my screen now? Hello?
The screen is completely grayed out.
It's gray right now.
Oh, so let me re-share it. Just a minute. Yes, can you see it now?
Can you go to full screen? Ah, yeah.
Yes, I am going.
Okay. Yeah, you have to escape that. What is that? The slide view. There's 3 dots. Click the 3 dots. No, not there. Not there. 3 dots.
I don't see it.
No, in the 3 dots, just click escape presentation view. Go to the 3 dots here.
Yeah, okay.
Below, when it is showing the slide 1 to 24, just above that there are 3 dots. So click that.
Okay.
And so hide presentation view. Hide presentation view. Yeah.
Okay. Is that now clear?
Well, now it came back to the
normal one. Right? Can you see now?
It's coming. It was working before when it tested. I don't know why.
Yeah, I don't know why now. So on my screen it's fine. So can you see the slides moving? Yeah, probably, right?
Yeah, can you go to the full screen now?
It is now full screen.
Maybe you are using multiple window or something.
I can change that if that creates a problem. Is it better now?
Yeah, you can present like this also. It will work.
Okay. So
yeah, now it is good. Now it is good.
fine. Okay. So thank you, Chairman, for the introduction. So and thank you, the organizing committee, Professor Muduli as well, for giving me an opportunity to talk about my work here. So today I'll be talking about exploring PMA in ferromagnetic system for Spinterface applications. So essentially, I'll be talking about a lot of imaging aspects of this PMA material. There are different ways or different techniques where you can use the imaging, but and I have used many of those techniques. But for today's presentation, I will be using mostly lab-based techniques like LFM, MOOC kind of imaging to understand the ferromagnetic system. And towards the end, I will be showing not ferromagnetic system, another system which shows perpendicular magnetic anisotropy, and using the help of magnetic fields of MFM, you were able to write fermionic structures. Okay, so which would look like this is not fermion, but similar kind of structures that you can write with the T field of magnetic force matrices. Okay, And the work that I'm going to present today has a lot of contribution from my the student who is posted now at NUS, Abhishek. The work also has a lot of contribution from Arut from DMRL as a collaborator. Ajit and Himadri as the students who are currently working on this system. So without going much more, detail into it, I mean, as for this audience, so magnetic fermions and their importance are, manifold. All of you know that there are competing energies that, interact between different kinds of structures, and usually you're looking for a non-collinear field structure. And as compared to previous speaker, when you talk about manipulation by electric current, we know there are issues with spinning, impurities, and defects. And therefore, we are looking for structures where we have competition between, your Heisenberg exchange versus DMI interaction. I think Professor Anil also discussed about it a bit. So essentially, you're looking at such structures where we can go from, this block wall, needle wall kind of structure that comes out from the Heisenberg exchange, and then look for this Galatonsky-Moria interaction with interactions, and that lead to fermions. And but there are a lot of advantages of the fermions because it has low consumption, low energy consumption, high processing speed. You can have room temperature operations, and so the question is how can we stabilize and manipulate them? Of course, there are a lot of other applications. I think one of them was discussed by previous speaker, Professor Same, regarding neuromorphic computing. But what our interest is, these are essentially people are looking at ferromagnetic system. So if you look at the ferromagnetic system, mostly these are the systems I have listed. There are of course many things, but I have listed few. There are ferromagnetic heterostructures where you are dealing with competing interactions of exchange, dipolar, PMA, DMI. Okay, and that mostly happens because of your inversion symmetry, and you have a heavy metal close proximity with respect to ferromagnet. Okay. And there are also this aspect of looking at, taking this application forward in terms of fermion racetrack memory. I think there has been talks in the beginning of this conferences on talking about racetrack and application of fermion, anti-fermions, and so on and so forth. But there is one essential problem in that because of this net magnetic moment that exists in the ferromagnet. Because of that, you use the Lorentz force, you can find out that the force magnetization is pointing up or down, and you are sending current along this direction, so you get a velocity where the current moves out of the track. That happens essentially because of the Spinnerface Hall effect. So now our idea is to look at how to solve as a material perspective what kind of material that you can find out so that this Spinnerface Hall effect can be reduced. Of course, you can go for an antiferromagnet. There has been a lot of interest into looking at antiferromagnetic spintronics. But in terms of imaging, which we are interested in, antiferromagnet is not that easy, in terms of imaging aspect, because of the same concept that there is no net magnetic moment. You can utilize, synchrotron-based technique, X-ray, linear dichroism, and so on. But still, you can see the ferromagnetic imaging in synchrotron-based technique as well as antiferromagnetic. Antiferromagnetic imaging is really, really rare because of contrast and so on. Okay. So what we are saying that if you see the problem that is being faced in this ferromagnetic based, if you're looking for real device application of the diameter of the fermion that you might think of less than 50 nanometer, and if you go for lesser thickness, then that decrease stability. Then if you want to increase the speed, then you want to go for thicker film probably. If you go to thicker film, then that reduce your DMI. And again, as inherent, this Fermion Hall effect will come into the picture. What we are suggesting, or we are trying out in our group, in a material development aspect, that we take a combination of rare earth and tungsten metal where it has strong spin orbit coupling, and the PMA in the system can be controlled, and it shows stability at higher thicknesses. So part of this problem can be taken care. The Spinnerface Hall effect is reduced due to the very zero, because this is a compensated antiferromagnetic thing. So it's a ferrimagnetic system. There is no it's very close to zero magnetization. So that means the Spinnerface Hall effect can be reduced. And it is also better for writing and observation if you want practicality as compared to, as I said, antiferromagnetic fermions. Okay. And what are the other advantages? If you look at this, we have there are different variety of systems that you can explore. We will talk about two systems, but they consist of similar kind of material. One is done in a perpendicular PMA is created here, where the rare earth and transformator are antiparallel with respect to each other in successive layers. This is an multi-layer structure. In another case, we look at this tensile metal and rare earth in an alloy form, where the coupling between this rare earth and tensile metal sublattices are antiparallel with respect to each other. So if you look at both aspects from here, if you look at the magnetic profile, they look very identical. Okay, I'll show you few facts of that. What is the advantage here? The advantage here is the tensile metal gives you by default high Icee, and the rare earth gives you strong magnetic moment, and depending on the situations and the control growth parameter, you can control the perpendicular anisotropy in the system. Okay, and we wanted to look at the two-fold implementation of this. First is the choice of the material system. Second, we optimize with different cap layer to induce BMI, and this part we are still working on. And then we can tune the PMA in the system. As I said, this can control the PMA. One is by growth condition, second one by tuning it with external perturbations, for example, applying field and temperatures and so on. How do you want to what do you want to get from there? We wanted to image them. So there's local writing and imaging by T3. As I said, I will discuss that in the bit. It's not related to this term, but into another PMA system. And we want real space imaging in a lab based as compared to the lab scale facilities. And all this experiment we wanted to kind of understand better each and micromagnetic simulation to understand our experiment better. Okay? That is what I would like to discuss. This is one system. Before I go to the rare earth and transformator system, this is of course system has been used by many research groups across the globe, where people look at this cobalt platinum cobalt palladium based system. This system has cobalt is magnetic and the platinum is not, but in the process platinum might get slightly polarized and it gets induced moment at this structures. And we have looked at similar kind of structures, and this shows the structural magnetic characterization. So of course for PMA you can expect an square hysteresis, but we have grown this multi-layers with higher thicknesses and higher repetitions of the individual layers. So that the remnant goes to zero. In that sense, that would be quite nice for us for this understanding the domain dynamics in the system. Okay, but ideally, if you want the system to be having a certain memory, so we want the square kind of hysteresis. Look, this is a corresponding AFM and MFM image of the same sample, and we could understand the by doing micromagnetic simulation for the total sample, and we have considered here in 1 micron area. And the overall features we can match nicely, and of course the sizes could be small. This is like 10 micron scale as compared with 1 micron simulation. It's just because of the computation limitation in that. Okay, and we have these are the parameters that we use to understand the simulation. Okay, so if you go to as compared to this PMA system in cobalt platinum, if you go to rare earth and tensile metal, this is what the constituents of different layers has been given here, and we have repeated this 116 times by sputtering method, and these are the parameters for the growth. And what you see is that these both layers are anti-parallelly oriented with respect to each other. This is measured by K rotation, where you are sensitive to the upper layers or the surface property. Here, this is measured by VSM, which is the bulk property that you can measure for the entire thickness of the sample. And this shows they are oppositely magnetized with respect to each other. And if you measure as grown sample at at zero field, this is the domain structure that you will get. Okay, very nice domain pattern, and we are actually interested in this to understand what happens and how do we control this domain size and growth and different property domain walls in the system. Okay, so we can do this for a comparison, with the micro. This is the micromagnetic simulations. This is the micromagnetic simulation of this experimental data. You can see, so we have quite good match with that. Of course, the overall features are same. Maybe the sizes might be slightly different here and there. That's because of the real sample will have a lot of pinnings, defects, and so on. Where here we don't assume anything, any short sort of pinning and defects. This is the Z component of magnetization, and this is a 3D layer that we can simulate through. And this is what is sensed by the Z component of the field is sensed by the MFM. These two can be comparable. But as we have the whole volume of magnetization now created in this micromagnetic program, then we can take the X and Y component together, that is the contribution of domain wall. And these domain walls are quite narrow, okay, 10 to 20 nanometer or at most 50 nanometer. In those senses, It is very, very difficult by any technique to, to get those resolution maps, even if you go to very high intense X-rays, X-ray imaging using holography or other, microscopy techniques. So this we can understand, and then we can slice at different positions to get, how the depth profile of this magnetic surface looks like. Now we have grown these films. This is done in our lab, where we can grow. This is by E-beam evaporator, and you can see that iron. This is alloy films. Iron and gadolinium are antiparallel with respect to each other. This is an extensity measurement done for iron age and gadolinium age. This shows, they are opposite to each other. We have optimized the thickness of the film. You can see this is 33 nanometer, 50 nanometer, 100 nanometer, and these are ASM, MFM, and corresponding to the FFT data. It says that at 50 nanometer around, you have a PMA, kind of builds up in the system, and it becomes robust once you go to 100 nanometer. And we have done the analysis to find out, what is the evolution of these domains and so forth. Okay, and it has. It's at 100 nanometer, you see the two second order peaks, which shows that it has a long range order for the entire sample surface, which is quite good for a lot of other applications. As I said before, everything we check with micromagnetic to understand the energetics of the system, and this shows the domain and domain wall for different thicknesses, and this is quite comparable to our experimental observations. And as we can match the domains with our experiment, we can extract a lot of parameters from the experiment and try to compare with the simulation. And this shows one where the domain size and thickness varies. This is the domain one width. As you can see, it is quite trivial, of course, that the domain size decreases as you go on to higher thickness, and then domain wall contribution kind of try to the domain wall increases and domain wall, I'm wrong. So domain size increases as we increase the thickness of the film, and the domain wall contribution tries to decrease. So they're vice versa. And then from there we can get the total energy contribution of this. And what it says that at higher thicknesses, demagnetization energy actually aids to sustain the outer plane component of the PMA, this material system. Now we have created this. As I said, we can manipulate this one. There are different ways to manipulate. We can do local as well as non-local manipulation. So we have used something called the laser-induced local modification. So this is the sample where we impinge the laser. The detail of the laser conditions are mentioned over here. This is the sample here, and we have this is the area which is exposed to laser. And what we see that the area which is affected by this laser intensity, the pulse of the laser, that the domain gets drastically changed as compared to the other area. Okay, and we try to understand that by modeling it with micromagnetic simulations. What you can see is that this area is modeled by considering anisotropy. Okay, that is a special distribution of magnetic anisotropy. That means this anisotropy is the anisotropy of the field as it is. And then we have graded the anisotropy, and of course the anisotropy is weaker at the center spot, which is more affected, and then it is graded from there to the outer area. So that can explain what is happening in the system. And of course we looked at the time dynamics of this one, which is I didn't discuss. I am not going to discuss this part over here. This is local modifications. We are also done non-local modifications in terms of heat treatment. So we have tried with a conventional annealing, which is 50 degrees Celsius per minute, and that actually shows no strong effect in terms of domain pattern, but we have used then rapid thermal processing where we heat the sample at 250 degrees Celsius per minute. Then we do two conditions. We fix the temperature and then vary the and keep the time constant. Okay, this is an overall property that you can see. This is as prepared sample AFM and MFM. The upper layers are all AFM and lower images are all MFM. This is at 300 degree, 400 degree, 600, 500 degree RTP for a fixed interval of time. What you can see that at 300 degrees, still the domains are there, but they are kind of contrast as weakened. And then as you go to 400, there are a lot of surface gets quite a lot of flux and things comes up on the surface. And the magnetic properties as far as the domains are concerned, we cannot image anything because the surface is so rough now. So that in these cases, how do you understand what happens? So therefore, we turn into the micromagnetic domains analysis in these cases to understand, because here this measurement doesn't, the topography doesn't allow us to do any more measurements in terms of magnetic imaging here. So this is kind of a summary of all that we have varied. So this is the time, and this is this is with AFM and MFM. This is where we have fixed the temperature and vary the time. These are two sequences that we have followed, and we can see there are a lot of reduction in domain sizes occurs, and then domain try to orient in different directions, and then you get a lot of topography induced contrast. Therefore, we cannot basically measure this kind of sample in MFM. We try to understand what is happening in the system. So we have done TEM and also for these samples to understand what happens at the interface between the substrate as well as in the films and the cap layer. So this shows that this is as prepared sample which is amorphous in nature, and then as you increase the RTP time, as you can see at 220 minutes RTP time, you can see iron crystallization VCC form, and there are reactions happening between the silicon substrate and iron interface. And of course, the upper surface, you can have free iron. So that means what is happening in this case, because of this RCP, the iron tries to knock out from the interstructure of gadolinium iron and go to the surface. And the iron becomes free. And that, if you zoom into these areas, you can see the lattice planes here, and that corresponds to the free iron VCC structure. And we have done elemental mapping to find out all the details in there. So we have also done RBS analysis to find out what is actually happening because of this temperature treatment, and it turned out that without going too much of detail into this, of course we can follow the details in the paper. Is that there is an outgress of iron from the film to the surfaces, and at the same time on the bottom area the iron gets reacts with silicon, and there is formation of iron silicide at the surface. And so that means because of this, the magnetic properties also get enhanced. So we can see that the outer plane field saturation increases compared to in plane saturation compared to here, because the higher MS happens due to the free iron. Iron was before the RCP, iron was in the lattice of iron gadolinium, and because of this RCP at this temperature and time, iron kind of become free, and free iron shows high MS as compared to this in the environment of gadolinium or any other element. So the in-plane remanence also increases. So what we see is actually the RCP tries to reduce the magnetic anisotropy from perpendicular direction to in-plane direction. That means we have a reorientation of spins happens. So that basically we destroy the perpendicular anisotropy in the system. Okay, so that means there is one way to control, and then we can destroy. We know how much temperature stability it needs to destroy this kind of PMA in the structure. Okay. We can also understand this in the simulation without going much of the detail. What we have done, we have assumed that the PMA we have a tilt. The anisotropy has a tilt angle. So we have fixed the saturation. We have varied the tilt in the anisotropy. So what we are saying, the PMA was perfect, perfectly perfect to the around the Z direction. So imagine there is a slight tilt in the PMA. If the tilt angle increases, what happens to the domain structure? This is one aspect. Second, we have checked we kept the MS constant, we vary the KU, anisotropy has been varied, and then we see what happens to the total overall behavior of this one. So we can understand that the contrast variation as well as the domain wall energetics from this, and we can the experimental value it's well matched when we consider the combination of anisotropy tilt as well as MS variations as we get the input from the experiment. And then also we try to optimize this PMA or modify this PMA by ion beam, and with ion beam playing with the energy of the ion and doses of the ion, we can destroy the PMA in the system. Okay, so this is an Ars-grown sample, so it's an AFM and MFM image, and this is the corresponding magnetic measurements of the sample. And when we apply argon ions doses from here, I can see. So A and B are with different energies, 50 kV and 100 kV, and from here to there we varied the fluences. You can see the PMA of the structure is completely gone. So this was outer plane, the domain structure reduces in sizes, and after we increase the fluence to higher fluences, up to 10 to the power 16 ions per centimeter square, the magnetization goes in plane, and this is evident by the in plane contrast that we see here in the MFM as compared to this outer plane structure that we measure for the Ars-grown sample. Okay. And we have gone further to look at this combination of two layers, bilayer structures, and there we see that depending on if the TBFE is little stronger in terms of anisotropy as compared to GDFE, and if we go TBAP on top of DDAP versus DDAP on top of TBAP, if we change the sequences, the effect is very, very different. Here you get a combined structure. You can see here. DDAP on top gives a combined structure of both domains. This is individual DTAP, this is individual TBAP layer. If you make the both layer on top of each other, then you can see this is a combined pattern of both these. While if you put TBAP on top and DDAP in bottom, you see the two isolated domains. So the lines domain that is small one is because of the DDAP, and this isolated fat kind of structure that happens because of the stronger anisotropy of TBAP. We have done this measurements at indoor, IEC indoor. Here we looked at the low temperature MSM data. You can see this is at 175 K, which is where you see the GDAP contribution domain as well as the TBAP bigger domain. When you go to low temperature, the anisotropy of TBAP is quite strong, so only you see the TBAP contribution domain. And this also, you can see the switching field that happens at different temperatures. And we try to understand that much more using XMCD measurement. This has been done at a synchrotron facility at Icee in Germany, and this shows clearly this is 300K, 150, and 100K. These three columns, the upper one are for iron, this is for gadolinium, this is for terbium. As you can see, iron and gadolinium are oppositely magnetized with respect to each other, which is always true. And then terbium is parallel to gadolinium. As you decrease the temperature, you see there is a state-like structure comes into picture, okay, because of the two structures try to decouple from each other. While the anisotropy or the corrosivity of gadolinium remains same, the corrosivity of terbium kind of expands a lot, because terbium is everything is dominated by terbium. We are yet to analyze the total spin moment observed in these systems, and also we have done imaging of using the CCD to understand what happens to the domains in the structure. The idea, as I said, I'm almost close towards the end of my talk. So this is what our idea is to create the domain. So this is still modeling data. We have taken a TBCO and a GDAP sample. So as a bilayer structure, as you can see over here, and without any DMI, what we said, this structure has an inherent tilt in magnetism. In the local environment, you see the magnetization is not exactly perpendicular with respect. They are slightly tilted with respect to each other. So we have kind of model the systems assuming that the magnetization is tilting within the volume of it. And if we do this and then try to understand what is happening as a function of different layer thickness, this is a kind of phase diagram. This is a thickness of TBCO layer, this is a thickness of the DFE layer, and this is phase diagram which shows that depending on the thickness of both layers, we can get variety of magnetic domains as well as chirality that for this fermions in the system. This is two scorpions that we can see both layers, both TBAP and GDAP layer. And if you apply magnetic field, we can create this kind of lattice structures where the scorpion gets stabilized. This is purely kind of a simulation result. We are still thinking of optimizing the system for a sample and experiment. As a final point, this is a slightly different system where we have this is done in collaboration through an India-Russia project, where this is not a rare earth and transformator system. This is cobalt iron silicon boron system. We have platinum here, so the platinum and this system gives you PMA, and this tungsten interface actually is responsible for DMI. And all of you know the platinum with respect to an ferromagnet, it has a negative DMI, and tungsten with respect to ferromagnet you have a positive DMI. But this is reversed here. So you see that aids to the DMI. So total DMI observed from brilliant light scattering is around minus 1.09 off per centimeter square in this case. Now what we have done here, this is experiment and simulation data. You can see it looks very similar to our rare earth kind of combination system. This is a magnetic domain of this one. Of course, what you can do, you apply field and you can go to a situation where we create a magnetic the size of this domain decreases and so on, but it doesn't form fermion by default. As we increase the field, it's because probably the DMI that needs is lower than the nucleation of fermions. But what we have done is apply the field with the tip field of the MFM. Okay, so this is done. So I think this is shown over here. This is the scheme that is done in the simulation, and this is the corresponding experiment. So as you can see, this marked area in dotted rectangle here, this area is never scanned. So that means we come for a tapping mode where we come very close to the sample surface, almost we tap it, So that is the field is applied perpendicular directions, both respect to sample and tip. And you see, we create these coordinates here, only this area that we scan. After that, what we do, we image in a non-contact mode where we can image the entire sample. So those area what we scan with the tip with a tapping mode where we can create this. Of course, there are a lot of optimization done to create this kind of structure, how much of field that we apply, how do we scan, what are the rate of scan. Okay, and here it shows. I think it shows a video, but okay. So somehow it doesn't show the video. So actually, you can create these patterns over here by the TP scanning from this direction. Of course, you can scan from another X direction, Y direction, and Y direction. To do a full scan, outer area will remain as it is, and the area that you scan, it will show you the formation of fermion. This one, and this is a very recent work, and it's published in ACS Nano. If you are interested, please have a look at the detail there. So with that, I hope I have explained you that what is the importance of looking at ferrimagnetic system for understanding, and how to control PMA and how to basically create and destroy PMA in the system. So when I say destroy, that means when you know how to destroy it, probably we will understand much more how do we create it and what is the potential of creating a stronger PMA in the system. And we also are interested in exploring the same exact technique of using a MFM chip in our sample to write the fermion as compared to what we have done in this QIP based system. With that, I will show you a nice, high resolution MFM imaging of a very large area and a cobalt platinum sample. And of course, we have the capability to look at, very high aspect ratio nanostructures where the roughness is, the sample heights are very, very different, but still you can able to get nice, structures which can be used for, this honeycomb and other kind of applications. I would like to thank the funding agencies, ACRB, DAD, this is the Russia Foundation for our combined project, and MHRD for the funding, as well as the DAE and DRDO for the funding. Thank you very much. Hello?
Yeah, so I would just open the floor for questions now. And if people have questions, they can please ask here or write on the chat and I can read it out.
Okay.
No questions?
There is no question on the chat.
No, I don't see any question on the chat. Yeah. Professor Mudil, you can ask me.
There is any question from the participants?
Yeah, you can unmute your microphone and also speak.
Well, maybe I will start with one question.
Yeah.
So this MFM direct write lithography. So you are using MFM to create the fermion. I didn't understand what is the message.
The message is.
Or you are moving the fermion by.
No. So what we do, we have the sample which is the usual at room at zero field. This is how the magnetization profile looks like. Okay. Now what we do is we apply a field both to the sample and the tip. So that means we rise close to where we have a single where the fermion comes to appear. So that means these domains are going to shrink in size. They form fermion. Okay. Now, how do you create this fermion to move? Actually, maybe this will move now. We can see this if possible. No. No, it doesn't work. So what we are doing, with the tip field of the MFM, we are scanning the sample. Okay, the sample area is scanned here. So this area, so that means you already apply a field, which is the field close to the nucleus of fermion in this material, because it has a DMI. Okay, as I told before. Now, but spontaneously it doesn't create those DMI because you need to apply the field up to that values here. And then on top of that, we move the tip on top of this, and of course we control the field values. Then we can write this fermions on top of that, okay, on this areas only. Now, how do you know that we are writing? Because when this is where we are very close to the sample, almost kind of touching the sample with the tip field, and then we take it off and then try to image this sample with a non-contact measurement where we are a little far away, maybe 50 nanometer off from the sample surface, which is shown over here. Okay, so this area has been scanned with the tip field, where you see the domains as the fermions are being created, and the outer side area where the tip is not scanned, this still remains as the original samples where we have this normal domain, the normal maze type of labyrinth kind of domain. That is what I meant by creating or writing a fermion using the magnetic force microscopy locally.
See, the other system that you talked about, where the torbium based, can this called graded anisotropy kind of system, or it's a different?
Actually, because what happens along, so if you take GD-FE system, so GD and FE they are pointing anti-parallel to with respect to each other. But when you add terbium, what it does, because it has a strong anisotropy, it try to tilt the anisotropy slightly off from the perpendicular direction. So you have a tilt in the anisotropy. But if you take an effective anisotropy, it will be always along the perpendicular direction. Now, when you combine this system, you make a bilayer system of TBFE, TBCO, and GDFE. Then your local environment, if you go to check it layer by layer, then they are not actually perpendicular with respect to each other. So they are slightly tilted with respect to each other. That is what you can think of that as if there is a graded anisotropy created within the system.
Okay. Is there any other question? I don't see any question in the chat window. Maybe from the participants here.
Okay.
By the way, the poster session people, you have informed them, right, that this is running late, or is there no poster session today?
There is no poster today for our.
Okay. All right. So then we have time. Then maybe we can have some more questions if there are people interested, or we can. Is Bhaskaran here, Professor Bhaskaran?
Yeah, I'm here.
Yeah. Okay, so then we can go on to the next speaker. So I will first go through the introduction for the next invited speaker, Professor Bhaskaran Muralidharan. Professor Bhaskaran Muralidharan obtained his BTech in electrical engineering from IIT Bombay in 2001, MS and PhD in electrical engineering from Purdue, West Lafayette, USA in 2003 and 2008 respectively. Between 2008 and 2012, he was a postdoctoral research associate at MIT and then at Institute for Theoretical Physics at University of Regensburg, Germany. Since 2012, he has been a faculty in the Department of Electrical Engineering at IIT Bombay, where he is currently an associate professor. He was also the recipient of the APS IUSSS TTF Professorship Award in 2014, the Shastri Indo-Canadian Fellowship 2019, and the ACRB Science and Technology Award for Research Star in 2020. So now I invite Professor Bhaskaran to give the talk.
So you can see my screen.
Yeah.
Yeah, everything good?
Yes, good. Go ahead.
Okay, so thank you, Debanjan, for this interview, and also thank everyone for inviting me for this conference. I've been associated with Icee since 2014, as we used to host it. So it turns out that my talk is probably the only theory talk in this whole spintronic session, possibly. So I'd like to start my talk. It's titled as Resonance Spin Filtering in Spin Torque Devices. So what we have here is our web page, which mainly our group works on quantum transport, and spintronics is an integral part of many things we do. Okay, so here's the outline of the talk. So today's talk, I will be talking about some of the works we did in the last 3-4 years, which is this idea of that you can use superlattice structures to engineer spin filtering in for various applications in what's the spintronics and spin torque. And everything that we do centered around this Keldysh formalism for quantum transport, which I'll introduce in the very beginning. And I'd like to briefly go into the other aspect which we're actively pursuing. In the end, we will talk about superconducting hybrid systems, where the theoretical framework is slightly different, but still it's a very important problem, that is a Rashba nanowire coupled to a superconductor. Okay. So the reason why quantum transport is very important, this is an engineering conference and I'd like to introduce this very important area, is that most of the device modeling, the reason, I'm explaining the reason why we are here, is that in electrical engineering, so device modeling has gotten to a very interesting juncture at this moment. We used to be in what's called the diffusive limit, where all quantum aspects are kind of encapsulated in some, constants and, effective mass and things like that. But as we moved on, we reached the ballistic limit where the concept of conductance was not so obvious as in the diffusive limit. Ohm's law was not valid, so on and so forth. And now devices have reached the quantum limit where the length is smaller than the mean free path, as well as the phase relaxation length and so on. So we are in a very, very, very tiny limit. And so here is when the quantum transport formalism should be applied in full force. So let me explain some of the basics very well. See, the important aspect of quantum transport is the fact that, the channel is what is there in the device. And that is typically captured by material scientists by using sophisticated Hamiltonian techniques and density functional, etc. However, a device modeling involves something more advanced. That is, it also includes the fact that you have a source and drain reservoirs connected to the channel, making it completely out of equilibrium because you apply a voltage, temperature gradient, shine light, do various kinds of things. So we need to look into the interface physics. And finally, there is an inflow-outflow dynamics, which finally gives you the current. We all agree to the fact that electrical engineers are concerned about current flow and the fact that nano devices also, almost all the advanced applications are related to finally measuring some kinds of currents. So the way currents are understood from a theoretical framework was beautifully developed in Feynman lectures on computation, surprisingly, where he talks about current flow in a device simply by considering a hydrodynamic analog where you have a source and drain reservoir and a canal that sort of acts as a channel. And as you lower the level of the reservoir on one side, if the canal is present between the two heights, water will flow. Of course, you can maintain steady state by connecting to a pump. Similarly, this is what happens in a nano device. You have a source, you have a drain, and you change the chemical potentials of the source and drain, and the number of states available between the source and drain potentials acts like the canal, and then a steady current is established through a battery. So another thing we electrical engineers are interested is the local control of the channel, which is like a tap that you have in a hydrodynamic system, and it is turning on and off. That is what you use as a gate. So all these concepts can be encapsulated into a mathematical model, which basically comes from a very advanced formalism in physics called the Keldysh formalism. And this is what we call as a non-equilibrium Green's function technique for device modeling. So basically, we have all the important aspects. The material aspects can be captured through a Hamiltonian and the interaction U. And the interface aspects are kind of captured through the self-energy with the inflow-outflow dynamics. And finally, the dissipative aspects in the channel can be captured through additional self-energy terms, which I'll talk about a little. So this is a unified framework to understand any device paradigm. We have applied it to various problems. It's like once you know Newton's law, you can apply it to cricket match or you can apply it to spacecraft, something like that. So this all starts with this beautiful, very interesting formalism called the Keldysh non-equilibrium Green's function technique, which basically treats quantum aspects through correlators. This is nothing but a correlator, correlates a wave function from time 1 and time 2. So these are fluctuations, and quantum fluctuations in the wave functions are treated using correlators. And we can do spintronic model by introducing the wave function as a spinner, which is basically, operator of the upspin and the operator of the downspin electron. And using this, we can build all these correlators. And using these correlators and noting the fact that we are doing steady state theory, anybody in electrical engineering knows that a correlation between two random processes with a correlator in a random process in steady state depends on the time difference, and that transforms to energy in the quantum case. And then we can write all the concepts of steady state into a energy in an energy axis, and then we can write the currents from the Green's function. So this is the basic idea of the big framework of the Green's function technique, especially in the non-equilibrium, to apply for device modeling. And this starts from the ancient 1965 Keldysh classic approach. So now that we have this, it's a matter of a few lectures that I can convince you, starting from the Keldysh correlation, you can go into what is called the matricized version of Green's functions, which can be employed by engineers by sitting on a high performance workstation. So all we need is a first step to invert the Green's function, invert these matrices to get the Green's function. From there, you can get all local properties like density of states, the electron density, and channel currents. Similarly, in the dissipative quantum transport, you can get everything you want by introducing the scatterers and the diffusion, scattering processes. So here we have the ballistic transport, and here we have the diffusive transport, completing the entire gamut of devices that can be modeled in this formulation. So no wonder that with this formulation, over the last 20 years, people have modeled all kinds of devices, starting from silicon channel, molecular electronics, silicon germanium transistors, and most importantly, magnetic RAM, which I'll talk about. So in our group, we've been kind of developing various aspects of this technique. As I told you, once you have those equations that I showed in the last slide, that's, it's literally like I know force is equal to mass times acceleration, but the application is complicated for each problem, right? Once you know Newton's law, you have to apply it to various problems. Same way, some of the things we worked in the last 4 years include the dissipative models, for instance, introducing non-equilibrium Green's function with, coupling to phonons, and seeing power dissipation in devices. We've also done decoherence effects with spin baths and other things. And most importantly, this is what I'll talk about, spintronic models coupled with magnet dynamics and also stochastic noise, which is a full-fledged thing which we have developed for this spintronics simulations. So today's talk will be, this is the basic introduction to quantum transport. So we'll be talking about superlattice spintronics and specifically some of the works which we've done in the last 4 years. And I will move on, change gears shortly into superconducting hybrid systems. So the idea of the superlattice spintronics comes from something interesting, that in quantum mechanics, two resistors need not sum to be twice the resistance. This is a standard interference effect. Those who have studied weak localization know this, but in electrical engineering, I explain it in a simple way. Two resistors give you 2R, but if you have two quantum resistors, they need not give you 2R. They can give you much smaller. Best example is, you can treat a quantum resistor as a barrier. A single barrier and two barriers together will not give you like a sum, right? When you have two barriers, you have these coherent effects where, electron comes in and certain energies, you can get perfect transmission. This is a well-known resonant tunneling effect. This clearly shows that it's not a monotonic sum of the two resistances. And this application of resonant tunneling was thought of in the 1990s, and a lot of devices were thought of, including the oscillators and things like that. But now we'd like to apply these concepts for spin filtering in the next few slides. So, as we know, spintronics is a very interesting juncture, and many types of things. Spintronics can lead to many things. One is the collective magnetization, which all of you are talking about, which will give rise to possibly switching and other applications, which is basically a substitution of CMOS paradigm, except that you use 0 and 1 as the up, down, or relative orientations of the magnets. The good advantage is these are room temperatures. So you can also use unstable magnets. There's a lot of work on the p-bits, which people have talked about in various contexts. That is, you can have unstable magnets to do computation. The other side of the story is the single spins, where you can use single spins as quantum bits and you can controllably rotate them to create the delicate superposition at very low temperatures to achieve quantum computing. Anyway, so we will be talking about these spin torque devices. They do not need any introduction at this point, but we all know one very important concept, that driving a current through a layered device can flip the magnet's orientation based on the Slonimsky spin transfer torque. And this obviously has tremendous applications, as we know that the MRAM technology is slowly coming to the fore. So the entire paradigm of the spin transfer torque is simply based on a a single barrier device where you have two magnets and you pass a current. It acts as a polarizer and sends a current to an analyzer and could flip it. This is simply based on a single barrier tunneling physics. Now, what happens is if we introduce multiple barriers, because these are stacked structures, we could show many interesting effects. So one of the most important effect is that in a multi-barrier device, it's like two quantum resistors that I showed you. And when you pass through a multi-barrier device, you can have these interesting resonant peaks. And these resonant peaks can give you some kind of new physics, is what we're showing. Now, very interestingly, people are also talking about 2D devices, stacking them to form MTJs. And there's a lot of interesting van der Waals ideas coming out of stacking various 2D functional structures. And the physics is essentially the same, that basically you stack some structures, you can have these resonant effects. Right? So what we have is monotonic opacity to tunneling in a single barrier structure, and in a multi-barrier structure, you have the physics of resonant tunneling. So here we are going to show a few applications due to these resonant states. And today we'll be talking mainly about enhanced switching abilities and to some extent magnetization dynamics. Our first work came back in 2014 where we hinted at the possibility that resonant filtering can give rise to a better spin transfer torque. So the idea is very simple. All of us know that the TMR is a tunnel magnetoresistance. That's the resistance between the parallel and the anti-parallel configuration can give you how good you can resolve the upper, +1 and 0 and 1 states. Now, a typical tri-layer device can show you some sort of a interesting TMR profile with voltage. But when you have a pentalayer structure, due to spin filtering, you can get a very interesting high profile, large TMR effects due to this resonant spin filtering, which I'll explain in the next slide. Okay, so the idea of spin filtering is as follows. You got these sharp resonant peaks that come in, and basically you have in the parallel and anti-parallel configuration different types of barrier structures, because you have the ferromagnet that has the exchange splitting, and you have the parallel configuration, you have the anti-parallel configuration. Now, due to the structure of the barriers, what you can achieve is the fact that in near the Fermi energy, where you conduct, when you conduct a current, you can have a resonant peak available for the upspin and not available for the downspin, creating a very nice filter. And this really makes it very sensitive. And due to the sensitive filtering abilities, you can sort of, conduct only one type of spin and not the other, giving rise to a super high TMR effect. And this effect has also been interestingly studied on the side in molecular spin filtering, where people did notice that, the molecular magnets states can have, perfect filtering of the upspin and downspin states and give rise to, currents that are very specific to the spin filtering happening in the configuration. However, we'd like to go further and see how the spin filtering affects the so-called spin transfer torque. We all know, again, since it's a spintronic group, that there is also not just the flow of current, but the magnetization dynamics that is incited by the current that can give rise to the torque and various things. And that's how you write information into a MRAM unit. So this magnetization dynamics is given by the precision term, the damping term, and the spin transfer torque term. Okay. So for this, of course, in terms of modeling and simulation and theory, we need to calculate what are called spin currents. Okay. So for this, we have developed our simulation platform in a systematic way. First is we, of course, did the spin transport simulation platform using the non-equilibrium Green's function, where apart from the charge current operator, we can also calculate the spin current operator from the Keldysh formalism. However, that's not enough. You have to feed it into the magnetization dynamics, because each time a spin current comes in, it updates the state of the magnet. And that updated state goes back into the system because the magnet state affects the channel current and so on. So it's a self-consistent loop here. Apart from that, the channel also has a Poisson part where there is a barriers which are getting modulated. So we have this full-fledged simulation platform that includes the Poisson equation with the Green's function, calculation of spin currents coupled with the Landau-Lifshitz-Gilbert solver for the magnet dynamics. So with this, we were inspired by optics next to design these multiple structures, which is the anti-reflective stuff I talked about. And specifically, there's this Fabry-Perot effect, where you can have complete anti-reflection at certain angles and at certain wavelengths, which are called Fabry-Perot filters. Similarly, we believe that we can generate such effects and see how it can affect MTJ structures by having the fixed magnet and the free magnet, and you have several layers which form the super lattice. And we have another type of structure which are this Fabry-Perot type, reflective layers, which we'll talk about, which we proposed back in 2018, just inspired by this optics phenomenon. So the idea is you have several layers. You have the fixed and free magnets, and then in this case, you have the anti-reflective layer, which is like half the width of the standard layers that is put in the two sides, which can actually create an interesting bandpass filter effect. Now, I'm saying all this that it looks like a 1D device, but the point is this can be applied in the context of several of the stacking of 2D devices that people are trying to explore now, which we are also beginning to start working on. So this is just a simple proposition that such spin filtering effects can be used in, in a stacked surface, structure. So here, when we could see that the Fabry-Perot magnet junction has this sensitivity to the spin filtering effect, you see in the parallel configuration, you have the upspin states, and in the anti-parallel configuration, you do not have these states. That gives rise to a super high TMR. Same with the regular super lattice structure. Now, using this, we tried to model the MTJ device. So the MTJ device, if we plot the charge currents in the parallel configuration and the anti-parallel configuration with voltage, and then you find the difference out, you can get what is called the TMR profile that tells you the percentage of TMR. You can also plot the Slonimsky spin torque term and the field-like spin torque term. This is the standard MTJ profile. Now, when you have these superlattice type devices, the spin filtering is way more enhanced. If you can compare the first panel on the left and the right, you can see that the anti-parallel current is much smaller compared to the parallel current, giving rise to a super high TMR, possible TMR. And of course, the Slonimsky and the this perpendicular, which is the field-like term, have a very different profile. And most interestingly, the Slonimsky term has a parallel, is basically symmetric, giving rise to the possibility of, having switching in both sides. One thing very interesting is this field-like torque, which is the perpendicular term, can have positive and negative signs. That shows that the spontaneous magnetization alignment can also change between ferromagnetic and antiferromagnetic. So then we studied the switching characteristics of the device by coupling it with the Landau-Lifshitz-Gilbert, and we could see that as you change the number of barriers, the critical voltage for switching sort of comes down, and from parallel to antiparallel and antiparallel to parallel. Now, what is more interesting is that the TMR fluctuates with the well width, as well as the Slonimsky term fluctuates with the well width. And of course, the switching profiles, as you can see, going from parallel to anti-parallel and anti-parallel to parallel is kind of more energy conserving, which I'll show you in the next slide. I have a question. Is my pointer visible or is my cursor visible?
Can you? I don't see the pointer now.
Now, can you see the cursor?
I can see the cursor, but can you move it a bit, like in the center?
Sorry?
It's a bit small.
Okay.
It's small and the motion is not very controlled, as in it just jumps.
Okay. So how do you turn on the, sorry for this. How do you turn on the?
Maybe you mention which figure to look at and we'll just take a look.
Okay, that's fine. Okay. So next we moved on to the spin transfer torque RAM with these structures. And we know very well that the spin transfer torque RAM is something that we are very interested in due to various interesting possibilities that come from in terms of the other mainstream competing memory technologies. This is the standard stuff about how much energy read, write, etc. So I'd like to start with our latest work, which we have submitted and is under progress, that we now propose a similar type of structure, a stack between the free and free and fixed ferromagnet. Here we have used a spin transport formalism coupled with the stochastic Landau-Lifshitz-Gilbert formulation. And in the stochastic LLG, we have introduced the stochastic fields into the picture. So now what we do next is that we try to see the switching probability of the device with respect to the applied pulse. I believe things like this will be useful for even understanding neuromorphic design and things, but we are just looking at regular switching. What we see is we vary the pulse width and the pulse height, and then we see what happens to the pen multi-layer structure and the tri-layer structure. This top panel is the tri-layer structure where you can see the switching probability and the switching time, and they are not very different with respect to the tri-layer and the so-called superlattice device. As you can see, the switching time is literally the same. However, you can see that the switching voltage is obviously much lower, corresponding to a much better energy profile. Between here you have about a 10th reduction of the switching voltage. So with this, we kind of plotted the voltage pulse width ratios and the switching probability landscape, from which we can see that, in a tri-layer device in the left panel, you have the switching probability and the time, the probability, this is the switching probability map, and with respect to the voltage from parallel to the anti-parallel, as you can see, this is the map. And here we have the, energy profile, which is in picojoules as expected. And from the anti-parallel to the parallel, we have, the map, which looks like typical stuff that we can see that we took cross sections to sort of show you some simple plots there. And then similarly, we have the energy profile. But now when you go into the, bandpass device or the Fabry-Perot device, we can kind of see that the switching energy is considerably reduced by a 10th. And similarly for parallel to anti-parallel as well as anti-parallel to parallel, kind of giving us an indication that you could use these structures for low energy switching purposes. So then we sort of studied the switching time and switching energy profiles as a conclusion from this, which we could show that the switching time goes down as expected with the application with reduction of voltage, and the switching switching energy goes down and the switching time goes up, which is expected. The difference is that when we talk about the penta-layer structure versus the tri-layer structure, you can kind of see that there's a much better performance when it comes to the switching energy. So with this, I kind of like to conclude that the large spin transfer torque in these kind of penta-layer structures or the multi-layer, what's called superlattice structures, gives a much lower bias for switching voltage. The switching energy is considerably smaller, and it has much more energy efficiency than the tri-layer based devices. I'd like to reiterate that this all that I have shown is coming from the concept of the filtering effect that is coming from multi-layer superlattice structures. Now, these superlattices need not be just engineered by the way we are talking about, but can also be used like a 2D stack, which people are talking about as a van der Waals stack. So the summary of this set of works was the fact that enhanced TMR can come due to spin filtering effects that can come only from multiple layer tunneling, and it gives a lot of interesting features, including possibility of better energy performance in the spin torque. Also, in a related work in 2017 in PhysRev Applied, we showed that the spin torque oscillator performance is also amplified a lot. I didn't talk about this little more ancient work, but we were only talking the last couple of years' work. I'd also like to point out that we have a couple of other works on thermal spin transfer torque, which I haven't presented here, but that's also a possibility that's looking promising in terms of engineering resonant structures for these purposes. Now I'd like to switch gears into what's called hybrid quantum systems, because they're forming a very important aspect in spintronics, whether it is the control of single spins for quantum computation, or whether it's the control or the use of Rashba spin orbit coupling and things like that. So hybrid quantum system is typically a system where you're coupling 1 or 2 degrees of freedom together to achieve certain functionalities. For instance, on the right panel, you're coupling a waveguide to quantum bits, giving rise to hybrid photon and spin manipulation. In the lower left panel, you're coupling the quantum system to a micromechanical resonator, coupling the phonon degree of freedom to the electronic degree of freedom and so on. So today I'll be talking mainly about how we're coupling superconductor to the nanowire, which is this 2 degrees of freedom, the Cooper pairs, and the normal system. So these are very important systems. As you know, most important is the fact that, when you have a Rashba nanowire, spin orbit coupled nanowire coupled to superconductors, we have these special things called the Majorana bound states. And as you know, this will form the basis of what is called the topological quantum bits. And these are supposedly, fault tolerant in terms of the quantum computing paradigms. So here again, we can sort of change our approach and use the same formulation, but adapt it to superconductors. So when you have a superconducting system sitting in the hybrid somewhere, you have to use what is called a Nambu spinner. In the earlier example, we used spinner, which contained an upspin electron and a downspin electron. That's a spinner, right? Here we have an interesting spinner, which is an upspin electron, but a downspin hole. Okay, so this is a C and a C dagger, which tells you have a operator for an upspin electron and an operator for a downspin hole. And this forms what is called the basis of modeling superconducting hybrid systems. Okay, so one of the most interesting processes that happens when you connect a superconductor to a normal system is called N-wave reflection. The basic idea, if you look at the right panel, is the fact that when you have a superconductor, there is a gap which is induced with the formation because of the formation of Cooper pairs. So when you have a normal conducting system, then when an electron tries to tunnel into the superconductor, it has to take another electron away with it. So basically, to form a Cooper pair in the superconductor. So in this kind of a reflection, an electron goes in and a hole is reflected out. And due to this, what you have is doubling of the conductance and so on. So one of the most important effects in all this is the Josephson effect. So basically, when you have a strong link, that is when you put a nanowire or something in between two superconductors, you get a very interesting so-called current phase relationship, or the Josephson effect, that is coming due to the N-wave reflection. And this is the standard sinusoidal Josephson effect that people know about in physics. That is, if you connect a superconductor to an insulator and between two superconductors. Okay. So again, we can sort of adapt this formulation into that superconducting framework. And what we showed is that the right-hand side, which is the dissipative quantum transport formulation, we kind of used to model something very interesting about the Josephson critical current oscillations, which have been seen in many experiments in the Rashba nanowire systems, where they noticed very interesting aperiodic oscillations, which we kind of could reproduce using what is called disorder and phase breaking effects into the formulation. Why I'm showing you all this is that this whole quantum transport formulation was initially developed to make, to model modern transistor devices. But you can see that once it was developed, it can be used for a whole array of problems, which is what I'm trying to hint at. And of course, next we are kind of working on, implementing this formulation to show how Majorana bound states are formed in these systems. This is, for example, a Rashba nanowire in the device region connected to two normal leads. And once you turn on the superconductivity, that's what's called the topological superconductivity, and you can see that the density of states in the system starts to go through these zero modes. As you can see this on the right panel, that you start seeing these sort of a braid systems where you start of seeing this sort of crossings, and this crossing is where the Majorana bound states happen. And when you actually plot the local density of states on the left panel, you can see zero energy modes sitting on the left and the right, which is an illustration of just, put it in the simulation, write the code. This is a toy problem. You can just show it that, when you put Rashba spin orbit coupling into the system, you can see these two nice Majorana zero modes sitting in the two left and the right edges. Yeah. So anyway, with this, I would like to show that some of the other works we've been working on, the spin momentum locking channels coupled to the hyperfine interaction in topological systems on the left panel. We also worked a bit on skyrmion oscillators last year. And something we are excited again is this topological regimes in the nanowire, and especially these superconducting systems. And of course, we've started working on 2D systems also. And recently we had last year a couple of works on semi-Dirac semi-metals and the fact that possibility of giant optical absorption too, and also various other effects, including thermoelectric effects. So with this, I'd like to sort of conclude the talk by kind of saying that, look, back in the 70s and 80s, electrical engineering people were working in this regime where we were talking about diffusive current flow and understanding things based on Ohm's law drift diffusion. But things have gotten this far in terms of modeling Intel transistors, but the whole thing is that the possibilities are infinite once we have this quantum transport. And today, hopefully, I've illustrated 2 or 3 possibilities of what can come out of quantum transport and understanding current flow through nanostructures. So with this, I'll kind of conclude. This is my group webpage, and here are a few people I collaborated with respect to these projects that I have talked about today. And special thanks to Ashwin, who was also given a talk a couple of days ago, and a few other colleagues from outside. And these are a few of my students who graduated after completing these works. And much of this work was done by Abhishek, who's now a faculty at IIT Roper, and another student who just joined Warwick as a postdoc, Warwick. And the superconducting work was done by undergrad, who's now at Stanford University. And so with this, I'd like to conclude, and thank you very much for giving me a chance to speak.
All right, I would now read out some of the questions that are written. I can see that already. The question is from Professor Prem Piramanagya. In MRAM community, researchers have studied double MGO magnetic tunnel junctions, but I don't know if they observed resonant tunneling. What's the key recipe for resonant tunneling? So in that line, I would also want to simply ask you this question. Does resonant tunneling help us in any way? I mean, is it like, does it improve TMR or something like that?
Thank you for this question. So theoretically, I believe resonant tunneling gives rise to very interesting filtering possibilities, because you have this sharp peak, which will correspond to one of the spin, and that's next one, which is probably, and the downspin does not have a corresponding peak. So automatically it should increase the TMR. But now why we are not seeing it? There are many reasons, right? Why it cannot happen. Theoretically, it can happen. But experimentally, what is the really difficult thing is that obviously the layers have to be so precisely placed. Maybe that's one reason. The other reason is possibly interfaces are not interfaces are causing problems. So I would like to know from Professor Prem about whether there are, I myself don't know this, but then there are these MGO layers, and possibly you could have MGO doped layers, I think, which form the resonant tunneling. This is what I don't know. If you can give me some examples of the experiments, that would be interesting. What is the sandwich comprise of?
So typically, it's cobalt iron boron is a magnetic layer. Then MgO is typically undoped.
Okay.
So it's about 1 nanometer thick.
Actually, I think 2 years ago there was some report of seeing an enhanced TMR, and I have to fish that out a bit. I didn't, but by putting a metallic layer in between two MGOs. But my belief is that the reason you don't see good effects is possibly the interface being completely scattering of some kind, and we have to see further. But there is strong possibility of using 2D van der Waals heterostructures instead. I do see that some experiments are slowly showing up.
So
But the physics is the same. I can't hear you, Professor Prem. Could you?
Okay, sorry. I'm going in the train. Maybe I'll not ask question.
Yeah.
Okay.
He's traveling, I guess. So
okay.
Maybe you can have the conversation later then. So
sure, I'd like to discuss with you. Yes.
Yeah, I wanted to ask you one more thing. The quantum computing technology that you're talking about, or your work is aimed at. So which kind of qubit technology is this?
Okay,
it's
good.
not the standard superconducting technology that IBM uses or Vijay uses in TIFR, right?
Thank you. Yeah, that's a good question. This is called topological qubits. Okay. So the IBM technologies are based on regular,
Josephson
transmon or
junction.
Josephson junction based, and that completely relies, that is a superconducting qubit.
Yes.
Either it's a flux qubit or there's a transmon qubit.
Transmon qubit.
Yeah, okay. So those are slightly different. They still believe in the same two-state system and rotating a two-state system to achieve your quantum computing. And so you have something called decoherence, which means that if I want my state to point in a particular, let's say orientation, it will wobble around that location, and that's called decoherence, and all quantum computing paradigms face it. Now, on the other hand, these Majoranas are very weird. So these are two Majorana states, okay? Now, let us say you have nearby such pairs sitting. The fact that you exchange two Majoranas gives rise to operation called a braid. And so quantum computing can be simply done by moving these Majoranas around. It's completely different from other forms of quantum computing. Because the Majoranas are guaranteed topological stability, so if you just move and form an operation like this, it is enough to complete the operation. I don't care how much impurities are around me. I just have to take this Majorana and this Majorana and swap them. And that's the operation. So that's the topological operation. It's one higher order. Like if I just swap them, and if I have 10 Majoranas and if I create a braid among them, I can create various gates that you need for quantum computing.
So you can get C0 gate and all the other gates.
All these are just, you just have to place Majoranas in a line, braid 1, braid 2, bring them and then measure.
How far has the technology progressed in Majorana-based quantum computing? Like, have people shown this experimentally that they build quantum processors?
Thank you so much. It is not even close to anywhere. Where we are right now is Microsoft has heavily invested in this technology through a few universities. The only thing they are not even sure of whether they have spotted those Majoranas. What they have seen is signatures, which everybody is saying that it could be an artifact too. So braiding is a far away thing.
So this is pretty behind the standard, even silicon. This is pretty behind even the silicon spin qubit technology, right?
Oh yes, it's far behind silicon spin qubit technology.
Okay.
Very far behind. In fact, a Nobel Prize will come if you demonstrate braiding. 100% sure. Because I'm sure the person who chose...
issue is not there. The decoherence issue is not there, basically.
Yes, because if you braid, that's all you need to do. Take this Majorana, push it there, push this guy here. I don't care how many impurities are around me. The operation is done, is the braid. As opposed to precisely pointing in one thing for the quantum computing. Other forms.
All right. Are there more questions?
Well, I had one question actually. I was just wondering when you saw this switching probability plots for one of the MTG, I think, I don't remember the system.
Yeah, I'll get it.
But how is it different to normal micromagnetic simulations?
Oh yeah, this, okay.
This one,
yeah, so physical, okay. So first of all, the currents...
Make it bigger. Can you make the thing bigger? Like, that's possible.
Yeah. Thank you for this question. Okay, so first of all, let me show you the formalism wise what is happening. It's first of all, this is where it's a microscopic calculation of the currents, but macro spin model applied to the LLG. So in a sense, yours, all that in our formulation, we need to calculate currents more precisely. But the LLG part is done in the macro spin model.
So you're not doing micromagnetics. You are just doing single domain.
Right, because you're taking into account the quantum mechanics of the system here, right? Whereas micromagnetics will take care of the magnet in a precise way.
Right.
But what is happening in that channel, all the quantum effects, is what we are doing. So therefore, ideally, we would like to couple this and micro to get the best possible answer. But
what is the blue and yellow colors curves that we're showing? They are not magnetic distribution. What was this? The blue, yellow color. I think that is where.
Oh, it's just a probability distribution. He was just asking, I think, about the methodology.
Yeah, what is the what probability?
Yeah, I mean, if somebody does this in micromagnetics, will he get similar results or different results?
We have to try it out, but But then we have to couple micromagnetics to our current, because for every time you change the magnet orientation, or in fact the distribution in the micromagnetics, it will affect the current flow. And so you have to couple quantum transport with micromagnetics.
I think in the Professor in Kaushik Roy's early neuromorphic papers on this domain wall devices, they say that they have done a coupled micromagnetic and NEGF. So when the thing that that Professor Ivan Prem was showing, that the domain wall moves, right? So if the domain wall moves, your MTJ's conductance will change. Yes. Our group, we just use unitary method there. I mean, we see how much the domain wall moves, and we just do unitary method. Lowest conductance, highest conductance, somewhere in between. We just do that.
That will be fantastic.
Kaushik was saying that in his papers, he refers to one of his earlier papers where they have put NEGF and
that's fantastic. That's great. I'll look it up. I would like to.
So see, somewhere in 2014 or 15, he has a paper where he has put NEGF and electromagnetics together. Yeah.
That's good. I'll look it up. Thank you.
Yeah. All right. So I think we are at the end of the session then, and we are it's about 5 p.m. So so Professor Ramesh's talk is at 5, or is it later on today?
His talk was in the morning.
Professor Ramesh's talk is in the morning.
It was in the morning. So
okay. Okay. So is there any more talk at 5 today?
There is. No, this session we have one more.
One more talk. We have one more talk, right?
Okay. Yeah, sure.
Thank you very much. Thank you.
Okay. So
thank you, Bhaskar, for this.
Thank you.
Thank you for so much for presenting. Yeah. So let me see. Yeah. So but the slides you sent me, I don't have any more persons. So this is just a contributor.
Just tell the title and you can ask Urmal.
Okay, so this is a presentation by our own IIT Delhi student Urmal Saran on effect of skyrmion phase in electronic fluctuations of platinum, cobalt, aluminum based multi-layered thin film sample. So Urmal, can you please start your presentation?
Yes, sir. So,
start sharing. Yeah. Go to full screen.
is it visible, sir?
Yes, it's fine.
Okay. 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 Good afternoon, everyone. I am Urmal Saran. So currently, I'm working as a PhD student in the Department of Physics, IIT Delhi. So today, I'll be talking about this effect of skyrmion phases in electronic fluctuation of platinum, cobalt, aluminum-based multi-layered thin film sample. So before starting, I would like to mention that this is a collaborative work. We have collaboration with Professor Vincent Cross, CNRS Thales, France. So all these samples device has been made in their lab, and this basic magnetic characterization, MFM, and this magnetic measurement has been done in their measurement. So we have basically performed this electronic transport measurement in our lab, which I am discussing today. So this the outline of my talk. So I will briefly introduce to this system. Then I'll talk about the sample details and magnetic characterization. Then I will introduce you to the fluctuation spectroscopy, which we are trying to use as a probe, as a technique, where we are trying to correlate between noise and skyrmion phases. So we'll be discussing about that. And after that, I will present this electronic transport measurement, and finally summary and conclusion. So magnetic skyrmion, we already know that these are vortex-like swirling spin configuration, so which are topologically stable. So this can be block-type skyrmion, nail-type skyrmion, depending on the domain level. So this skyrmion can be characterized by skyrmion number. Let me point. Okay. Skyrmion number can be defined by this equation. So this basically means that the number of times it wraps around a sphere if the spins of the skyrmions are mapped to a point. So this for skyrmion, these are basically plus or minus 1 depending on the core and surrounding polarity. There are several mechanisms where skirmion can be formed, but the main interaction, is like competition interaction between exchange and DM interaction. So in DM interaction, these two spins parallel try to align parallel. In DM interaction, the spins arrangement is such that it makes a 90-degree angle to make this energy, this Hamiltonian minimum. So initially, the skirmion was observed at very low field, very critical condition. But in recent advancement, even skirmion at room temperature has already been reported in a system where this thin ferromagnetic layer is sandwiched between these heavy metals. So in this kind of systems, this DMI, GLSMSK-Mori interaction appears due to the broken inversion symmetry at the interface and this presence of large spin orbit coupling due to the heavy metals adjacent to this thin layer. So in this kind of system, in some kind of system, this DMI interaction, is have additive nature. So if you take large number of stacks, you will get enough DMI, that this skirmion is stabilized at room temperature. So what's most exciting thing is its interaction with electrons. So this skirmion can be moved. This skirmion can be moved by some electron. If you pass some electron, the skirmion can be moved by spin transfer torque mechanism. So this electron also get deflected due to the emergent field of the skirmion, or you can say because of the Berry phase curvature, it attends when it traverses to this each spin of the skirmion. So this interaction between the skirmion and this electron, this fingerprint can be observed in Hall measurement data also. So this is the first topological Hall measurement data, where they have observed some deviation. You can see some deviation from ordinary and anomalous component. So after subtracting this anomalous and ordinary component, they have observed some peak-like features. So these are basically called topological Hall effect. This skirmions has huge potential because of their very small size, because of their very small this skirmion in the practical and this electrical detection and manipulation requires proper understanding of charge carrier transport behavior in this captive system, how this electron and this skirmion interacts, and if there is a lot of skirmion, how it behaves. So one needs to understand. So that where our motivation lies. So this is the sample. Layer structure which has been grown in CNRS Thales. We have got it from through Professor Cross. This fabrication of the device has also been carried out there. So using optical lithography followed by dry etching, followed by bonding we have done in our lab in IT Delhi, West bonding. So this magnetization, this magnetic behavior has also been studied in their lab. So this is the MOOC data, magnetization data. So this has been done in presence of out of plane magnetic field. And these are the MFM data, magnetic force microscopy image. So before going into they have followed the proper sequence. Proper field protocol has been followed before we're doing this MFM measurement. So first the sample is saturated at negative direction, and then you go back to the zero or positive field, and then starting the magnetic force microscope measurement. And this has been done very carefully using very low moment tip, so that this stray field coming out from the tip doesn't affect this spin texture inside the sample. So this is the MFM image corresponding to 0 millitesla field. So if you see, you can see some elongated structure, worm-like structure, red and blue structures. So these are the cycloid structure. And if the field is increased in positive direction, out of plane, positive outward direction, you can see some isolated circular structure along with the small, shorter worm-like structure. So this is kind of mixed patch, where the skirmion has already been stabilized, along with that some cyclone state is there. So they are doing this kind of measurement routinely. So these are practically these are skyrmion. So if the field is increased sufficiently higher at around 95 millitesla, you can see that the stabilization of this isolated stable skyrmion. So you can see a circular structure in this. So if the field is increased sufficiently higher at around 145 millitesla, we can see two things, that this density of the skyrmion is reduced, and the size also got reduced. So we want to understand just these are the different phase in presence of field. So can we detect in our electron transport measurement in our, so that's our motivation. So we have tried that. So I'll be showing in the next slide. So this is the Hall measurement. This is the Hall measurement. So this is the Hall resistivity plotted along with the magnetic field for applied current of 140 microampere of the current. So this is the room temperature data, and I forgot to mention that this MFM data which I showed in previous slide, this is also room temperature data. So to compare with the magnetization data, we have plotted normalized magnetization along with the normalized Hall resistivity data. So we can see that it almost follows this magnetization curve. So from here, we have tried to extract this topological component. So additional component, some additional component apart from this anomalous and ordinary component. So this is the total Hall effect. If we can write, this is the ordinary component, this is the anomalous component, and this is the topological component. So this anomalous component can be right in this type where this term is related to scattering independent term, and this is the skew scattering term. So we have considering the dominance of scattering independent term, we have fitted this calculated anomalous and ordinary Hall effect with the total Hall resistivity data. So if we can see that when coming from the positive field to negative field, we can see some deviation starting from this point, and we can see. So at this point, this is almost overlapping onto each other. So if we subtract this fitted anomalous and ordinary Hall effect data from the total Hall effect data, so we get this additional component which are getting. So this appears like some topological Hall effect, but this in literature, they have observed this topological Hall effect in both sides, both positive and negative side. So we are getting only at one side. So this peak is very small. So if we have, I have converted the in terms of written in terms of the Hall voltage. So this is only 1.9, around 2 micro volt. So what about the dynamical behavior of the charge carriers? So before going into that, so I would like to introduce you to the fluctuation about some noise spectroscopy. So noise is either information or it's some kind of nuisance. So it depends how you are looking into it. So suppose you have some resistors. So you are taking some time series data. So if this voltage fluctuation, if the voltage is totally random, so it is totally random, so it will appear like this. So this is the average voltage drops, and across that you will see some fluctuation. This is the time series data. If the signal is like random work with some correlation, full correlation, so this will appear like this. So this will not tell that much. So we need to convert it into frequency domain. So for physical system, this is not as rough as the random signal, not as smooth as the correlated one. So this is kind of intermediate in real system. So if you have some time domain data captured in between this time, we can Fourier transform, and we can get some frequency domain data. So it is interesting to ask that how much power is associated with the different part of frequency. So this power spectral density, this can be expressed using this formula. So this is the time series data. This is the noise power spectral density versus with respect to the frequency. So for the white noise, you can see that noise power is equally distributed over a wide range of frequency. In case of like 1/f nature, so you can see this kind of behavior, that is that at low frequency, this power is much higher. And similarly for 1/f square. So in case of in case of for stationary process, this voltage power spectral density can be related to this autocorrelation function using this formula, Wiener-Kenchin theorem. So this is a measure of this memory of electronic process. So what remains after some time? What remains from the fluctuation after some time? So that is, so this is basically observed in low frequency dynamics of charge carriers. So from the Hooke's model, this SV by power spectral density by V square is proportional to this. So this gamma is equal to Hooke's parameter, which indicates the strength of the noise. This n is carrier density, omega is the volume. So this n omega basically says the total number of charge carriers, and a to the power alpha. So for a particular system, this is constant, this is constant. So only for particular system, we can write this, this SB by B square is proportional to 1 by F alpha. So alpha is this frequency exponent. So in the literature, it varies from 0.8 to from 0.14. So let's go to our data, what we have measured. So before that, this is the noise measurement setup which we are using. So I'd like to emphasize, like we are using 5-probe technique, where we can control the current independently in the 2 branches, so that the total voltage drop is minimized, total average voltage drop is minimized, and we can do the measurement with a very high sensitivity. And other tools are like lock-in amplifier, which captures the time signal data, this spectrum analyzer. So we don't do ourselves this FFT data. So the spectrum analyzer takes care of that. And we have very low noise preamplifier. So now let's go to our data. So this y-axis is power spectral density, and this x-axis is frequency. So this is the spectrum at different currents, at a different current. So we can see that this spectrum is changing, this noise value is changing with different current. So to calculate the noise value at particular frequency, what we have done, we have fitted this equation with some straight line, and from there we have obtained this intercept and alpha value, which I mentioned in earlier slide, alpha value. And from there we can calculate this parameter, we can calculate the noise value corresponding to any feed. So if we see that this noise value at 1 Hz, so we have taken noise value at 1 Hz around that point from all the currents. So if we plot that, so we see that this noise is, this power spectral density is changing linearly with the square of the current. This ensures that whatever we are measuring, that is coming from the sample and not due to extrinsic source. So after that, we have done magnetic field dependent noise. So this is the power spectral density in and y-axis, x-axis this frequency. So on this. So if we see that this at around 85 millitesla, where in MFM also we saw some Skarman pages at 86.5 something millitesla. So we see that around that point this noise is also increasing. So that is interesting. We have repeated, we have done a lot of measurement using different scan, which I am not showing here, but these are reproducible, that around at that field it's increasing. So when we plot this field, so this measurement is still going on. So we have not completed yet. Yeah, that's going on. So if we see that variation, this variation of power spectral density at 1 Hz with respect to the field, we see that this is increasing. So total increase with respect to this point is around 38%. So this is where what we are trying to correlate with the Skarman pages. So maybe this increment in the noise is because of the stabilization of Skarman pages. So we are onto it. So we are trying to understand that in details. Next, we have plotted. We have plotted this alpha value with the field. So its variation, it shows that this alpha value is some increasing trend, so it's increasing with the field, and after certain point, after 80 or 85 millitesla, it's becoming flat. But what does it mean? What does it mean basically? So this, when alpha value is larger, the slope becomes steeper. That means that noise value at low frequency increases. That means that this carrier dynamics becomes slower, becoming slower at higher field. So that also we are trying to understand that. So this is the observation. So with this, I would like to conclude. So we have basically observed stabilize the Scarmian phase at around 90 millitesla out of plane magnetic field. We have observed some topological Hall light signature. We have measured this electronic fluctuation, and we have seen that this stabilization of the Scarmian and this increment of the electronic fluctuation is correlated. We have also seen that when this Scarmian is stabilized in the sample, this dynamics of the electrons become slower. So that is interesting, and we're trying to understand. And we have also observed this low frequency broadband peak at around 100 millihertz, which we actually don't know where it is coming from, but that is also we are trying to understand. So finally, I would like to acknowledge my supervisor, Dr. Printodas Yogesh Kumar, who is helping me in the measurement, Professor Vincent Cross for providing us the sample. Without whom the measurement would not have been possible, and Fernando Ajejas, Nicholas Raiden for this basic characterization and fabrication of the device, and finally this CSR for research fellowship. And thank you for your attention. Thank you.
Thanks, Hurmal, for the nice talk. I would like now ask people to ask questions. I do not see any question on this chat forum, so maybe people can unmute the microphone and ask questions. Okay, don't hear anything. Professor Mudili, do you have any question?
Yeah, I was wondering, did you see, you said that the Scarmians are stabilized at certain 50 millitesla or some field, right?
Yes.
So when the Scarmian are stabilized, is there anything change at that point in the noise that you observed, the alpha parameter or something?
Oh, it got hanged.
Go, just
okay.
Yeah, this one.
So yeah, so if we see the MFM data, so we can see the stabilization of Scarman at around 85 millitesla. So so starting from here, so we can see some dense structure at around 95 millitesla. So it's in between the some range. So and in noise measurements also we see that this noise is increasing with the field. So suddenly, so at around 85 millitesla, you can see increment. So we have not completed the total range, so we need to check that also. So, but it seems that these are correlated, strongly correlated. This seems.
I have one question. At what temperature did you measure the topological Hall effect signal?
This, sir, we have done in room measurement. We have planned to perform in the lower temperature also, but this is the room temperature measurement.
How do you see? How do you know this topological Hall effect? Can you open the plot once again?
Yes. Yes. So
yes.
this is
how
the
do you know
raw
this topological Hall effect here, and it's not just simple anomalous Hall?
We have calculated from this magnetization curve this anomalous component and ordinary component. After subtracting that, we get.
I understand, but how did you calculate the anomalous and ordinary Hall effect?
So just this is the total Hall effect. So at saturation, so obviously there will be no topological Hall component. So in saturation, so this will be like this, and we are considering this term as the dominant factor. So rho xy is equal to basically is equal to r0h and b rho x square m. So if we plot rho x y by h and rho b rho x square m by h, so this will become a linear equation. So from their slope and intercept, we get this R0 and B component. It would be better if I could show that, but
is rho xx also a function of h?
Yes, but this change is very small. So we have observed, we have measured that thing also, but total change in the resistance is very small, 0.08% only, total change in magnetic resistance.
I need to go through the written form of this paper later on to understand this better. But I see a question over here. How do you isolate line noise from noise spectroscopy measurement? Have you done any specific test for that? So the question is, how do you separate line noise from noise spectroscopy?
Line noise is basically flat. So we basically measure the X component of the noise. Whatever in lock-in, we get X component, Y component. So X component shows some feature and Y component is flat. So that is the background of the sample that contains from the instrumental noise, from the line noise that contains that Y signal. So during the analysis, we are subtracting the X component, the Y component from the X component. And yeah, line component is there, so you will definitely get peak around 50 hertz. So you can't get rid of that completely. Yes.
Okay. Any more questions?
So in that, I have one more question. That noise plot that you're showing. So is it 1/f or 1/f square? What is the dependence? Yeah.
This is 1/f. So 1/f. So alpha value is around 0.9 to 1.27 maximum.
So this is directly measured using the spectrum analyzer, right? Not
yes.
not from
We get we get directly from the spectrum analyzer.
There's something going on at very low frequency. I don't know if that is real or artifact. It's kind of flat.
Yes. Yes. So we have also performed this measurement at very low span. So in that case, the resolution, frequency resolution is improved. And we have observed this, which I mentioned, this broadband low frequency peak. So we still don't know. We don't understand properly why it is coming. But yeah, it's real. We have observed in small span also.
It's also changing with the current. So it seems the feature is there and the level is changing.
Yes, level is changing, but the feature I need to check, sir, carefully, so that I have not checked yet.
Yeah, can I comment into this here?
Yes, please.
Yeah. So we actually checked very carefully about this low frequency feature, as Hurmul Saran was saying. Right now, we do not understand that this is a real feature actually, because we have tried with other different samples where we don't have any signature in the low frequency, which is completely flat. Here we are seeing this feature. So there are several systems where you see this kind of Lorentzian peak, which typically comes. Typically, you see if you have certain kind of fluctuator, with a certain frequency. So one can derive some frequency dependence, try to understand energetics of that. We have not done this analysis so far. Actually, our work got affected due to the COVID, but this is what we are looking after right now. Finally, I mean, this just to comment, this is a real feature in this system.
It's very interesting results.
Yeah.
Okay.
Yes, I would agree. Yeah. Okay. All right.
There's
so
no more question, I guess. So
yeah, I think we are. Yeah. So we are done with this session, and so maybe if there are no more questions, we can conclude the session. We will thank all the speakers for finding out time to give the talks, and for everybody else to attend and ask questions. Yeah. So that's okay, right? We can conclude the session now.
Yeah.
All right.
Yeah. Thank you. So we also thank Professor Devanjan Bhaumik for agreeing to chair this session. And so this session is officially
over.
Closed now, and we speak with them and thank all the speakers.
Yeah.
And this is also the last session of this conference. So.
Oh, okay. So there's nothing after this. At 5 p.m. there is nothing there today. Like not
there is
Spinterface, but general.
There is some kind of discussion concluding session.
Okay.
But that is not a scientific session.
Oh, okay. No scientific session.
So actually the concluding session, I think they have announced we're going to announce this guest posters.
Okay. So you got my this thing, all that. Everything is fine, no? You got the feedback.
I have already sent.
Very good. Okay. Thanks.
Okay. Thank you, everyone.
Yeah.
Thank you.
Thanks everyone for joining.
Hopefully my thing was also in time.
Say that again. Hello. Was that
Pintu was saying something.
No, I think he's gone. Yeah. Okay. All right.
Yeah, I just telling that that hopefully you received this poster evaluation in time from my side.
Yeah. I received from all of you. Thank you very much for your time.
Yeah. Okay. Bye.
Bye.
Yeah, no problem. It was interesting. Yeah.
Okay, thank you. Bye.
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 Thank you.